The past is gone. Everyone knows this. It happened. It's over. It's behind us. We remember it, sure, but it doesn't exist anymore. Right? Wrong. Completely, fundamentally wrong. And Richard Feynman, one of the greatest physicists who ever lived, can explain exactly why. The past isn't gone. It never left. It's still here, right now, woven into the fabric of everything you see and touch. And once you understand why, you'll never think about time the same way again. Let me show you what I mean. Right now, you're sitting somewhere, reading this, existing in what you call the present moment. You think of now as a single point in time, a razor's edge between past and future. The past is behind you. Done. Finished. The future hasn't happened yet. And you're stuck in this tiny sliver called now. But here's the thing Feynman understood. That picture is wrong. Completely wrong. Time doesn't work that way. The present moment isn't a point, the past isn't gone, and the future isn't waiting to happen. It's all more connected, more intertwined, more simultaneous than you've ever imagined. Now, Feynman had this incredible gift for taking the most mind-bending ideas in physics and making them feel obvious, almost simple. And when it came to time, he saw something that most people miss. He saw that when we talk about the past being gone, we're making an assumption, a big assumption. We're assuming that time flows, that it moves forward like a river, carrying us from past to future. That moments happen and then disappear, replaced by new moments. We think of time like pages in a book, where you're always on the current page, and the previous pages, well, they're behind you. You can remember them, but they don't exist in the same way the current page exists. But what if that's not how it works? Here's what Feynman would tell you. In physics, in the actual mathematical description of reality, time doesn't flow. It just is. All of it. Past, present, future, they're all equally real, equally existing. They're all part of the structure of the universe, like different locations in space. Think about it this way. You don't think Los Angeles stops existing when you're in New York. You don't think New York disappears when you travel to Los Angeles. They're both real places. They both exist simultaneously. You just can't be in both at once. Time, according to physics, works the same way. Yesterday is a place in time. Tomorrow is a place in time. They're both real. They both exist. You just can't be in both at once. You're located at today, but that doesn't make yesterday any less real than Los Angeles is when you're in New York. Now, I know what you're thinking. That sounds crazy. You can go to Los Angeles. You can get on a plane and fly there. But you can't go to yesterday. You can't travel to the past. So how can they be the same? And that's a fair question. But here's the thing. The reason you can't travel to yesterday has nothing to do with whether yesterday exists. It has to do with the structure of space-time and the laws of physics. There are restrictions on how we can move through time, just like there are restrictions on how we can move through space. You can't travel faster than light through space. That's a law of physics. But that doesn't mean the places beyond your light cone don't exist. Similarly, you can't move backward through time under normal circumstances. But that doesn't mean the past doesn't exist. Feynman understood this at a deep level. He worked with something called the path integral formulation of quantum mechanics. And in that formulation, particles don't just take one path through space-time. They take all possible paths, every path, simultaneously. A particle going from point A to point B doesn't just travel in a straight line. It explores every possible route, including ones that loop backward in time, ones that zigzag wildly, ones that take detours through every corner of the universe. And all of those paths contribute to the final result. All of them are real, in a sense. Now, the paths that go backward in time, the ones that violate our normal sense of causality, they mostly cancel out when you add them all up. They're there, but they interfere with each other and don't contribute much to what we observe. But they're not forbidden. They're part of the mathematics. They're part of how the universe actually works at the quantum level. And this reveals something profound. The distinction between past and future, the arrow of time that feels so obvious to us, it's not fundamental. It's not built into the basic laws of physics. The equations work the same whether time runs forward or backward. If you filmed the interactions of particles and played the film in reverse, you couldn't tell the difference. The laws don't care. So where does our sense of time's arrow come from? Why does the past feel different from the future? Why do we remember yesterday but not tomorrow? Feynman knew the answer. It comes from entropy, from the second law of thermodynamics, from the fact that disorder increases over time, but that's a statistical law, not a fundamental one. It's about probabilities and large numbers of particles, not about the deep structure of time itself. Let me explain what that means. Imagine you have a box of gas molecules. At the start, all the molecules are in one corner of the box. That's a low entropy state, a high degree of order. Now you let the molecules spread out. They fill the entire box. That's a high entropy state, more disorder. And here's the key. This process is much more likely to happen than the reverse. It's incredibly unlikely that all the molecules would spontaneously gather back in one corner. Not impossible, just fantastically improbable. So when we watch this system, we see entropy increasing. We see order turning into disorder. And we say time is moving forward. But notice something. The molecules themselves don't know about time's arrow. Each collision, each interaction between molecules could just as easily run backward. The laws governing those collisions are time-symmetric. The arrow of time emerges from statistics, from the fact that there are vastly more disordered states than ordered states, so systems naturally evolve toward disorder. That's it. That's where our sense of past and future comes from. Not from time itself, but from entropy. Now, here's where it gets interesting. Because of this, because the arrow of time is statistical and not fundamental, there's a sense in which all moments in time are equally real. The past hasn't gone anywhere. It's still a part of space-time, still a valid location in the four-dimensional structure of the universe. When physicists write down the equations describing the universe, they include all of time, past, present, future. It's all there in the mathematics. It's all part of the solution. The universe, from this view, is a four-dimensional object. 3 dimensions of space, 1 dimension of time. And just like every point in space is part of the object, every moment in time is part of the object. The Big Bang is part of it. The moment you were born is part of it. This moment right now is part of it. The heat-death of the universe billions of years from now is part of it. All of it exists. All of it is real. We just experience it sequentially because of how our consciousness works, because of how memory and causality function in a universe with increasing entropy. Feynman had this way of making you see that our everyday intuitions about time are parochial, limited. We think time flows because we experience it flowing. We think the past is gone because we can't go back to it. But those are facts about us, about our perspective, about the limitations of our consciousness and memory. They're not facts about time itself. It's like the bug on the ball from that other example. The bug thinks its universe is two-dimensional because it can't perceive the third dimension. We think time flows because we can't perceive all of time at once, but the flow is an illusion created by our particular way of experiencing reality. Now, let me show you something that'll really bend your mind. You know how we think of ourselves as moving through time. We imagine we're traveling forward, 1 second per second, from past to future. But there's another way to think about it. What if you're not moving through time at all? What if you exist at all moments simultaneously, and consciousness is just the experience of different time slices of that four-dimensional object that is you? Let me explain. Imagine your entire life as a long, worm-like object stretching through space-time. One end is your birth, the other end is your death. And in between, Every moment you've ever experienced, every moment you will ever experience, they're all part of this object. This four-dimensional worm is the real you, the complete you. Now, at each moment, you're only conscious of a thin, three-dimensional slice of this worm. You experience one moment at a time. But that's just your perspective. From outside time, from a God's eye view, all of you exists at once. You at age 5, you right now, you at age 90, all equally real, all equally part of the structure. This is called the block universe view, and it's a natural consequence of Einstein's special relativity, which Feynman knew intimately. In special relativity, there's no universal now. Different observers moving at different speeds will disagree about which events are simultaneous. What I call now, you might call the past or the future, if we're moving relative to each other. And if there's no universal now, if simultaneity is relative, then the present moment isn't special. It's just a particular slice through space-time that you happen to be experiencing. And that means the past and future are just as real as the present. They're other slices through the same space-time. Okay, now watch this, because this is where Feynman's genius really shines. He didn't just accept this abstract picture. He showed how it actually works in practice, how it explains real phenomena. Take antiparticles, for example. An antiparticle is like a normal particle, but with opposite charge. The antiparticle of an electron is a positron. Same mass, opposite charge. Now, Feynman had this incredible insight. He realized that you can think of an antiparticle as a regular particle moving backward in time. I'm not kidding. This is actual physics, not science fiction. When a positron moves forward through time, it looks exactly like an electron moving backward through time. The mathematics is identical. And Feynman used this idea to develop his famous Feynman diagrams, which are pictures showing how particles interact. In these diagrams, time is usually shown going upward. A particle moving up is going forward in time. A particle moving down is going backward in time, which we interpret as an antiparticle moving forward in time. Now, here's the beautiful part. This isn't just a mathematical trick. It's revealing something deep about the nature of time and particles. It's showing that the distinction between past and future, between particle and antiparticle, is more subtle than we thought. It's showing that time-reversed processes are just as valid as time-forward processes. And it's showing that the past is still there, still part of the structure, still contributing to the present. Because when you calculate what happens in a particle interaction using Feynman's methods, you're summing over all possible paths, including the ones that loop backward in time. Those backward-in-time paths correspond to antiparticles, and they're essential to getting the right answer. Without them, the calculations don't work. The past, in this sense, is actively participating in the present. Let me give you another example. Light. You see light from the sun, right? That light was emitted 8 minutes ago because it takes 8 minutes for light to travel from the sun to Earth. So when you look at the sun, you're seeing the past. You're seeing what the sun looked like 8 minutes ago, not what it looks like now. And when you look at distant stars, you're seeing even further into the past. Some stars are thousands of light years away. The light you're seeing was emitted thousands of years ago. That star might not even exist anymore, but its light is still reaching you. Now, here's the thing. That light, that information from the past, it's still real. It's still here. It's still part of the universe. The past is encoded in the light traveling through space. It's not gone. It's in transit. And not just light. Gravitational waves work the same way. When two black holes collided billions of years ago, they sent ripples through space-time. Those ripples traveled across the universe, and we detected them in 2015 with LIGO. That event from the distant past reached us in the present. The past, in the form of those waves, crossed billions of years to arrive here and now. So the past isn't gone. It's embedded in the universe. It's in the light reaching us from distant stars. It's in the cosmic microwave background radiation, the afterglow of the Big Bang, which we can still detect today. It's in the fossils in the ground, in the rings of trees, in the layers of ice in glaciers. Every part of the universe carries information about its past. The past is written into the present. It's not separate, it's not disconnected, it's part of the continuous structure of space-time. Now, Feynman would push this even further. He'd say that when you interact with something, when you touch a table or see a tree, you're not just interacting with that object in the present, you're interacting with its entire history. The atoms in that table were forged in stars billions of years ago. Those stars exploded in supernovas, scattering the atoms across space. Those atoms eventually came together to form the Earth, and then the wood, and then the table. Every atom carries that history, and when you touch the table, you're touching all of that. The past is physically present in the structure of matter. Here's another way Feynman thought about it. He was obsessed with the idea that the universe might be deterministic, that the present state of the universe completely determines both the future and the past. If you knew the position and velocity of every particle in the universe right now, you could, in principle, calculate what the universe looked like at any point in the past and what it will look like at any point in the future. The information is all there. It's encoded in the present. Quantum mechanics complicates this, adds uncertainty, but the basic idea holds. The past isn't erased. It's compressed, encoded, preserved in the structure of the present. Let me tell you something Feynman said that really captures this. He once remarked that from the perspective of a photon, a particle of light, no time passes at all. A photon travels at the speed of light, and at the speed of light, time dilation becomes infinite. From the photon's perspective, it's emitted and absorbed in the same instant. It doesn't experience duration. For the photon, the entire journey from a distant star to your eye happens in zero time. Think about what that means. For the photon, there is no past and future. There's only one eternal moment. And in that moment, everything that we perceive as separated in time is simultaneous. The star emitting the light traveling through space, you seeing the light, all the same instant from the photon's point of view. Now, obviously, we're not photons. We experience time. We have memory, causality, a clear sense of before and after. But Feynman's point is that our experience isn't the only valid perspective. The laws of physics describe a universe where time is more flexible, more relative, more interconnected than our intuition suggests. And when you take those laws seriously, when you follow them to their logical conclusions, you find that the past doesn't disappear. It remains as a valid part of space-time, as real as the present, just located at different coordinates in the four-dimensional structure of the universe. Here's the thing, though, and Feynman would be the first to admit this. This doesn't mean you can change the past. You can't go back and undo what happened. The past is fixed, frozen, unchangeable. Not because it's gone, but because it's already part of the structure. It's like asking if you can change New York while you're in Los Angeles. You can't. New York is what it is, whether you're there or not. Similarly, yesterday is what it is, whether you're there or not. The block universe view says all moments are equally real, but it also says they're all fixed. The past exists, but you can't alter it. Time travel, in the sense of going back and changing things, creates paradoxes that physics seems to forbid. But, and this is crucial, the past still affects the present. It's still causally connected to now. Everything that happened before led to this moment. The past is the foundation on which the present is built. And in that sense, it's not gone at all. It's more present than ever. Every memory you have, every scar on your body, every skill you've learned, every person you've met, all of that is the past persisting in the present. You are, in a very real sense, a living record of your past. The atoms in your body are remnants of dead stars. The patterns in your brain are shaped by experiences you had years ago. The past lives in you. It's not behind you, it's inside you. Now, let me address something that might be bothering you. If the past still exists, why can't we access it? Why can't we go back? Why does it feel gone even though physics says it's still there? And the answer comes back to entropy, to the arrow of time, to the statistical nature of why we experience time the way we do. Imagine a movie playing forward. You see events unfolding, things happening in order. Now play the movie backward. You see the same events, but in reverse. The physics of individual particles doesn't care which direction is which. But when you have many particles, when you have macroscopic objects like people and planets, entropy gives you a direction. Things break. They don't unbreak. Eggs shatter. They don't spontaneously reassemble. And our consciousness, our memory, is tied to this entropy increase. We remember the past because low entropy states evolve into high entropy states, and that evolution creates records, creates memory traces, creates the feeling of time passing. But here's the kicker. From the block universe perspective, memory isn't about the past being gone and then recovered. Memory is about different time slices of you having access to information from other time slices. Your brain right now contains patterns that were created by your brain 5 years ago. That's a physical connection across time. It's not mysterious. It's just information being preserved in a structure that persists through time. And that persistence is possible because the past and present are part of the same continuous space-time. If the past were truly gone, if it didn't exist, there would be nothing to remember. The fact that you can remember the past is evidence that it's still there, still part of the structure. Now, Feynman loved thought experiments. He loved taking ideas to their extremes to see what they revealed. So let's do one. Imagine the universe is like a film reel. Every frame is a moment in time. When you watch the film, you see one frame after another, and you perceive motion, change, a story unfolding. But the film reel itself, the physical object, contains all the frames simultaneously. They all exist at once on the reel. You watching the film corresponds to you experiencing time, but the film doesn't care about your experience. All the frames are equally part of the film. The universe, according to this view, is like that film reel. All moments exist simultaneously in the structure. We experience them sequentially, frame by frame, but they're all there. The past frames aren't gone. They're still on the reel. We just can't rewind and watch them again because our consciousness only moves forward through the frames. Okay, here's another mind-bending thing Feynman understood. Quantum mechanics, the theory governing the behavior of particles at the smallest scales, has this weird feature. Particles don't have definite properties until they're measured. Before measurement, an electron doesn't have a definite position or velocity. It exists in a superposition, a combination of all possible states. And when you measure it, the superposition collapses, and you get one definite outcome. Now, here's the strange part. The act of measuring affects not just the present, but also the past. There's an experiment called the delayed choice experiment. You send a photon through a setup where it can take 2 different paths. But you don't decide how to measure it until after the photon has already committed to a path. And what you find is that your choice of measurement in the present seems to determine which path the photon took in the past. It's as if the present reaches back and affects the past. Now, this doesn't mean you can send messages to the past or change history. The mathematics prevents that. But it does mean that the relationship between past and present is more entangled than we thought. The past isn't a fixed, independent thing that's completely separate from the present. The present helps determine what the past was. And this makes sense in the block universe view. If all of time is part of one structure, then correlations can exist across time, not just across space. The past and present are connected, not just causally, but in deeper ways revealed by quantum mechanics. Feynman worked extensively on quantum electrodynamics, the theory of how light and matter interact, and in QED, the fundamental entities are events in spacetime. An electron here emits a photon. The photon travels. Another electron there absorbs the photon. Each of these events is a point in spacetime, and the theory calculates the probability of different sequences of events. But notice what's happening. The theory treats time and space on equal footing. Events are located in space-time, not separately in space and in time. The past events, the present events, the future events, they're all part of the same calculation. They all contribute. The past isn't gone from the equations. It's right there, interacting with the present and future through the rules of quantum mechanics. Let me give you a concrete example. When an electron and a positron annihilate, they produce two photons. From one perspective, you have an electron and a positron coming together and turning into light. But from another perspective, using Feynman's time-reversed view, you have a single electron that emits a photon, reverses in time, emits another photon, and then continues forward in time. Both descriptions are valid. Both are different ways of looking at the same space-time events. And in the second description, the electron is literally traveling backward in time for a brief interval. The past and future are intertwined. The particle visits the past and then returns to the present. This isn't science fiction. This is how physicists actually calculate what happens in these interactions. And it works. The predictions match experiments to incredible precision. Now, here's something beautiful. Feynman didn't just accept these strange ideas, he used them. He turned them into tools. His diagrams, his path integral formulation, his whole approach to quantum mechanics was based on taking the idea of particles exploring all possible paths through space-time, including backward in time, and using that to make predictions. And those predictions are the most accurate in all of science. Quantum electrodynamics predicts the magnetic moment of the electron to 11 decimal places, and it matches experiments. That's not a coincidence. It's because the theory is capturing something true about reality. And part of that truth is that the past isn't gone. It's part of the structure that determines what happens. Now, you might be wondering, okay, fine, the past exists in some abstract sense. But so what? What does this mean for me? How does this change anything? And that's a fair question. On a practical level, it doesn't change much. You still can't go back and fix your mistakes. You still have to live with the consequences of your choices. You still age, grow, and eventually die. But on a deeper level, it changes everything. It changes how you think about your life, your identity, your place in the universe. If the past still exists, then every moment you've ever lived is still real. It's still part of the structure of space-time. Your childhood, your first love, your greatest triumphs, your worst failures, they're all still there, not just as memories, but as actual events, actual parts of the universe. You're not leaving them behind. You're carrying them with you in a sense, because you're a four-dimensional object stretched across time, and every moment is part of that object. Here's another way to think about it. You know how sometimes people say, "I wish I could go back to that moment"? Well, in a sense, you never left. That moment still exists. You're just not conscious of it right now because your consciousness is located at a different point in the four-dimensional structure. But the moment itself is still there, still real, still part of space-time. And in a strange way, that's comforting. Nothing is ever truly lost. Every experience, every person you've loved, every beautiful sunset you've seen, it's all still part of the universe. It exists eternally in the structure of space-time. Feynman had this profound respect for the universe as it actually is, not as we wish it were or imagine it to be. And when you look at the universe as it actually is, when you follow the mathematics and the experiments, you find that time is not what you thought. It's not a river carrying you from past to future. It's a dimension, like space, and all points in that dimension are equally real. The past exists, the future exists, and you're a thread woven through all of it, experiencing it moment by moment, but existing all at once in the greater structure. Now, let's talk about something else. Because there's a related idea that Feynman also thought about. If the past still exists, does that mean the future already exists too? And here's where things get tricky. In the block universe view, yes, the future is just as real as the past. It's already there, already part of the structure. But, and this is important, that doesn't mean you don't have free will. It doesn't mean your choices don't matter. Here's why. Even if the future is fixed, even if it's already determined, you don't know what it is. You still have to make choices. You still experience uncertainty. And your choices are part of what determines the future. They're part of the causal chain. So the future might be fixed, but it's fixed in part by the choices you make right now. It's not that the future is written and you're just reading the script. It's that the future is written and you're one of the authors. Think about it this way. In a book, every page exists simultaneously. The ending is already there from the moment the book is printed. But when you read the book, you experience it page by page. You don't know what's going to happen. And the characters in the book, if they were conscious, would experience themselves making choices, even though those choices are already determined by the text. The block universe is like that. All of time exists, but you experience it sequentially, and your experience includes making choices, feeling uncertainty, and living as if the future is open. And from your perspective, the future is open. You just happen to live in a universe where that perspective coexists with the deeper reality of all time existing at once. Feynman wouldn't want you to get too caught up in the philosophical implications, though. He was pragmatic. He cared about what you could calculate, what you could test, what you could predict. And the block universe view, the idea that past and future exist, it's useful because it gives you the right answers. It explains antimatter, it explains quantum interference, it explains why the laws of physics are time-symmetric, even though we experience time as asymmetric. It's a tool for understanding the universe, not a source of existential dread. But let me come back to the main point. The past isn't gone. It's still here, woven into the structure of space-time, encoded in the present, influencing everything that happens now. Every light ray from a distant star, every atom in your body, every memory in your brain, it's all a connection to the past. The past is not behind you. It's beneath you, around you, inside you. It's the foundation on which the present is built. And that's not just poetry. That's physics. Now, here's something Feynman would absolutely insist on. Don't take my word for this. Don't take anyone's word for it. Look at the evidence. Look at the experiments. Look at the mathematics. Special relativity shows that simultaneity is relative, that there's no universal now. That's been tested. Time dilation is real. Clocks on airplanes run at different rates than clocks on the ground. That's been measured. Quantum mechanics predicts interference effects that only make sense if particles explore multiple paths through space-time, including backward in time. Those predictions have been confirmed in countless experiments. The cosmic microwave background radiation, the afterglow of the Big Bang, is light that's been traveling for 13.8 billion years. We can detect it. We can measure it. The past is not theoretical. It's observational. So when I say the past still exists, I'm not speculating. I'm describing the universe as physics reveals it to be. And Feynman, more than anyone, taught us to trust the equations, to trust the experiments, to let reality surprise us. He didn't cling to intuition when intuition was wrong. He followed the evidence wherever it led. And the evidence leads to a universe where time is a dimension, where all moments are equally real, where the past is not gone but preserved in the eternal structure of space-time. Here's the deepest part, and I want you to really sit with this. You are not a thing moving through time. You are a process. You are a pattern of matter and energy that persists and changes across time. The you of 10 years ago is not gone. That version of you still exists at its point in space-time. And the you of 10 years from now, that version already exists too, at its point in space-time. What you experience as the present moment is just your consciousness located at one particular slice of this four-dimensional structure. But the whole structure is you. All of it, from birth to death, that's the real you, the complete you, and every part of it is equally real. This is what Feynman understood. This is what physics tells us. And it's not sad, it's not diminishing, it's the opposite. It means every moment matters. Every experience is eternal. Every choice is part of the permanent structure of reality. You're not a fleeting spark in an indifferent universe. You're a thread in the fabric of space-time, woven into the cosmos itself, existing forever in the only way anything can exist, as part of the four-dimensional tapestry of everything that is, was, and will be. Now, let me be clear about something. I'm not saying you can visit the past. I'm not saying you can change it. I'm saying it exists. It's real. It's part of the universe. And that means something. It means the universe has memory. It means information is preserved. It means the story of everything that's ever happened is written into the structure of space-time and can never be erased. The past is not gone. It's just not accessible to you right now in the same way that distant places in space are not accessible to you right now. But they exist. They're real. They're part of the same universe. Feynman had this wonderful way of making you feel small and large at the same time. Small because the universe is vast and strange and operates according to rules that don't care about your intuitions. Large because you, tiny as you are, can understand those rules. You can do the math. You can run the experiments. You can figure out how reality actually works. And when you do, you find that reality is far more interesting than you imagined. Time is not a river. The past is not gone. The future is not empty. It's all one structure, one magnificent, interconnected whole. And you're part of it. So what's the takeaway? What should you do with this knowledge? Nothing, necessarily. You still live your life the same way. You still make choices, have experiences, move forward through time. But maybe, just maybe, you see it differently. Maybe you appreciate each moment a little more, knowing it's not fleeting, not disappearing, but becoming part of the eternal structure. Maybe you're a little less haunted by the past, knowing it's not gone, just located elsewhere in space-time. Maybe you're a little less anxious about the future, knowing it's already part of the structure, already woven into the fabric of reality. Or maybe you just think this is all crazy, and that's fine too. Feynman would be the first to tell you that physics is weird, that it doesn't match our intuitions, that it's okay to be confused or skeptical, but he'd also tell you to keep asking questions, keep looking at the evidence, keep following the logic wherever it leads, because that's how we figure things out. That's how we discover what's true. Here's the final thing I want you to understand. When we say the past isn't gone, we're not being mystical. We're not being poetic. We're being literal. The laws of physics, the mathematical descriptions of reality, they include all of time. Past, present, future. It's all there. It's all part of the solution to the equations. And those equations work. They predict things. They explain things. They've been tested to incredible precision. So when they tell us that the past still exists, we should listen. We should take it seriously. We should let it change how we think about time and memory and existence. The universe is not what you thought. Time is not what you thought. The past is not gone. And once you understand that, once you really grasp it, you can't unsee it. You see the universe for what it is, a four-dimensional structure where every moment is real, every event is eternal, and nothing is ever truly lost. That's what Feynman saw. That's what physics reveals. And that's the truth about time. So the next time someone tells you the past is gone, you can smile and think, no, it's not. It's still here. It's always been here. It's part of the structure of space-time, woven into the fabric of reality, existing eternally in the only way anything can exist. The past isn't gone. It's home. It's where we came from. It's what made us. And it's still out there, still real, still part of everything. That's not philosophy. That's physics. And Richard Feynman, genius that he was, understood it better than almost anyone. Now, let me tell you something else that Feynman would want you to know. This idea that the past still exists, it's not just about abstract physics. It has real implications for how we understand causality, how we understand the relationship between events. You see, we think of cause and effect as a one-way street. The past causes the present causes the future. It's a chain, each link connected to the next. And that's mostly true. But in the quantum world, in the world of particles and fields, causality is more subtle. Events can be correlated across time in ways that don't fit our simple cause and effect picture. Feynman worked on this extensively when he developed the theory of quantum electrodynamics with Julian Schwinger and Shinichiro Tomonaga. They showed that you could think of an interaction between particles as an exchange of virtual particles. An electron here creates a virtual photon. That photon travels across space and time, and another electron there absorbs it. And in the mathematics, that photon can travel forward or backward in time. It can connect events in ways that blur the distinction between cause and effect. The past influences the present, yes, but the present also helps define what the past was. They're locked together in a mutual dependency that's hard to visualize, but perfectly clear in the equations. Here's another thing. Feynman loved to point out that our psychological sense of time, our feeling that the past is different from the future, is tied to memory. We remember the past, we don't remember the future, and that's not mysterious once you understand entropy. Memory is a physical process. It requires creating records, storing information, and that process increases entropy. Your brain right now is in a higher entropy state than it was yesterday because it's accumulated more memories, more information about the world. That entropy increase gives you the sense that yesterday is past and tomorrow is future. But if you could somehow reverse entropy, if you could make your brain go to a lower entropy state, you'd remember the future instead of the past. Time would seem to flow the other way. The direction of time is tied to the direction of entropy increase. And entropy increase is statistical, not fundamental. What this means is that the arrow of time, the thing that makes the past feel different from the future, it's emergent. It arises from the collective behavior of many particles, not from the laws governing individual particles. And that's why the past still exists, because at the fundamental level, the level where the laws of physics operate, there is no past and future. There's just space-time, and all parts of it are equally valid. The asymmetry we experience, the feeling that time has a direction, that's about us, about how we interact with the world, not about time itself. Feynman had this incredible lecture where he talked about the reversibility of physical laws. He pointed out that if you filmed almost any microscopic process and played it backward, you couldn't tell it was reversed. An atom emitting light looks the same as an atom absorbing light if you reverse time. A particle collision works the same forward and backward. The laws don't distinguish. And he'd ask, so where does the irreversibility come from? Where does the arrow of time come from? And the answer is always the same. From the initial conditions, from the fact that the universe started in a low entropy state at the Big Bang, and has been increasing in entropy ever since. That's it. That's the only thing that breaks the time symmetry. And it's not a law. It's a boundary condition, a fact about how the universe began. Now think about what this implies. If the arrow of time comes from entropy, and entropy is about statistics and probabilities, then the arrow of time is not a feature of space-time itself. Space-time doesn't have an arrow, it's symmetric. All moments are on equal footing. The arrow is something we impose, something that emerges from our perspective as entropy-increasing beings living in a universe that started with low entropy. But the underlying reality, the space-time structure itself, treats past and future identically. They're both real. They're both part of the fabric. Here's something else Feynman understood deeply: the relationship between quantum mechanics and time. In quantum mechanics, particles exist in superposition until measured. They're in multiple states at once. And when you measure them, the superposition collapses and you get one definite outcome. But here's the weird part. That collapse seems to violate time symmetry. The forward evolution of a quantum system is reversible. You can run it backward. But collapse is not reversible. It picks one outcome and discards the others. So what's going on? Is time symmetry broken by quantum measurement? Feynman wrestled with this, and his answer essentially was that collapse is not a fundamental process. It's an effective description of what happens when a quantum system interacts with a macroscopic environment. The environment acts like a measuring device, and the interaction creates correlations that make the system look like it's in one definite state. But fundamentally, the whole system, quantum particle plus environment, is still evolving according to time-symmetric laws. The appearance of collapse, the appearance of irreversibility, it's about our limited perspective, our inability to track all the degrees of freedom in the environment. It's not about time itself. This ties back to the block universe view. If all of time exists, if past and future are both real, then quantum mechanics is describing correlations across time. When we say a particle is in a superposition, we're saying it's correlated with future measurements in a specific way. And when we measure it, we're not changing the past. We're discovering which branch of the wave function corresponds to our location in space-time. The past and present are consistent because they're part of the same structure. The wave function describes the whole structure, all of time, and measurements reveal which part of that structure we're in. Okay, now let me tell you about something really profound that Feynman said. He once remarked that the same electron could be moving backward and forward in time, multiple times, creating what looks like many electrons. This was a half-serious idea he discussed with his advisor John Wheeler. Wheeler suggested that maybe there's only one electron in the universe, and it just zigzags back and forth through time, creating the illusion of many electrons. Every electron you see is the same electron at different points in its journey through space-time. And every positron, every anti-electron, is that same electron moving backward through time. It's a crazy idea, and Feynman knew there were problems with it. The number of electrons and positrons doesn't match, for one thing, but the idea captures something deep. It captures the idea that time is not what we think, that particles can move through time in ways that defy our intuition, and that the past and future are so intertwined that even identity, the question of whether two electrons are the same or different, becomes ambiguous. This is the level of strangeness we're dealing with. And Feynman embraced it. He didn't shy away from the weirdness, he used it. He turned it into a tool for understanding reality. And what he found is that when you take these strange ideas seriously, when you follow them to their logical conclusions, you get theories that work. You get predictions that match experiments. You get a deeper understanding of how the universe actually operates. The past isn't gone. Particles can move backward in time. Space-time is a four-dimensional structure where all moments exist. These aren't philosophical speculations. They're features of our best theories of physics. And those theories are tested every day in laboratories around the world. Let me give you one more example of how the past persists. Quantum entanglement. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But experiments have confirmed it's real. Now, here's the thing. Entanglement creates correlations across space, but it also creates correlations across time. You can have particles that are entangled not just with each other in space, but with their own future and past states. Your measurement now can be correlated with a measurement that happened in the past or will happen in the future. The past state of the particle is not independent of the present state. They're connected, entangled, part of the same quantum system. And that system spans time, not just space. Feynman's path integral formulation makes this explicit. When you calculate the probability of a particle going from point A to point B, you sum over all possible paths, and those paths include loops in time. A particle can go forward, then backward, then forward again. And all of those paths contribute to the final answer. The past is not a separate thing. It's part of the same calculation. It's woven into the quantum description of reality. The particle's history is not a sequence of definite events. It's a superposition of all possible histories, and those histories include ones that visit the past multiple times. Now, I know this sounds like science fiction. It sounds too strange to be true. But here's the thing. These ideas have consequences. They make predictions, and those predictions have been tested. The interference patterns you see in quantum experiments, the precise values of physical constants, the behavior of particles in accelerators, all of it matches what you'd expect if particles really do explore all possible paths through space-time, including backward in time. The math works. The experiments agree. And the simplest way to understand why is to accept that the past still exists, that it's part of the structure particles are exploring. Feynman would tell you not to trust intuition here. Intuition is built from experience, and our experience is limited. We don't experience quantum superposition directly. We don't experience time reversal directly. We don't experience the four-dimensional structure of space-time directly. So of course it feels weird when physics tells us about these things. But that doesn't make them any less real. It just means reality is bigger and stranger than the small corner of it we evolved to navigate. And the way to understand reality is not to force it into our intuitive categories, but to let the evidence guide us, to follow the mathematics, to accept that the universe might work in ways we didn't expect. Here's the beautiful part. Despite all this strangeness, despite the weirdness of particles moving backward in time and the past still existing, and the block universe and all of it, the theory works. It's not just philosophically interesting. It's practically useful. Engineers use quantum mechanics to design transistors and lasers and MRI machines. Physicists use it to understand stars and black holes and the Big Bang. The Global Positioning System, GPS, requires corrections for both special and general relativity to work accurately. If we didn't understand how time dilation works, if we didn't know that time passes at different rates in different places, GPS would be off by miles within hours. This stuff is real, it's been tested, it works, and it tells us the past is not gone. So here's where we are. The universe is a four-dimensional structure called space-time. Every event, every moment, is a point in that structure. The past is not behind us in some metaphorical sense. It's at different coordinates in space-time, just as real as the present, just not accessible to us because we move through time in one direction due to entropy. Our memories are physical records of past events, but the events themselves still exist in space-time. Light from distant stars is literally the past reaching us in the present. Every atom in your body carries information about its past, and the laws of physics describe all of time, past, present, and future as parts of a single unified whole. That's what Richard Feynman understood. That's what physics tells us. And that's the truth about time. What if I told you the Big Bang never happened? Not because some religious zealot wants it that way, but because the very question, what happened before, is like asking what's north of the North Pole. You see, we've been trained to think time is this river flowing one direction. Past, present, future. But what if time itself is the illusion? What if the universe didn't start at all, but we just can't think outside the box our brains built for us? Stick with me, because once you see what I'm about to show you, you'll never look at a clock, a birthday, or even your own mortality the same way again. Now I know what you're thinking. You're thinking, Feynman, you've lost it. I've seen the documentaries. I've read the articles. The Big Bang is settled science. We know the universe is 13.8 billion years old. We have the measurements. We have the cosmic microwave background. We have Edwin Hubble's observations. This is done. This is proven. And you know what? You're both right and catastrophically wrong at the same time. And that's exactly where this gets interesting. Here's what this video is going to do for you that no one else is willing to say out loud. It's going to give you permission to stop pretending you understand something you don't. And more importantly, it's going to show you why not understanding is actually the more intellectually honest position, and ultimately the more liberating one. You've been lied to. Not maliciously, but culturally. You've been told that science has proven the universe began 13.8 billion years ago in a cosmic explosion. You've seen the graphs, the cosmic microwave background radiation maps, the confident pronouncements from scientists in lab coats standing in front of blackboards covered with equations, and somewhere deep inside, you nodded along while a quiet voice whispered, "But what was before that?" And when you asked, maybe to a teacher, maybe to a professor, maybe just to yourself late at night, you got hand-waved away with, "Time didn't exist yet," or, "That question is meaningless." And it felt like a cop-out, didn't it? Because it is a cop-out. Here's the reframe I want you to hold on to. The Big Bang is not a creation event. It's a description of what happens when we run our best equations backward until they break. It's the horizon of our current understanding, not the edge of reality. Confusing the two is like ancient sailors thinking the ocean ended where their maps did. They'd draw their beautiful charts, accurate and detailed for the waters they'd sailed, and then at the edge they'd write, "Here be dragons." Not because there were actually dragons out there, but because that's where their knowledge stopped. That's where the map ended. We've done the exact same thing with the Big Bang. We've found the edge of our map and declared it the edge of the world. What you're going to get from this video is clarity about what we actually know versus what we've mythologized. You'll learn to think like a physicist, to hold uncertainty without collapsing into either dogma or nihilism, and you'll walk away with a completely different relationship to existence itself. Not as a thing that started, but as a thing that simply is, in ways our monkey brains are only beginning to glimpse. This isn't about answers, it's about upgrading your questions, it's about learning to be comfortable in the vast, beautiful, terrifying space of not knowing. So let me take you on a journey, not through space or time, but through the architecture of how we think about space and time. Because that's where the real revolution happens. Not in the data, not in the telescopes, but in the way we frame the questions we're asking. Imagine you're an ant. I want you to really picture this. You're an ant, and you live your entire life on the surface of a balloon that's being inflated. You don't know it's a balloon, of course. To you, this surface is the entire universe. It's all that exists. You can walk north, south, east, west across this surface, and it seems infinite to your tiny ant perspective. But here's the thing that's happening without your knowledge. The balloon is being slowly, steadily inflated. And as it inflates, you notice something absolutely remarkable. You notice that all the other ants, every single one, is moving away from you. No matter which direction you look, everyone's receding. The ants to your north are getting farther away. The ants to your south are getting farther away. Every ant, in every direction, moving away from you at the center. Now, you're a smart ant, a physicist ant. You went to ant university, you studied ant mathematics, and you're good at this. So you start thinking. You think, if everyone's moving away from me and I run this process backward in time, that means we all used to be closer together. In fact, if I extrapolate backward far enough, there must have been a moment when we were all touching. There must have been a beginning, a moment zero, when all the ants were in the same spot. So you start calculating. You measure the speeds at which the other ants are receding. You work backward. And you find it. You calculate that 13.8 billion ant seconds ago, you were all at a single point. The great squish, the primordial touching of all ants. You announce your discovery, you publish papers, you give lectures, you win the Ant Nobel Prize, you're famous, you're celebrated, you've discovered the origin of the universe. But here's what you missed, and this is crucial. You live on a surface. The balloon has no center on the surface itself. If you're an ant confined to the two-dimensional surface of the balloon, there's no special point that's the center from your perspective. Every ant can legitimately claim to be at the center because everyone else is moving away from them equally. The expansion is happening everywhere at once. The beginning, you calculated, that primordial point where all ants were touching. It isn't a place on the balloon. It's when the balloon was deflated down to nothing. But here's the question that should haunt you. Does that mean the balloon itself didn't exist? Or does it just mean the balloon was in a different state? Maybe the balloon was always there, just scrunched up, compressed, waiting to be inflated. Maybe the balloon goes through cycles, inflating, deflating, inflating again, like a cosmic lung breathing in and out. Maybe there are infinite other balloons you can't see, can't detect, because you're trapped on the surface of your own. The point is this, and I need you to really hear this. Your equations describe the surface's expansion perfectly, beautifully, with stunning accuracy. But they can't tell you what the balloon is made of. They can't tell you whether it had a creator who tied it off and started blowing. They can't tell you what's outside the balloon in the larger room. You've described motion brilliantly, but you've mistaken that description for ultimate truth. You've confused the map for the territory. That's us. We're ants on a surface. We're trapped in our 3 spatial dimensions plus time, extrapolating backward to a singularity and calling it the beginning. We're calling it the Big Bang and declaring the case closed. But we might just be at the limit of what our dimensional perspective can see. We might be looking at the edge of our map and mistaking it for the edge of reality. And you know what's beautiful about this? It means the mystery is deeper than we thought. It means reality is more interesting, more strange, more provocative than everything started 13.8 billion years ago and will end in heat death. That story is too small, too tidy, too convenient for creatures who desperately want beginnings and endings because that's how we understand our own lives. But wait, if the Big Bang isn't the beginning, then what is it? What are we even talking about when we say Big Bang? Hold that question. Let me show you something even stranger first. Let me tell you about a student I once had. I had this student, brilliant kid, genuinely one of the sharpest minds I'd encountered in decades of teaching. Sharp like a knife. Sharp like broken glass. The kind of smart that sometimes cuts yourself on. He came to my office one afternoon, and I could see he was absolutely tortured. Hadn't slept. Had that wild look in his eyes that you get when you've been thinking about something so hard that you've forgotten to eat, forgotten to blink, forgotten that other people exist. I knew that look. I'd worn it myself many times. He sat down and he said, "Professor Feynman, I've been thinking about time, specifically about how time could begin, and I'm stuck. I'm completely stuck, and it's driving me insane." I leaned back in my chair and said, "Okay, tell me about it." And he starts talking, fast, like if he slows down he'll lose the thread. He says, if time started at the Big Bang, what does start even mean? To start implies a before state and an after state. Something wasn't happening, and then it was happening. But if there's no time before the Big Bang, the word start becomes meaningless. We're using language that requires time to describe the origin of time. We're trapped in circular logic. It's like trying to use a ruler to measure the first inch of the ruler itself. I looked at him for a long moment, and I said, "You're absolutely right. You've discovered something that most physicists spend their whole careers very carefully avoiding thinking about too hard." He looked relieved for about half a second, and then the relief turned to terror. "So, what do we do? If the language doesn't work, if the concepts don't work, what do we do?" And I told him something I want you to hear too. I said, "We get comfortable with paradox. We accept that our language, the words we use, the grammar we think in, evolved to describe medium-sized objects moving at medium speeds through medium amounts of time, rocks and trees and people and horses. That's what our brains are built for. That's what language is optimized for. When we try to apply that language to the origin of the universe, to the nature of time itself, it breaks. Not because we're stupid, not because we're doing it wrong, but because we're asking our tools to do something they weren't built for. It's like trying to use a ruler to measure justice or a thermometer to measure love. The tool isn't broken. The tool is just the wrong tool for the job. The student sat there quietly, processing. Then he asked the question I'd been waiting for. He said, "But doesn't that mean we can't really know? Doesn't that mean this whole enterprise is kind of futile?" And I said, "Exactly. We can describe, we can measure, we can predict with astonishing accuracy. But knowing in the deep, ultimate, capital K knowing sense, that might not be available to creatures with our cognitive architecture. We might be like dogs trying to understand calculus. Not because dogs are dumb, dogs are great, but because their brains aren't wired for abstract mathematical reasoning. Similarly, our brains might not be wired to comprehend the true nature of time and existence." I leaned forward and I said, "And you know what? I find that deeply comforting. I find it beautiful, because it means the universe is more interesting than our brains. It means reality is under no obligation to make sense to us. It means there's genuine mystery baked into the structure of things, and no amount of clever equation writing will dissolve it completely. That doesn't make science useless. It makes science humble. It makes science honest." He left my office still troubled, but differently troubled. Before, he was troubled by the paradox itself. Now he was troubled by the infinity of what might lie beyond the paradox. That's progress. That's the beginning of real thinking. That's the moment when you stop being a student reciting answers and become a scientist grappling with reality. So if our language breaks down, if our concepts fail us, how do we think about this? What tools do we actually have? Let me show you what the math says, and more importantly, what it doesn't say. All right, story time is over. Let's get into the deep water. I'm going to give you 3 core truths that will completely reframe how you think about existence, time, and what we call the beginning. These aren't easy truths. These aren't comfortable truths, but they're honest truths. And I think you'd rather be uncomfortable and honest than comfortable and deluded. First truth: the Big Bang Theory doesn't explain where the universe came from. It describes what happened after a certain point. This distinction is absolutely crucial, and it's where most people get confused. So let me walk you through this carefully. When Edwin Hubble looked through his telescope in the 1920s, he noticed something shocking. He was measuring the light from distant galaxies, and he noticed that the light was shifted toward the red end of the spectrum. Now, this is important because of something called the Doppler effect. You know how an ambulance siren sounds higher pitched when it's coming towards you and lower pitched when it's moving away? That's the Doppler effect. Waves get compressed when the source moves toward you and stretched when it moves away. Same thing happens with light. Light from objects moving toward us shifts blue. Light from objects moving away shifts red. Every galaxy Hubble looked at, every single one, was redshifted. They were all moving away from us. All of them, in every direction. And here's the kicker. The farther away they were, the faster they were receding. This was observational gold. This was the kind of data that makes physicists wake up in the middle of the night, excited. It meant the universe was expanding. Not that things were flying apart from some central explosion point, but that space itself was stretching, carrying galaxies along with it like raisins in rising bread dough. Now, if things are getting farther apart right now, run the film backward and they must have been closer together in the past. Simple logic. Undeniable logic. Run it back far enough and you get to a state of incredible density and temperature. Everything squished together, compressed, unimaginably hot. This is what we call the Big Bang state. We calculate that about 13.8 billion years ago, everything we can observe in the entire universe was compressed into an unimaginably small, hot, dense point, smaller than an atom, maybe infinitely small. The math suggests a singularity, a point of infinite density. Now notice what I didn't say. Notice very carefully what I didn't say. I didn't say, the universe was created 13.8 billion years ago. I said, the observable universe was compressed into a hot, dense state. Big difference, enormous difference, universe-sized difference. The Big Bang theory describes cosmic expansion. It makes very specific, testable predictions. It says, if this is true, the universe should be cooling down as it expands, just like air cools when you let it out of a compressed tank. Check, it's cooling. The theory says there should be background radiation left over from the early hot state, a kind of afterglow from when the universe was so hot that atoms couldn't even form. Check, we found it in 1965. The cosmic microwave background radiation. It's everywhere. It's perfect. It's exactly what the theory predicted. The theory says the proportions of hydrogen and helium in the universe should match certain very specific calculations based on conditions in the early universe. Check. They match to absurd precision. Every prediction checks out. Every test passes. The theory is spectacularly, breathtakingly successful. It's one of the great triumphs of human reasoning. I'm not here to tear it down. I'm here to clarify what it actually says versus what people think it says. Here's where people get confused, where the slippage happens. Successful description doesn't equal ultimate explanation. The theory tells us the universe was in a hot, dense state and expanded. Full stop. That's what it tells us. It doesn't tell us why it was in that state. It doesn't tell us what before means, or if before is even a coherent concept. It doesn't tell us whether time itself had a beginning, or whether time is something more fundamental. It doesn't tell us whether our universe is all that exists, or whether it's one bubble in an infinite foam of other universes. We've done something psychologically slippery, something very human and very understandable, but ultimately misleading. We've taken a scientific model with precise, limited claims, and we've inflated it into a creation myth. We've turned the universe expanded from a hot, dense state into the universe exploded into existence from nothing. That second version? That's not science. That's storytelling. That's us satisfying our deep psychological need for beginnings and endings, for stories with a chapter 1. Science is humbler than that. Real science says, here's what we can measure. Here's what the math predicts. Here's the boundary where our equations break down, and we honestly don't know what's happening anymore. That last part, the breaking point, that's where the Big Bang actually sits. It's not the beginning of everything. It's the beginning of what we can currently describe with our current tools. Think of it like this. Imagine you're watching a movie and you walk into the theater late. The movie is already playing. You see characters in the middle of an argument. You can describe what you're seeing. You can say, the man is angry, the woman is crying, they're in a kitchen. All true, all accurate, but you don't know why they're arguing. You don't know what happened before you walked in. You don't know if this is the first time they've fought or the 100th. You're describing the middle of a story and calling it the beginning because it's where your observation began. That's us with the Big Bang. We're watching the universe expand, and we're running the footage backward until the film gets too damaged to read. And we're calling that first unreadable frame the beginning, because it's where our ability to see clearly stops. But the movie might have been playing long before we walked in. So if the Big Bang is just where our math breaks, what happens when we try to push past it? What's on the other side of that wall? And that brings me to the second truth, the one that really scrambles people's brains. Second truth. Time is not a river flowing from past to future. It's more like a dimension, similar to space. And once you really understand this, everything changes. Everything. In our everyday experience, time feels absolute. It flows. It marches forward relentlessly. You're born, you age, you die. Eggs break, but don't unbreak. Milk spills, but doesn't unspill. The arrow of time seems undeniable, carved into the bedrock of reality. This is how we experience the world. This is how we think. But Einstein showed us something radically different. He showed us that time is relative. It bends, it stretches, it slows down near massive objects, or when you're moving at high speeds. There's no universal now that everyone agrees on. An event that's in your past might be in someone else's future, depending on your relative motion. If you're standing still and I'm flying by you in a spaceship at near the speed of light, we will literally disagree about what's happening right now on a distant star. Not because one of us is wrong, but because simultaneity itself is relative. Now is not an absolute concept. It's observer-dependent. This is weird. This is deeply, fundamentally weird. But it's not speculation. It's measured. It's tested. We have atomic clocks on airplanes and satellites that run at different speeds than clocks on the ground, exactly as Einstein predicted. Time is not the rigid framework we thought it was. It's flexible. It's part of the fabric of space-time, woven together with the 3 dimensions of space into a 4-dimensional whole. Now, when we combine this with quantum mechanics, things get truly bizarre. At the quantum level, particles don't have definite pasts until we measure them. There's this famous experiment, Wheeler's delayed choice experiment, that suggests the past can be influenced by measurements we make in the present. You can set up a situation where you decide how to measure a photon after it's already passed through a certain point, and your choice affects what the photon did back then. It's as if the past isn't fixed until you look at it. Causality itself becomes fuzzy, uncertain, negotiable. I know this sounds like science fiction. I know it sounds like I'm making this up. But this is the world quantum mechanics reveals to us. This is what the experiments actually show, again and again and again. Now apply this understanding to the Big Bang question. We ask, what happened before the Big Bang? But that question assumes something very specific about the nature of time. It assumes time is a container that existed independently, sitting there empty, waiting to be filled with events. It assumes time is the stage, and the universe is the play happening on that stage. But what if that's wrong? What if time itself is a property of the universe, not something the universe exists inside of? What if time is as much a part of the physical system as matter and energy? If time is a dimension woven into space-time, and space-time itself emerged from or expanded from the Big Bang state, then asking what came before is like asking, what's north of the North Pole? Think about that for a second. What's north of the North Pole? The question sounds reasonable. It has grammatical structure. It uses familiar words, but it contains a category error. Once you're at the North Pole, the concept of north loses meaning. Every direction is south. There is no more north to go. The question dissolves when you understand the geometry of the Earth properly. Similarly, if time is a feature of the universe that emerged with or from the Big Bang, there might be no before. Not because something prevented events from happening before, but because before requires time, and time might not exist independently of the physical universe. The question might contain a category error. It might be asking for something that's incoherent once you understand the actual structure of reality. But, and this is crucial, we don't know that time began. We don't know that for certain. We just know our current equations stop working at a certain point. They give us infinities. They give us nonsense. They break down. Maybe time really did begin with the Big Bang. Maybe it didn't. Maybe time is cyclical, looping back on itself. Maybe time is an emergent property of something deeper, some more fundamental substrate we haven't discovered yet. Maybe there are regions of a larger reality where time flows differently or doesn't exist at all. The honest answer, the only honest answer, is we don't know. But here's what's beautiful about this. Recognizing the limits of our concepts, recognizing that time might be a provincial, local phenomenon specific to our patch of reality, opens the door to possibilities way weirder and more wonderful than the universe started 13.8 billion years ago, and that's that. It means the mystery is deeper than we thought. It means we're still at the beginning of understanding, not the end. And that's exciting. That's the opposite of disappointing. That means there's still work to do, still questions to ask, still reality to grapple with. And if time itself is negotiable, if our basic framework is potentially flawed, what does that mean for the idea of a beginning at all? What does creation even mean if time doesn't flow the way we think it does? Let me show you where modern physics is actually heading with this. Let me show you the cutting edge, third truth. And this is the one that breaks people's brains. This is the one that makes people angry, uncomfortable, disoriented. Maybe there was no beginning. Maybe infinity is not a bug in our thinking. Maybe it's a feature of reality. Humans hate infinity. We are deeply, viscerally uncomfortable with it. It makes us want to run away. We want edges. We want boundaries. We want starts and stops. We want to point to a moment and say, there, that's when it began. It gives us psychological closure. It lets us sleep at night. Even physicists, people who should know better, people who work with infinity in their equations every single day, rush to insert a creation event into cosmology, because the alternative is too vertiginous, too dizzying, too much. But look at what modern physics is actually telling us when we're brave enough to listen. Look at where the math is pointing. Some versions of quantum cosmology suggest the universe could be in an eternal quantum state, with no definite beginning. In these models, what we call the Big Bang is just one fluctuation, one particular expression, in an infinite field of quantum possibilities. The universe doesn't start, it's always in a superposition of states, and the Big Bang is the crystallization of one particular outcome. But the underlying quantum field? That might be eternal. No beginning, no end, just an infinite space of possibilities, constantly collapsing and recollapsing into concrete realities. Then there are the cyclic models. These propose the universe goes through infinite cycles of expansion and contraction. Big Bang, expansion. The expansion slows, reverses, everything collapses back into a big crunch, which then triggers another Big Bang. Over and over, infinite cycles, no beginning to the chain, no end. Just eternal breathing in and out, expansion and contraction, like a cosmic lung that's been breathing forever and will breathe forever. There's eternal inflation theory. This suggests our Big Bang was just one bubble in an eternally inflating multiverse. Picture a pot of boiling water. Bubbles form, expand, pop. New bubbles form. The process never stops. Each bubble is a universe with its own Big Bang, its own laws of physics potentially, its own timeline. And the underlying field that's producing these bubbles? That's eternal. It's always been inflating, always will be inflating. Universes are being born constantly. The process never started and never ends. Our Big Bang was just one bubble forming in an infinite sea of bubble universes. And then, even stranger, some interpretations of quantum mechanics suggest removing time altogether from the fundamental equations. In these frameworks, time is an illusion, an emergent property of our macroscopic experience. At the deepest level of reality, everything just is. Timelessly, eternally existing. The whole history of the universe, past, present, and future, exists all at once in a timeless quantum state. Time is something that emerges when you look at the system from the inside, from the perspective of a conscious observer embedded in the system. But fundamentally, no time, no sequence, no before or after, just existence. Now, none of these are proven. I want to be crystal clear about that. These are speculative. These are hypothetical. These are physicists taking the math seriously and asking, what if we follow these equations all the way? What do they imply? They're not fringe nonsense. These are serious proposals published in serious journals by serious physicists. But they're not settled. We don't know which, if any, is correct. But here's the pattern I want you to notice. Here's what's happened again and again throughout the history of science. Every time we think we've found a boundary, a limit, an edge to reality, we later discover it was just a limit of our perspective. The Earth feels flat when you're standing on it, but it's not flat. It's round. The horizon isn't the edge of the world. It's just the edge of what you can see from where you're standing. The solar system isn't the universe. It's one solar system among billions in our galaxy. The Milky Way isn't the only galaxy. It's one galaxy among hundreds of billions in the observable universe. The universe isn't static. It's expanding, dynamic, evolving. Every time. Every single time. We thought we had it figured out, and reality was bigger, stranger, more extravagant than we imagined. So why would the beginning be any different? Why would this be the one time where we actually found the real edge, the real limit? Isn't it more likely that the Big Bang is another horizon, not an edge? Another limit of our current perspective, not the boundary of reality itself? Maybe the universe doesn't owe us an origin story. Maybe existence is more fundamental than causation. Maybe the question, why is there something rather than nothing, is as confused as asking, why is there up rather than down? That second question presumes a symmetry that doesn't exist. Up and down aren't opposites in some cosmic scale. They're directions relative to a gravitational field. Without gravity, without mass, the concepts lose meaning. Similarly, maybe something versus nothing is a false dichotomy. Maybe nothing isn't even a coherent concept. Maybe existence is the ground state. Maybe the default. Maybe asking why there's something rather than nothing is like asking why there's existence rather than non-existence, when non-existence might not even be a possible state of affairs. This isn't defeat. This isn't me throwing up my hands and saying we can never know anything. This is liberation. This is permission to stop torturing yourself trying to imagine what nothingness looks like. Permission to stop trying to conceive of before time. You can accept that some questions might dissolve when we understand them more deeply, that some questions reveal themselves to be based on flawed premises. The terror of infinity becomes the wonder of infinity. The discomfort of not knowing becomes the excitement of genuine mystery. You don't have to have it all figured out. You don't have to pretend certainty. You can sit in the uncertainty and find it beautiful. Okay, I've just thrown a lot at you. Metaphors and paradoxes and speculative physics and ants on balloons and movies and North Poles. Your brain is probably doing somersaults right now. You might feel a little dizzy, a little unmoored. That's normal. That's good, actually. That means you're actually thinking about this, not just passively absorbing it. So let me bring this down to earth. Let me give you 3 practices, 3 ways to actually use this understanding in your life, in your thinking right now. Because philosophy that doesn't change how you live isn't philosophy. It's just word games. First practice, and this is the hardest one for most people. Start noticing when you're pretending to understand something you don't. And practice saying out loud, I don't know, and that's okay. This sounds simple, it sounds trivial, but it's radical. It's revolutionary. We live in a culture that rewards certainty, confidence, having answers, being decisive. Saying I don't know feels like failure. Feels like you're not smart enough, like you haven't done your homework, like you're falling behind all the people who seem to have it figured out. But here's the secret, and I've known this for 70 years of doing physics. The smartest people I've ever known, the real geniuses, the ones who actually moved the field forward, are comfortable with uncertainty. They can hold a question without collapsing into a premature answer. They can say, "This is fascinating, and I don't understand it yet, and I'm going to keep thinking about it." They don't need the psychological comfort of a tidy answer. They're comfortable in the mess. The people who pretend to know everything, they're either lying or deluded, and usually both. The universe is too big, too strange, too complex for any human brain to fully comprehend. Anyone who tells you they have it all figured out is selling you something. So try this. Try it this week. When someone asks you a big question about God, about meaning, about consciousness, about what happens after death, about how the universe started, instead of reaching for a comfortable cliché or a half-believed answer you picked up somewhere, try saying, "I don't know. I've thought about it, and I genuinely don't know. Isn't that interesting?" Watch what happens. Some people will be uncomfortable. They'll push back. They'll say, "But you must have some theory." They need you to play along with the game of certainty. That's fine. Let them be uncomfortable. But other people, the interesting ones, will lean in. They'll say, "Me neither." And suddenly you're having a real conversation instead of a tennis match of certainties. You're actually exploring together instead of defending positions. Not knowing isn't ignorance. Not knowing is the starting point of wisdom. It's the doorway to actual learning. As long as you think you already know, you can't learn anything new. Your cup is full. But empty your cup, admit you don't know, and suddenly there's room for reality to surprise you. Second practice. When you hear a scientific claim, any scientific claim, ask yourself, is this describing what happens or explaining why it happens? This distinction is everything. This is the difference between science and scientism, between understanding and ideology. The Big Bang Theory describes cosmic expansion. It doesn't explain why expansion occurred in the first place. Evolution describes how species change over time through mutation and selection. It doesn't explain why life exists at all or why the universe is capable of producing self-replicating systems. Quantum mechanics describes the behavior of particles with extraordinary precision. It doesn't explain why reality is quantum, why the universe operates according to these particular rules rather than some other rules. This distinction matters enormously. Most arguments between science and religion, between materialism and spirituality, between different worldviews happen because people confuse these levels. Someone says, "Science has shown that the universe began with the Big Bang." But what they mean is, science has described a pattern of cosmic expansion. The listener hears, "Science has explained the ultimate origin of everything, and there's no room for anything else." And then the fight starts. But the fight is based on a confusion. Practice catching this in real time. Listen to a documentary about cosmology. Read an article about neuroscience and consciousness. Notice when "we have observed X" slides imperceptibly into "therefore Y is the ultimate truth about reality." Notice when a map is being sold as the territory. Notice when description is being inflated into metaphysics. This doesn't make science less valuable. It makes it more valuable. Science is astonishingly good at description and prediction. That's its superpower. That's what it's optimized for. We can describe how stars form, how light bends around massive objects, how chemicals react, how genes are expressed. We can predict eclipses centuries in advance, land robots on Mars, cure diseases, build computers. This is extraordinary. This is humanity at its best, but demanding that science also provide ultimate meaning, ultimate purpose, the answer to "why is there something rather than nothing" is like demanding your thermometer tell you who to marry. It's the wrong tool for the job. The thermometer is great at measuring temperature. Don't get mad at it for not solving your relationship problems. When you can distinguish these levels clearly, you stop expecting physics to answer philosophical questions, and you stop dismissing philosophy as just speculation that's inferior to science. You can hold both. You can be rigorously scientific about what science can address, and rigorously philosophical about what it can't. You can be scientific and humble about the limits of science at the same time. Third practice, and this one might sound weird, but trust me on this. Spend 5 minutes this week sitting with the feeling of infinity. Just the raw feeling. Not thinking about it. Not analyzing it. Just feeling it. Here's how you do it. Find a quiet place. Close your eyes. Take a few breaths. Now imagine space extending outward from where you're sitting. Outward past the walls of your room. Past your house. Past your city. Keep going. Past the Earth. Past the solar system. Past the galaxy. Past the cluster of galaxies. Farther, farther. Imagine it never stopping, never ending. No wall, no edge, just more space. Forever. Notice what happens in your body when you do this. Does your stomach drop a little? Does your breath catch? Do you feel a little dizzy, a little vertiginous, maybe a little awe, maybe a little terror, maybe both at the same time? Good. That's the feeling I want you to notice. Sit with it. Don't try to resolve it. Don't reach for a comforting thought like, but God contains it all, or, but it probably does end somewhere we just can't see. Just sit with the raw experience of endlessness. Let yourself feel small. Let yourself feel the scale. Then do the same thing with time. Imagine the past extending backward. Before you were born. Before your parents were born. Before humanity existed. Before the Earth formed. Before the solar system. Before the galaxy. Keep going backward. Before the Big Bang. Keep going. Imagine it never starting. No first moment. Just infinite past extending backward forever. Notice the discomfort. The way your mind wants to flinch away. Stay with it. Breathe. Feel it. This isn't about reaching a conclusion. This isn't an intellectual exercise. It's about training your nervous system to tolerate uncertainty and vastness without shutting down. Most of us never do this. We think about infinity for 3 seconds, feel uncomfortable, and immediately grab our phone to distract ourselves with something manageable, something finite, something we can control. But if you can sit with it, if you can really sit with the feeling of infinity for even just 5 minutes, something shifts. The terror becomes curiosity. The vertigo becomes awe. You start to understand viscerally, not just intellectually, that the universe is under no obligation to make sense to you. That reality is bigger than your ability to conceptualize it. And paradoxically, instead of making you feel disconnected or small in a bad way, it makes you feel more connected, more part of it, because you're not fighting it anymore. You're not demanding it fit into your categories. You're letting it be what it is. 5 minutes. This week. Try it. See what happens. I think you'll be surprised. All right, let's bring this home. Let's land this plane. We started with a question that's been haunting humanity since we first looked up at the stars and wondered, where did all this come from? How did it begin? Why is there something rather than nothing? These are the deepest questions we can ask, the most profound, the most important. And I told you something uncomfortable. I told you we don't know. The Big Bang isn't the answer you thought it was. It's not a creation event where the universe exploded into existence from nothing. It's a description of cosmic expansion. It's the horizon of our current understanding, not the edge of reality itself. It's where our equations break down, and we have to be honest and say, beyond this point, we're guessing. But here's what you've gained. Here's what's different now from when we started. You've learned to think like a physicist. Not like a physicist in the sense of memorizing equations. Anybody can memorize equations. But thinking like a physicist in the deeper sense. You've learned to distinguish what we know from what we've mythologized. To separate description from explanation. To get comfortable with uncertainty without collapsing into either dogmatic certainty on one side or nihilistic despair on the other. You've seen that time might not be what you think it is, that it's not this rigid container everything happens inside of, but a flexible dimension woven into the fabric of space-time itself. And if time itself is negotiable, if time might be emergent or cyclical or even illusory at the deepest level, then the whole question of the beginning transforms. It might not even be the right question to ask. You've seen that infinity might be more real than beginnings, that the universe might be eternal in ways we're only starting to glimpse, that what we call the Big Bang might just be one event in an infinite process, one bubble in an eternal foam, one cycle in an infinite series of expansions and contractions. And most importantly, you've learned that the smartest thing you can do is admit when you don't know. That intellectual humility isn't weakness, it's strength, it's honesty. It's the only rational response to a universe this vast, this strange, this beautiful. This isn't just about cosmology. This is about how you hold reality. Do you need tidy answers to sleep at night? Or can you dance with mystery? Can you be intellectually honest and emotionally okay at the same time? Can you sit with the big questions without immediately reaching for comfortable lies? Here's what I want you to remember. Here's what I want you to come back to when the vertigo hits, when the uncertainty feels overwhelming, when you're lying awake at 3 a.m. trying to imagine what before time could possibly mean. Here's your mantra. You are not broken for not understanding infinity. You're human, and your confusion is not a flaw. It's not a sign that you're not smart enough or haven't thought hard enough. It's your brain brushing up against something bigger than itself. That's not failure. That's contact with the real. That's your mind touching the edge of what minds can do. And that's beautiful. That's precious. That's the most honest thing you can experience. The universe didn't start with the Big Bang. Or maybe it did. Or maybe the question itself is confused. We don't know. But your willingness to think clearly, to be honest about what we know and what we don't, to hold uncertainty with grace, that can start right now. That's available to you immediately. You don't need a PhD in physics. You don't need to understand the equations. You just need to be willing to say, I don't know, and I'm okay with that. If this resonated with you, if you felt something shift even a little, if some knot of confusion loosened just slightly, do me a favor, hit the like button. Not for the algorithm, though that helps too, but because it tells me I'm not alone in thinking we need more honest conversations about what we don't know. It tells me there are other people out there who are tired of fake certainty and hungry for real thinking. Drop a comment and tell me, what's the question you're most comfortable not having an answer to? What's the mystery you've made peace with? I read every single comment, and I learn from you. Some of the best insights I've had have come from conversations in the comments. You're not just an audience, you're part of this exploration. And if you want more of this, more thinking that doesn't insult your intelligence or pretend certainty where there isn't any, subscribe. Stick around. Let's keep asking the hard questions together. Let's keep pushing against the boundaries of what we can know. Let's keep finding the beauty in not knowing. Because the universe didn't start with the Big Bang. The universe is weirder, more mysterious, more wonderful than that. And the adventure of trying to understand it, of bumping up against the limits of what human minds can comprehend, that's what makes life worth living. Thanks for watching. Now go sit with infinity. Let it wash over you. Feel how small you are and how connected you are at the same time. I'll be here when you get back. Right now, as you watch this, you're sitting in an ocean. An electromagnetic ocean. It's crashing through your body at the speed of light, carrying energy from every wire in your walls, every device on your desk, every star in the night sky. You can't see it. You can't feel it. But it's more real than the chair you're sitting on. And here's the disturbing part. We teach children that electricity is a thing that travels inside wires, when the actual physics, the real story, is so much stranger and more beautiful that it would change how they see invisible forces forever. Let me show you what's actually there. You've been lied to about electricity. Not maliciously, I want to be clear about that. Nobody sat in a dark room plotting to deceive you. But pedagogically? Absolutely. We teach it wrong because the truth is inconvenient for building circuits in sophomore year. So you learned that electricity is electrons flowing through wires like water through pipes, that voltage pushes and resistance slows down this flow, and that energy travels inside the conductor from source to load. You memorized Ohm's law, you passed the test, you moved on. Every single part of that story is misleading. Here's what you actually need to know, and I mean really need to know if you want to understand how reality delivers energy. Energy moves through fields, not matter. When you turn on a light, the energy that powers the bulb isn't traveling through the copper wire. It's propagating through the electromagnetic field that exists in the space around the wire. The Poynting vector, which describes energy flow in electromagnetism, points perpendicular to the wire, not along it. The electrons themselves, they barely move at all. They drift at millimeters per second, jiggling in place while the field configuration changes at light speed. Now I know what you're thinking. You're thinking, Feynman, that can't be right. I've seen electricity work. I flip the switch, the light comes on. Obviously something is traveling through that wire. And you're not wrong to think that. Your intuition is telling you that cause and effect require some kind of physical transfer, something moving from here to there. That intuition has served humanity well for thousands of years. When you push a rock, the rock moves. When you throw a ball, the ball flies. Physical contact, mechanical transfer, objects acting on objects. But here's the thing about intuition. It's built from experience at human scales, human speeds, with objects you can touch and see. And electricity doesn't care about your intuition. It operates according to rules that are profoundly, beautifully non-intuitive. And once you see those rules, once you really see them, you can't go back. The world becomes stranger and more wonderful. So this video is going to give you 3 things. First, perceptual liberation. You're going to stop seeing electricity as a plumbing problem and start seeing it as it actually is. A disturbance in an invisible ocean that fills all of space, including your body, right now, at this very moment. Second, intellectual honesty. I'm going to show you where the standard story breaks down, why it persists despite being wrong, and what happens when you ask the questions your textbooks hoped you wouldn't ask. And third, a new vocabulary for energy. By the end, you'll understand why physics had to invent fields, why action at a distance terrified Newton and gave him nightmares, and why the universe operates more like a drumhead being struck than like a machine with gears and pulleys. The myth you've been sold is that electricity is simple. It's not. But the truth? The truth is so much more gorgeous, so much more strange, that once you see it, you'll never flip a light switch the same way again. This isn't about making you smarter in some abstract way. This is about making you see what's been invisible your whole life. Let me take you back to 1844. Samuel Morse sends the first telegraph message from Washington to Baltimore. About 40 miles of copper wire strung between wooden poles, and he's sitting there with his hand on the telegraph key. He taps out a message in code, "What hath God wrought?" And in Baltimore, 40 miles away, the receiving operator watches his device, and the message appears almost instantly. The clicks come through. The dots and dashes resolve into words. Communication across distance, seemingly instantaneous. Now here's the problem, and this is where the whole story of electricity as we teach it starts to fall apart. Nobody in 1844 understood why this worked. If you believe the electron flow story we teach kids today, you'd expect a massive delay. Let me explain why. Electrons move slowly. I mean really, really slowly. We're talking about a drift velocity of about 1 millimeter per second in copper. That's slower than a snail. That's slower than honey pouring out of a jar on a cold day. At that rate, it should take weeks for electrons to physically travel from Washington to Baltimore. Weeks, but the message arrived in less than a second. So what actually happened? The answer is simultaneously simple and metaphysically disturbing. And I want you to really sit with this. Nothing physical traveled the length of the wire at all. Not one single electron made the journey from Washington to Baltimore. What traveled was a disturbance in the electromagnetic field surrounding the wire, a wave in the invisible ocean. The electrons in Baltimore didn't wait for electrons from Washington to arrive and give them the news. They responded to a change in the field configuration that propagated at nearly the speed of light through the space around the conductor. Think about this for a moment. Really think about it. The energy, the information, the cause of the effect in Baltimore, it never touched the inside of the wire. It surfed the electromagnetic field in the air, in the empty space around the conductor. The wire was just there, like a guardrail on a highway, defining the path but not carrying the cargo. And here's where it gets stranger, because if energy doesn't travel in the wire, then where is it traveling? And what is a wire actually for? These questions should bother you. They bothered me for years. They still bother me in the best way because they point to something deep about how the universe actually works. Everyone loves the water-through-pipes metaphor for electricity. I mean everyone. Students love it because it makes sense immediately. Teachers love it because it's easy to draw on a blackboard. Voltage is pressure, current is flow rate, resistance is the diameter of the pipe. It's clean. It's intuitive. It gets you through your first circuits class with a passing grade and a feeling that you understand something about the world. But then one day, if you're lucky, someone asks you a simple question. Maybe it's a curious kid. Maybe it's a student who actually thinks instead of just memorizing. They say, if electricity is like water and the wire is like a pipe, then what happens to the energy when it reaches the light bulb? Does the water get used up? And you say, confident in your metaphor, no, the electrons aren't consumed. They just transfer their energy and loop back around to the battery. Okay, they say, but where in the pipe does that energy transfer happen? And now you're stuck, because in the water metaphor, energy would transfer inside the pipe, where the water physically touches the turbine. The mechanical contact is everything, the collision, the push. But in reality, the energy in an electrical circuit is flowing outside the wires entirely, in the surrounding electromagnetic field, and it gets absorbed by the resistive load through field interactions that have nothing to do with mechanical contact, nothing to do with electrons bumping into atoms like billiard balls. The metaphor didn't just simplify reality, it lied about the geometry of what's happening. Here's a better metaphor, and I want you to hold on to this one because it's going to help you see what's actually real. Imagine the wire as a railroad track. You've got two metal rails running parallel to each other. Now imagine the electromagnetic field as a train that runs alongside the tracks, never touching them. The train is floating just above and beside the rails, moving forward. The tracks guide the train's path. They define where the energy can flow. They set the boundary conditions, if you want to get technical about it. But the train, the actual energy, the thing doing the work, is riding through the air next to the rails. When you flip the switch on a circuit, you're not sending something down the track like a coal car being pushed from behind. You're changing the field configuration so that energy can suddenly propagate along a new path through space. The field rearranges itself almost instantaneously, and energy starts flowing through the region around the conductors. Now you might be thinking, okay, Feynman, if this is true, why don't we teach it this way? Why did I spend years believing the wrong thing? And that's a great question. That's exactly the right question to ask. And the answer reveals something uncomfortable about how we choose convenience over truth in education. We teach the wrong story because the field picture is mathematically harder and conceptually weirder, and for 90% of electrical engineering, you don't actually need it. Ohm's law works beautifully for designing circuits. Kirchhoff's laws work. You can build computers, wire houses, design power grids, all while believing the electrons flow through wires story. It's a useful fiction. It gets the job done. But here's the cost. And this is what breaks my heart as a teacher. You never learn to see the invisible. You never develop intuition for how energy actually moves through space. And when you encounter edge cases, transmission lines, waveguides, antennas, anything involving electromagnetic radiation, anything quantum, you're stuck. Your mental model is fundamentally wrong, and now you have to unlearn everything before you can move forward. Worse than that, though, and this is the part that really matters, you internalize the idea that reality is mechanical, that cause and effect are local, that the universe is made of things pushing other things, gears turning gears, water flowing through pipes. You develop a clockwork view of existence, and that's just not true. Reality is fields all the way down. It's relational, non-local, deeply strange. There are no gears in nature. There's no plumbing. There's just fields interacting with fields, waves interfering with waves, and somehow out of all that abstraction, you get light switches and toasters and beating hearts. Let me tell you about the hardest truth in physics, the one that took humanity centuries to accept. The electromagnetic field is not a mathematical convenience. It's not a trick we invented to make the equations work out. It's a physical thing. It has energy. It has momentum. It can carry waves. You are, right now, at this very moment, sitting inside a quantum field that extends through all of space, and every charged particle in the universe is creating disturbances in it. When you were taught about forces in school, gravity, electromagnetism, you were probably told that objects exert force on each other. The Earth pulls on the Moon. A proton attracts an electron. Two magnets push or pull depending on their orientation. This is called action at a distance, and it horrified physicists for centuries. I mean, it genuinely disturbed them. It seemed like magic, like voodoo. How does the Earth know the Moon is there? How does a charge reach across empty space to push another charge? What's the mechanism? Newton himself hated this about his own theory of gravity. He wrote about it, expressed his frustration that he couldn't explain how gravity worked, only that it did. The math was perfect. The predictions were flawless. But the mechanism was invisible, spooky, impossible to visualize. Objects were affecting each other across vast stretches of nothing, with no physical contact, no medium, no explanation. The resolution, when it finally came, was fields. The Earth doesn't pull on the Moon directly. The Earth creates a gravitational field that permeates space, extending outward in all directions, getting weaker with distance, but never quite reaching zero. And the Moon responds to the field at its location. The field is the intermediary. It's real. It's there, even when you can't see it or touch it. Same with electricity. When you connect a battery to a circuit, the battery doesn't send electrons on a journey through the wires like little workers carrying energy in buckets. The battery creates an electric field in the surrounding space. That field propagates outward at the speed of light, or rather at a significant fraction of the speed of light depending on the medium. When the field configuration reaches the light bulb, the charges at the bulb respond to the field at their location. They start moving. They start oscillating. And in doing so, they absorb energy from the field. The energy flows through the field, not through the wire. And I need you to really absorb this, because it changes everything. If you cut a wire while current is flowing, the light doesn't stay on for a fraction of a second while the electricity inside the wire finishes traveling to the bulb. The light goes out instantly. Why? Because the field configuration collapses. The pathway for energy flow disappears. Energy isn't a thing that travels in the sense of a physical object moving from point A to point B. It's a property of how the field is arranged in space. There's this beautiful, terrifying equation in electromagnetism called the Poynting vector. It's written as S equals 1 over mu naught times E cross B. Don't worry about memorizing that. Don't worry about the Greek letters or the symbols. What it tells you is this: the direction and magnitude of energy flow is perpendicular to both the electric field and the magnetic field. Let me make that concrete with an example. Take a simple circuit: a battery, a wire, and a resistor. Maybe a light bulb if you want something that glows. The electric field points along the wire, from the positive terminal of the battery toward the negative terminal. That's the voltage gradient, the pressure in the water metaphor. The magnetic field circles around the wire, created by the current flowing through it. If you've ever held a compass near a wire carrying current, you've seen this. The compass needle deflects because it's responding to the magnetic field surrounding the conductor. Now cross those two directions. Electric field along the wire, magnetic field circling the wire. The cross product of those two vectors, the direction you get when you combine them using the right-hand rule, points radially inward, from the space around the wire into the resistor. The energy flows through the air, not the copper. Let me say that again because it's so important and so completely opposite to what you were taught. When you power a toaster, the energy is not flowing through the cord. It's flowing through the space around the cord, guided by the electromagnetic field configuration, and it gets absorbed by the heating element through field interactions at the surface. Why does this matter emotionally? Why am I spending so much time on this one point? Because it means the invisible is primary. The stuff you can't see, fields, forces, the quantum foam of space itself, is doing all the work. The solid things, the wires and resistors and batteries, the objects you can hold in your hand and measure and take apart, they're just landmarks in a much larger, much stranger landscape. They're the tracks guiding the train, but they're not the train. Here's where people get stuck, and I want to address this head-on because it's the most common objection I hear. But Feynman, if energy flows through fields, why do we need electrons at all? What are they doing? Electrons are necessary, absolutely. But not in the way you think. They're not carrying the energy like little trucks hauling cargo from the power plant to your house. They're responding to the field and creating new fields in response. They're part of a feedback loop. They're participants in a vast, dynamic dance of charges and fields interacting across space. Think of it this way. Imagine a long line of people holding hands in a dark room. You're at one end. You push the first person's hand forward. Instantly. Well, as fast as the mechanical wave can propagate through linked arms, the person at the far end of the line feels a push and steps forward. Did your hand travel to the end of the line? Of course not. A wave of coordination traveled through the medium of connected bodies. Information propagated, energy transferred. But no individual person made the journey from your end to theirs. Electrons in a wire are similar. When the electric field changes at one end of the circuit, electrons everywhere in the wire respond simultaneously, or rather, nearly simultaneously, at the speed that electromagnetic disturbances propagate through that particular medium. The energy propagates as a field disturbance. The electrons just participate. They're the medium, not the message. Let me give you some numbers because numbers make this concrete in a way that metaphors can't. Drift velocity, the actual speed at which electrons move through a conductor, is about 1 millimeter per second in typical household wiring. 1 millimeter per second. That's about the speed of a very lazy snail. Meanwhile, the signal velocity, the speed at which energy and information propagate, is around 200,000 kilometers per second. That's about 2/3 the speed of light in vacuum. The difference between those two speeds is literally 100 billion. 100 billion. If you think electricity is about electron motion, you're off by 11 orders of magnitude. You're not even in the same ballpark. You're not in the same sport. You're playing a completely different game. So why do textbooks teach the wrong story? Why do we perpetuate this myth of electrons flowing through wires like water through pipes? I've thought about this a lot over the years, and I think the answer is both practical and tragic. Practically speaking, the field picture is mathematically harder and conceptually weirder. To really understand fields, you need vector calculus. You need to be comfortable with partial differential equations. You need to visualize things that have no macroscopic analog in everyday life. That's a big ask for a high school physics class or even an introductory college course. The water through pipes metaphor gets students through the material quickly. They can solve problems, they can pass tests, they can move on to the next topic. But here's the tragic part. Most of those students never come back. They never learn the deeper truth. They go out into the world as engineers, as electricians, as informed citizens who vote on energy policy, and they carry with them a fundamentally wrong picture of how reality works. And that matters. It matters because when you think electricity is a substance flowing through wires, you can't understand wireless power transmission. You can't understand how antennas work. You can't understand light, which is just an electromagnetic wave propagating through the field with no medium required, no water, no ether, just the field vibrating itself into existence. You end up with a mechanical view of the universe, a clockwork cosmos, where everything is local, everything is touch-based, everything is intuitive. And you miss the strangeness, you miss the beauty, you miss the fact that we live in a reality so much weirder than we were told. But you're here now. You asked the deeper question. You wanted to know what's actually real, not just what's useful. And that curiosity, that willingness to have your intuition broken and rebuilt, that's what makes you a physicist in the truest sense, whether or not you ever solve another equation in your life. Once you understand that energy flows through fields, not matter, a whole bunch of things suddenly click into place. Things that seemed like different phenomena, isolated tricks of technology, reveal themselves to be expressions of the same underlying reality. Wireless charging, for example. You put your phone on a pad and it charges without any physical connection. To most people this seems like magic, like science fiction made real. But once you know that energy always flows through fields, wireless charging becomes obvious. It's not doing anything special, it's just making explicit what was always true. The charging pad creates a time-varying magnetic field. That field extends through space, including through the back of your phone. Inside your phone, a coil of wire experiences that changing magnetic field, which induces an electric field, which drives a current. Energy flows from the pad to the phone through the electromagnetic field in the air between them. No mystery, no magic, just fields doing what fields always do. Antennas are the same way. When you transmit a radio signal, you're not sending electrons into the air. That would be absurd. You're creating an oscillating electric field at the antenna, which creates an oscillating magnetic field, which creates an oscillating electric field, and on in a self-sustaining wave that propagates outward through space at the speed of light. The receiving antenna picks up that wave by responding to the oscillating fields at its location. Again, no particles traveling, just field disturbances propagating. And light. Light is the ultimate example. Light is an electromagnetic wave, a self-propagating disturbance in the electromagnetic field, with no medium required. This broke everyone's brain in the 19th century. Scientists were so convinced that waves needed a medium, water waves need water, sound waves need air, that they invented an invisible substance called the luminiferous ether that filled all of space and carried light waves. They designed elaborate experiments to detect the ether, to measure Earth's motion through it. And they found nothing. Because there is no ether, light doesn't need a medium. It is the medium vibrating itself. The field is the substance. The field is what's real. Now, if you're starting to feel like everything you were taught is suspect, good. That means you're paying attention. Let me take this one step further into territory that might make you uncomfortable. Quantum mechanics becomes slightly less weird when you realize particles aren't things. They're not little billiard balls bouncing around. They're excitations in quantum fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. The universe isn't made of objects in the way you think about objects. It's made of fields, and what we call particles are just persistent patterns in those fields, like whirlpools in a river. You start to see that the universe isn't made of stuff. It's made of relationships, field values at different points in space interacting according to rules, creating patterns that persist, that move, that interact with other patterns. And somewhere in all that abstraction, in all that mathematics made physical, you get stars and planets and trees and people. You get you. You're a pattern in a quantum field. Where do you end and the universe begins? That's not a rhetorical question. It's a real question without a clear answer, because the fields that make up your body extend through all of space, overlapping and interfacing with every other field. You're not separate from the universe. You're a particularly organized region of it, a temporary standing wave in the cosmic ocean. Does that make you less real? No. Does it make you less important? No. But it should make you feel connected to everything else in a way that the old mechanical picture never could. Now let me give you something practical to do with all this. Because understanding is one thing, but practice is how you make knowledge your own. For 1 week, every time you interact with electricity, and you interact with it dozens of times a day, probably more, I want you to pause and visualize the invisible. Flip a light switch. Don't imagine electrons flowing through the wire like water through a pipe. Instead, imagine a field disturbance propagating through the space around the wire at nearly light speed. Picture the energy flowing outside the conductor, guided by the wire's geometry but not contained by it. See the invisible ocean responding to your action. Plug in your phone. Visualize the electromagnetic field configuration changing, energy flowing through the air in the charging cable, absorbed by the battery through field interactions at the molecular level. Turn on your car. Feel the starter motor drawing energy that's flowing through space, guided by wires but not trapped in them. This isn't just a mental game. This is training your brain to see what's actually there. Most people go their whole lives thinking electricity is a plumbing problem, a substance being pushed through pipes. You now know better. Practice seeing the invisible ocean you live in. Whenever you encounter an electromagnetic phenomenon, a magnet on your refrigerator, a radio in your car, a microwave oven heating your food, ask yourself one question. What is the field doing here? Not, what are the electrons doing? Not, what's the mechanism in the mechanical sense? But, how is the field configured in space, and where is the energy flowing through it? For example, a magnet. The magnetic field extends through space in loops from the North Pole to the South Pole. Bring a piece of iron near the magnet, and the iron's internal magnetic domains, tiny regions where atoms have aligned their magnetic moments, reorient themselves to align with the external field. That alignment creates attraction. The field is the actor. The field is what's real. The solid objects, the magnet and the iron, are just responding to field configurations. A radio. An antenna creates an oscillating electric field. That oscillating electric field generates an oscillating magnetic field. That oscillating magnetic field generates an oscillating electric field. And on, ad infinitum, a self-sustaining wave that propagates outward through space. No medium required, no particles traveling, just the field creating itself, moment by moment, according to Maxwell's equations. This reframes everything from mechanism to geometry. You stop asking, how does it work, in the sense of gears and pulleys, and you start asking, what shape is the field and where is the energy? You develop geometric intuition for invisible things. Here's another practice, and this one's important. Teach someone else the truth. Find a kid, a friend, a skeptical engineer at a party. Explain to them that energy doesn't flow through wires. Watch their reaction. It'll probably be disbelief at first. That can't be right. I've been taught the opposite my whole life. Answer their questions. Defend the field picture using your own words, your own metaphors. Don't just repeat what I've said. Find your own way of expressing the truth. Teaching is how you discover what you actually understand. If you can't explain it simply, you don't understand it well enough. And when you put this idea into the world, when you share it with someone else, you're fighting back against a century of convenient lies. You're giving someone permission to see reality as strange again, instead of domesticated and mechanical and boring. Show them the pointing vector if you're feeling ambitious. Draw the electric field pointing along the wire. Draw the magnetic field circling around the wire. Show them how the cross product of those two vectors points radially inward, from the space around the wire into the resistor. Make it visual. Make it weird. Make it real. Now here's a practice that's more philosophical, but it matters just as much. Get comfortable with the idea that most of what's real is invisible. Sit with that discomfort. Let it be strange for a while. Fields, forces, quantum wave functions, information, consciousness maybe, though we don't know yet. These aren't metaphors or mathematical abstractions. They're real, and they're often more causally important than the tangible stuff you can hold in your hand. The wires in your wall aren't delivering electricity. They're guiding an invisible field. The neurons in your brain aren't producing thought like a factory produces widgets. They're patterns in a biological field of electrical and chemical signals, and somehow that pattern has the property of being conscious, of experiencing, of being you. You aren't a thing in the way you probably think about things. You're a process, a standing wave in a material substrate. The atoms that make up your body right now will be completely different atoms in 7 years, cycled out through eating and breathing and excreting, but you'll still be you. Why? Because you're not the atoms. You're the pattern. You're the field configuration that persists, even as the underlying substance changes. Sit with that. Let it break your intuition for a bit. Let it make you uncomfortable, because on the other side of that discomfort is a much richer, much stranger understanding of what it means to exist in this universe. You're not a separate thing. You're a particularly organized region of the cosmos, temporarily coherent, aware of itself, capable of looking back at the rest of the universe and trying to understand it. And here's the last practice, and it's simple. Notice when you use the old story and forgive yourself. You're going to slip. You're going to say electricity flows through the wire because it's easier, because everyone knows what you mean, because the truth is cumbersome in casual conversation. That's okay. The goal isn't purity. The goal is awareness. Notice when you use the old metaphor. Smile at it. Know that you know better, even if you're not always in the mode to explain it fully. Language is a tool, and sometimes the slightly wrong tool is good enough to get the job done. But never forget, the map is not the territory. And the territory is so much weirder, so much more beautiful than the map could ever capture. So let's come back to where we started. You thought electricity was electrons flowing through wires, like water through pipes. Simple, mechanical, intuitive. Now you know. Energy flows through fields, not matter. The wires are just guides, defining the boundary conditions for field configurations. The electrons are just participants, responding to fields and creating fields in response. The invisible ocean around you, the electromagnetic field that permeates all of space, is doing all the work. This isn't a small correction to your understanding. This isn't a footnote. This is a perceptual revolution. You now see that the universe operates on principles that are deeply, beautifully non-intuitive. Cause doesn't require contact. Energy doesn't require substance. Action at a distance isn't magic. It's mediated by fields. The most important things, the things doing all the actual work, are invisible. And here's what I want you to take with you. What I want you to remember the next time you flip a light switch or charge your phone or look up at the stars. You're not broken for being confused about this. You weren't stupid. You weren't lazy. You were taught a lie of convenience because the truth was deemed too hard or not practical enough for the masses. But you're here now. You asked the deeper question. You wanted to know what's actually real, not just what's useful for passing a test. That curiosity, that willingness to have your understanding overturned, that desire to see what's truly there, even when it's strange and uncomfortable, that is what makes you a physicist in spirit. That's what makes you someone who looks at the world and doesn't just accept the surface story. You dig deeper. You ask why. You sit with confusion until clarity emerges. The invisible is real. The strange is true. And you are awake to it. Say that to yourself. Let it be a mantra. The invisible is real. The strange is true. And I am awake to it. The next time you flip a light switch, pause for just a second. Feel the click of the mechanism. See the light come on instantaneously. And know, really know, that what just happened is not what you were taught. Energy didn't flow through the wire. A field configuration changed, and energy propagated through the space around the conductors at nearly the speed of light, guided but not contained, invisible but absolutely real. You're not living in a machine. You're living in a field. A vast, interconnected, dynamic ocean of electromagnetic potential that responds to charge, that carries energy, that makes light and electricity and magnetism and ultimately life possible. And now you can see it. Not with your eyes, but with your mind. You can visualize what's actually happening beneath the surface of everyday experience. And that changes things. It changes how you think about connection. You're not separate from the world around you. Your body is constantly exchanging electromagnetic signals with everything nearby. Photons from the sun, radio waves from cell towers, the electric fields from power lines. You're part of the field. You're swimming in it. You always have been. It changes how you think about causation. When someone flips a switch 100 miles away at a power plant, the change in the electromagnetic field propagates outward, and your lamp responds. There's no delay for particles to travel. The field is the medium of cause and effect, faster than any mechanical transfer could ever be. It changes how you think about what's possible. Once you understand that energy moves through fields, wireless power stops seeming like magic. Transmission of information through empty space stops seeming miraculous. It's all just fields doing what fields do, following rules we've discovered and written down in equations, rules that make testable predictions about how reality behaves. And maybe, if you let it, it changes how you think about yourself. Because if you're a pattern in a field, if you're a standing wave in the cosmic ocean, then where you end and everything else begins is not as clear as you thought. You're made of the same fields as everything else. You're subject to the same rules. You're part of the same universe, not separate from it, not a ghost in a machine, but a pattern in the tapestry. Does that mean you're not special? No. It means you're exactly as special as everything else, which is to say, infinitely special, because the fact that the universe has organized itself into patterns complex enough to understand themselves, to look back at the cosmos and ask questions about fields and energy and truth, is the most astonishing thing we know of. You're a localized region of increasing entropy becoming temporarily self-aware. You're matter that has learned to think about matter. You're the universe studying itself. And the tools you use to do that studying, mathematics, physics, the scientific method, they work because the universe is knowable, because it follows rules, because fields interact in predictable ways that we can discover and test and use. That should fill you with wonder. Not in a vague, mystical sense, but in a precise, technical sense. The fact that you can flip a switch and understand, really understand what's happening at the level of fields and charges and energy flow, that's a miracle of human understanding. That's the Enlightenment paying off. That's everything we've learned as a species about how to look at reality and see it clearly. So if this shifted something for you, if you're seeing electricity differently now, if you're seeing reality differently now, do me a favor. Leave a comment. Tell me what clicked. Tell me what you're still confused about. Tell me what question you're sitting with now that you weren't sitting with before. I genuinely love hearing how people think, and your question might be the spark for the next video, the next exploration, the next attempt to take something we teach wrong and teach it right. And if you want more of this, more physics that breaks your brain in the best way, more truth that's stranger than fiction, more attempts to see what's actually real instead of what's convenient, hit subscribe. Not because I need the numbers, not because of any algorithm or metric, but because you deserve to keep seeing the invisible. The universe is generous with its secrets if you're willing to look, if you're willing to have your intuition challenged, if you're willing to sit with strangeness until it becomes familiar. There's so much more to explore. We barely scratched the surface of electromagnetism today. We didn't talk about Maxwell's equations, the 4 fundamental laws that govern all electric and magnetic phenomena. We didn't talk about special relativity, which reveals that electricity and magnetism are actually the same force seen from different reference frames. We didn't talk about quantum electrodynamics, the most precisely tested theory in all of science, which describes how charged particles interact by exchanging virtual photons in the quantum field. But we started something. We broke the surface. We saw beneath the convenient lie to the strange truth. And once you've done that, you can't unsee it. You're part of a smaller group now, people who know that energy flows through fields, not wires, people who see the invisible ocean, people who understand that the universe is weirder and more beautiful than we were taught. Welcome to that group. Welcome to seeing reality a little more clearly. Welcome to the strangeness and the wonder. The invisible is real. The strange is true. And you are awake to it. Now go flip a light switch and really see it. Feel the click. Watch the light appear. And know what's actually happening in that moment. Know that you're part of something vast and interconnected and deeply, profoundly strange. Know that you live in a field, not a machine. Know that the most important things are the things you can't see. And carry that knowledge with you. Let it change how you look at the world. Let it change what you think is possible. Let it remind you that reality is generous with its mysteries, patient with your questions, and always, always stranger than you imagine. Thanks for wondering with me. Thanks for being curious enough to watch this all the way through, to sit with ideas that challenged what you thought you knew, to be willing to see something new. That curiosity is everything. That's the spark. That's what makes humans special. Not that we're smarter than other animals necessarily, but that we're curious enough to ask questions we don't know the answers to, and patient enough to sit with those questions until clarity emerges. Keep asking questions. Keep looking beneath the surface. Keep refusing to accept the convenient story when the true story is available if you're willing to work for it. The universe is waiting. The invisible ocean is all around you. And now you can see it. You think you understand dimensions? You don't. Most people don't. And that's not your fault. Your brain was never designed to think about this properly. But here's the thing. Richard Feynman, one of the greatest physicists who ever lived, figured out how to make dimensions click. Not with fancy math, not with abstract nonsense, with simple, brutal clarity. And once you see it his way, you can never unsee it. So let me show you what he showed us. Let me show you why everything you think you know about dimensions is incomplete, and why the truth is so much stranger and more beautiful than you ever imagined. Let's start with something you think is obvious. A point has 0 dimensions. A line has 1 dimension. A square has 2 dimensions. A cube has 3 dimensions. Simple, right? You learned this in school. You've known it forever. But here's what they didn't tell you. Here's what Feynman understood that most people miss. Dimensions aren't just counting directions. Dimensions are about freedom, about how many independent ways you can move, about the fundamental structure of reality itself. Let me explain what I mean. Imagine you're a prisoner. You're locked in a cell. But this isn't a normal cell. This cell is so small that you can't move at all. You can't go forward, backward, left, right, up, or down. You're frozen in space, completely stuck. How many dimensions of freedom do you have? 0. You're a point. You exist, but you cannot move in any direction. That's 0 dimensions. Not the absence of space, but the absence of freedom to move through space. Now the prison guard loosens your chains slightly. You can move, but only along a wire. You can slide forward or backward along this one wire, but that's it. No left, no right, No up, no down, just forward and backward. How many dimensions of freedom do you have now? 1. You live in a one-dimensional world. Your entire universe is a line. Everything that exists somewhere along this line. And here's the crucial part. From your perspective, inside this one-dimensional world, you cannot even imagine what left or right would mean. Those concepts don't exist for you. The guard loosens your chains again. Now you can move forward and backward, but also left and right. You're on a flat surface. You can slide anywhere on this plane, but you still can't go up or down. 2 dimensions, 2 independent directions of freedom. This is the world of the bug we talked about before, the bug on the surface of the sphere. 2 dimensions of movement, but nothing else. Finally, the guard removes all the chains. You can move forward, backward, left, right, up, and down. 3 dimensions, 3 independent directions. This is the world you live in, the world you know, the world that feels complete. But here's Feynman's question, the question that changes everything. Why should it stop at 3? Think about it carefully. What makes 3 special? What makes 3 the final number? You can move forward and backward. That's 1 dimension. You can move left and right. That's a 2nd dimension, independent of the first. You can move up and down. That's a 3rd dimension, independent of the other 2. But why can't there be a 4th direction? A direction that's somehow perpendicular to all 3 of the ones you know. Not up, not down, not left, not right, not forward, not backward, but something else entirely. Some other direction that you simply can't perceive. Now, your brain immediately rebels against this. Your brain says, that's impossible. I can see all of space. There's nowhere else to go. Up, down, left, right, forward, backward. That's everything. But is it? Feynman would ask you to consider the bug again. The bug on the 2-dimensional surface. That bug would say exactly the same thing. I can see all of space. Forward, backward, left, right. That's everything. There's nowhere else to go. And the bug would be wrong. Dead wrong. Because up and down exist. The bug just can't perceive them. So here's the terrifying possibility. You might be the bug. You might be living in a higher dimensional space, moving through it, existing in it, but completely unable to perceive the extra dimensions. You might be like a prisoner who's only aware of forward and backward, completely oblivious to left and right, even though left and right are right there, real, physical, surrounding you. This isn't science fiction. This is a genuine possibility that physicists take seriously. Now, let me show you why this matters, why Feynman cared about this, why understanding dimensions isn't just an abstract game. It's about understanding the fundamental structure of reality. And it starts with a simple observation. The laws of physics look different in different numbers of dimensions, not just mathematically different, actually fundamentally different. Things that are possible in 3 dimensions are impossible in 2 dimensions. Things that are possible in 4 dimensions are impossible in 3 dimensions. The number of dimensions determines what can happen, what can exist, what laws govern reality. Here's an example Feynman loved. In 3 dimensions, you can tie a knot. You can take a rope, loop it around, thread it through itself, and tie a knot that stays tied. Try to do that in 2 dimensions. Try to tie a knot on a flat surface where the rope can't leave the surface. You can't. It's impossible. The rope always crosses itself and you can slide the loops apart. Knots don't exist in 2 dimensions. The topology is different. The structure of space itself doesn't allow it. Here's another one. In 3 dimensions, you can have stable orbits, planets orbit stars, moons orbit planets. Electrons orbit nuclei, sort of. These orbits are stable because of an inverse square law. Gravity and electric force both follow inverse square laws in 3 dimensions. The force gets weaker as 1 over distance squared. But in 4 dimensions, the force would follow an inverse cube law, 1 over distance cubed. And with an inverse cube law, orbits aren't stable. Planets would spiral into stars or fly away. Atoms wouldn't hold together. Chemistry wouldn't work. Life, as we know it, couldn't exist. This is profound. The number of dimensions doesn't just change the math, it changes everything. It determines what structures can form, what patterns can emerge, what complexity is possible. 3 dimensions isn't arbitrary. It's special. It allows knots and stable orbits and all the intricate structures that make the universe interesting. Fewer dimensions would be too simple. More dimensions would be too chaotic. 3 is, in some sense, just right. But that raises a question. If 3 is special, why do physicists talk about extra dimensions? Why do theories of physics propose 4 spatial dimensions, or 5, or 6, or even 10 or 11? Here's where it gets interesting. Feynman understood something crucial. There's a difference between large dimensions and small dimensions. The 3 dimensions you know, up, down, left, right, forward, backward, these are large, infinite, or at least vast. You can move as far as you want in these directions and keep going. But a dimension doesn't have to be large. A dimension could be small, very small, so small that you'd never notice it. Imagine this. Imagine that space has a 4th dimension, but that 4th dimension is curled up, wrapped around in a tiny circle. So tiny that you can't see it. You exist in this 4th dimension. You're extended into it. But the extension is microscopic. Smaller than an atom. Smaller than anything you could ever measure. From your perspective, the 4th dimension doesn't exist. But mathematically, it's there. And it has consequences. Feynman explained this with one of his famous analogies. Imagine an ant walking on a tightrope. From far away, the tightrope looks one-dimensional. It's just a line. The ant can only move forward or backward along the rope. But zoom in, look closely at the rope. The rope has thickness. It's actually a cylinder. And the ant, if it's small enough, can move around the rope. It can walk forward and backward along the length, and it can also walk around the circumference. 2 dimensions, not 1. But the 2nd dimension is curled up. It's finite. It loops back on itself. And if you're looking from far away, you don't even notice it. Our universe might be like that tightrope. We think we live in 3 dimensions, but there might be extra dimensions, curled up so small that we can't detect them. We move through these dimensions constantly, but the movement is confined to such a tiny scale that it's invisible. And yet these hidden dimensions might be crucial. They might explain things we don't understand. They might be the key to unifying all the forces of nature. Now here's where Feynman's genius really shines. He didn't just talk about dimensions abstractly. He showed how to think about them, how to visualize them, how to make them concrete, and his method is brilliant. Here's what he'd tell you. If you want to understand 4 dimensions, don't try to visualize a 4-dimensional object all at once. You can't. Your brain isn't built for it. Instead, look at slices. Look at 3-dimensional slices of a 4-dimensional object, and watch how those slices change. Let me show you what I mean. Start with something simple. A 0-dimensional object, a point. If you slice a point, you get nothing or you get the point. That's it. Now, a 1-dimensional object, a line segment. If you slice a line segment perpendicular to its length, each slice is a point. And as you move the slicing plane along the line, the point appears, exists, and then disappears. The point is the 1-dimensional object's intersection with the 0-dimensional slicing space. Now, a 2-dimensional object, a circle. Slice a circle with a 1-dimensional line. Depending on where you slice, you might get nothing, you might get a point where the line just touches the edge, or you might get a line segment where the line cuts through. And as you move your slicing line across the circle, the line segment appears, grows, reaches maximum length at the center, shrinks, and disappears. You can reconstruct the whole circle just by watching how the slices change. Are you starting to see the pattern? Good. Because now comes the leap. A three-dimensional object, a sphere. Slice a sphere with a two-dimensional plane. Each slice is a circle, and as you move the slicing plane through the sphere, the circle appears, grows, reaches maximum size at the equator, shrinks, and disappears. You can reconstruct the entire three-dimensional sphere just by watching the sequence of two-dimensional circles. This is how we understand CT scans and MRI scans. We're looking at two-dimensional slices of a three-dimensional body. Now, the jump to 4 dimensions. A 4-dimensional sphere, called a hypersphere. If you slice a hypersphere with a 3-dimensional space, each slice is a 3-dimensional sphere. And as you move your slicing space through the hypersphere, the 3-dimensional sphere appears, grows, reaches maximum size, shrinks, and disappears. You can't visualize the whole hypersphere at once, but you can visualize the sequence of 3-dimensional spheres. And that sequence is the hypersphere. That's what it means to exist in 4 dimensions. Feynman would push this further. He'd ask, what does a 4-dimensional cube look like? You can't see it all at once, but you can see its 3-dimensional slices. Start by slicing a 4-dimensional cube, called a tesseract or hypercube. At first you get nothing. Then, suddenly, a 3-dimensional cube appears. It grows. At the middle of the tesseract, you get a cube. Then the cube starts shrinking, and finally it disappears. The tesseract is the collection of all these cubes stacked in the 4th dimension. But here's where it gets wild. Feynman realized that you can actually see hints of 4-dimensional geometry in 3-dimensional shadows. Just like a 3-dimensional object casts a 2-dimensional shadow, a 4-dimensional object would cast a 3-dimensional shadow. And mathematicians have computed what these shadows look like. The shadow of a tesseract is a cube within a cube, with the corners connected. It looks impossible, because you're trying to represent 4-dimensional structure in 3 dimensions, and things overlap and intersect in ways that seem wrong. But that's exactly the point. The wrongness is the signature of the extra dimension. Now let's talk about something Feynman was obsessed with, the way dimensions affect physics. I mentioned earlier that the laws change in different dimensions. Let me be more specific. In 1 dimension, things are simple. Very simple. Particles can only move in a line. They can't go around each other. If 2 particles meet, they bounce back. That's it. No complexity, no interesting dynamics. In 2 dimensions, things get more interesting. Particles can move around each other. You can have rotation, circulation, vortices. But you still can't have knots. You can't have certain kinds of field lines. The electromagnetic field behaves differently. Gauss's law works differently. Gravity follows a different force law. In 2 dimensions, gravity doesn't follow inverse square. It follows inverse first power. Force decreases linearly with distance, not quadratically. In 3 dimensions, we get inverse square laws. Both gravity and electromagnetism follow inverse square laws. Why? Because of geometry. Because in 3 dimensions, the surface area of a sphere grows as the square of its radius. The field spreads out over that surface, so the field strength decreases as 1 over the square of the distance. This is geometric. This is forced by the structure of 3-dimensional space itself. In 4 spatial dimensions, you'd have inverse cube laws. The surface of a 4-dimensional sphere grows as the cube of its radius. Forces would weaken faster with distance. And as I said, orbits wouldn't be stable. Atoms wouldn't work. Stars wouldn't work. Nothing would work the way it does in our universe. Feynman found this fascinating. The fact that physics is so intimately tied to geometry. That the number of dimensions determines the laws. That you can't separate the physics from the dimensionality of space. And this leads to one of his deepest insights. When you're doing physics, you're not just calculating forces and trajectories. You're exploring the geometry of reality. You're figuring out the shape of the space you live in. Here's something Feynman loved to point out. We don't actually know that space has exactly 3 dimensions. We observe 3 large dimensions, sure, but there could be more. Small dimensions, curled up, hidden. How would we detect them? Well, if there are extra dimensions, even tiny ones, particles can move in them. And that movement would show up as extra energy. Energy we can't explain with just 3 dimensions. Think about it this way. If there's a small extra dimension, a dimension curled up into a circle, a particle can move around that circle. And because the dimension is small, the particle's wavelength has to fit into that small space. Quantum mechanics tells us that a confined particle has energy. The smaller the confinement, the higher the energy. So particles moving in extra dimensions would have extra energy states. And we could detect those states in particle colliders. We could smash particles together at high energies and look for signs of extra dimensions. This is not speculation. This is real physics. Experiments at the Large Hadron Collider have looked for evidence of extra dimensions. So far, they haven't found any. But the search continues, because if extra dimensions exist, they would revolutionize our understanding of the universe. They would explain mysteries we can't currently solve. For example, gravity. Gravity is weirdly weak compared to the other forces. Electromagnetism is vastly stronger than gravity. Why? One possibility is that gravity leaks into extra dimensions. While electromagnetism is confined to our 3 dimensions, gravity spreads out into extra dimensions, diluting its strength. If this is true, then on very small scales, in the extra dimensions, gravity might be much stronger than we think, and we could detect this with precise enough experiments. Another example is the hierarchy problem. The fundamental particles have masses that span an enormous range. The Higgs boson is much heavier than an electron. Why? The math suggests the Higgs should be much, much heavier than it is unless something cancels out the extra mass. Extra dimensions could provide that cancellation. They could explain why particles have the masses they do. Now, watch this. Feynman understood that dimensions aren't just a mathematical curiosity. Dimensions have real physical consequences. And one of the most profound consequences is this. The dimensionality of space determines what information you can store, how much complexity you can pack into a region, how much structure can exist. Think about it. In 0 dimensions, in a point, you can store essentially 1 bit of information. The point exists or it doesn't. In 1 dimension, along a line, you can store a sequence of bits. The amount of information grows linearly with the length of the line. In 2 dimensions, on a surface, the information grows with the area. You can pack many more bits into a 2-dimensional region than into a 1-dimensional line of the same size. In 3 dimensions, information grows with volume. Even more storage. But here's the weird part. In our universe, there's a limit to how much information you can store in a region. And that limit is determined by the surface area, not the volume. This is called the holographic principle. It suggests that our 3-dimensional universe might actually be encoded on a 2-dimensional surface. That the 3rd dimension might be, in some sense, an illusion. A hologram. Feynman didn't live to see this principle fully developed, but he would have loved it, because it's exactly the kind of deep connection between dimensions, information, and reality that he spent his life exploring. Let me give you another one of Feynman's insights. He understood that dimensions affect how things scale, how structures change when you make them bigger or smaller. This is called dimensional analysis, and it's one of the most powerful tools in physics. Here's how it works. Suppose you want to build a bridge. You build a small model and it holds up fine. Now you scale it up. You make it 10 times bigger in every direction, 10 times longer, 10 times wider, 10 times taller. What happens? Well, the volume of the bridge scales as the cube of the size. If you make it 10 times bigger, the volume goes up by a factor of 10 cubed, which is 1,000. The mass goes up by a factor of 1,000. But the strength of the bridge depends on the cross-sectional area of its supports, and area scales as the square of the size. If you make it 10 times bigger, the area goes up by a factor of 10 squared, which is 100. So the mass goes up by a factor of 1,000, but the strength only goes up by a factor of 100. The bridge is 10 times weaker, relative to its weight, than the small model was. This is why you can't just scale up a design and expect it to work. This is why giant creatures can't exist. Why a giant ant would collapse under its own weight. The strength of bones and muscles scales with cross-sectional area, which goes as length squared. But the weight scales with volume, which goes as length cubed. Make an ant 10 times bigger, its weight goes up 1,000 times, but its strength only goes up 100 times. The ant collapses. Feynman loved this kind of reasoning, because it's pure geometry, pure dimensional analysis. You don't need to know the details of the ant's biology. You just need to know how things scale in 3 dimensions. And that tells you what's possible and what's not. Now here's where Feynman takes it further. He asks, what if space had more than 3 dimensions? How would scaling work then? In 4 spatial dimensions, volume would scale as length to the 4th power. Surface area would scale as length cubed. Strength would scale even more slowly compared to weight. Structures would be even more fragile. It would be even harder to build large, stable objects. This is another reason why 3 dimensions might be special. It's a sweet spot where you can have structures that are both complex and stable. Let me tell you about one of Feynman's most beautiful demonstrations. He wanted to show people how to think about dimensions in a concrete, visual way. So he invented a game where you try to visualize 4-dimensional objects by looking at their 3-dimensional cross-sections. Here's how it works. Imagine you have a 4-dimensional cube, a tesseract. You slice it with a 3-dimensional space. Depending on the angle of the slice, you get different 3-dimensional shapes. If you slice parallel to one of the faces, you get a cube. If you slice at an angle, you might get a hexagonal prism or other shapes. And as you rotate the tesseract in 4 dimensions, the shapes change. Cubes morph into other polyhedra. Faces appear and disappear. Edges connect in strange ways. Feynman would have people practice this. He'd describe the tesseract's structure. 8 cubes arranged in 4 dimensions, connected at their faces. And he'd ask, if I slice here, what do I see? If I rotate this way, what changes? And slowly people would start to develop an intuition, not for seeing 4 dimensions directly, but for understanding how 4-dimensional objects behave, how they project into 3 dimensions, how they change when manipulated. This is Feynman's genius. He didn't just explain dimensions, he taught people how to think about them, how to build mental models, how to connect abstract mathematics to concrete visualization. And in doing so, he made dimensions click for countless students and physicists. Now, let's address something fundamental, something that confuses people endlessly. What is a dimension, really? I've been talking about directions, about freedom to move, about independent ways to vary. But what does that mean, precisely? Feynman had a beautiful answer. A dimension is a parameter, a number that can vary independently of all other numbers. That's it. That's the definition. Think about it. To specify a point on a line, you need one number, the position along the line. That's one parameter, one dimension. To specify a point on a plane, you need 2 numbers, x and y coordinates, 2 parameters, 2 dimensions. To specify a point in space, you need 3 numbers, x, y, and z, 3 parameters, 3 dimensions. To specify a point in space-time, you need 4 numbers, x, y, z, and time. 4 parameters, 4 dimensions. But here's the key. The parameters have to be independent. They have to vary separately. If you have 2 parameters that are related, that always change together in a fixed way, then you don't really have 2 dimensions. You have 1 dimension described in a complicated way. Here's an example. Suppose I give you 2 numbers, a and b, and I tell you they're always equal. A equals b, always. Then even though I gave you 2 numbers, you only have 1 degree of freedom. 1 parameter you can change, 1 dimension. The second number is redundant. It doesn't add information. It doesn't add freedom. This is crucial for understanding dimensions. It's not just about how many numbers you write down, it's about how many independent directions you can move, how many ways reality can vary. And Feynman understood this deeply. He knew that dimensions are about the structure of possibility, about the space of all possible configurations. Here's where this gets profound. In physics, we talk about configuration space, the space of all possible states of a system. And the dimension of configuration space is the number of independent parameters needed to specify the system's state. For a single particle in three-dimensional space, configuration space is three-dimensional. For two particles, it's six-dimensional. 3 coordinates for each particle. For 100 particles, it's 300-dimensional. Feynman spent much of his career working in these high-dimensional spaces. In quantum mechanics, the state of a system is a point in an abstract, high-dimensional space, and the evolution of the system is a path through that space. Feynman's path integral formulation of quantum mechanics is all about summing over all possible paths in configuration space, and configuration space can have arbitrarily many dimensions, hundreds, thousands, infinitely many. This is where Feynman's understanding of dimensions became essential. He had to think about spaces with millions of dimensions, spaces that no human can visualize. And yet, he could work with them. He could derive physical predictions from them. He could make them meaningful. How? By using the principles I've been explaining. By thinking about dimensions as parameters, as degrees of freedom, as independent directions. By not trying to visualize everything at once, but instead focusing on slices, projections, and specific properties. Now let me tell you about one of Feynman's most startling ideas. An idea that connects dimensions to the fundamental nature of reality. He realized that the number of dimensions in our universe might not be an accident. It might be determined by the laws of physics themselves, or conversely, the laws of physics might be determined by the number of dimensions. Here's what I mean. In string theory, which Feynman was skeptical of but acknowledged as interesting, the fundamental objects are not particles, but tiny vibrating strings. And for the mathematics of string theory to work, for the equations to be consistent, space must have exactly 10 dimensions. Not 9, not 11. 10. 6 of those dimensions are spatial dimensions we can't see, curled up small. But the theory demands 10. The consistency of the mathematics requires it. Feynman found this remarkable. The idea that you can't just choose the number of dimensions arbitrarily. That the structure of the theory constrains the dimensionality of space. This suggests something profound. That dimensions and laws are intertwined. That the geometry of space and the physics of matter are two aspects of the same underlying reality. But Feynman was also cautious. He'd remind people that just because a theory requires 10 dimensions doesn't mean space actually has 10 dimensions. It means the theory requires 10 dimensions. And if the theory is wrong, then its dimensional requirements are irrelevant. This is the scientific method. This is how you think carefully about these ideas. You distinguish between what the math says and what reality is. You test, you observe, you check. Let me give you a concrete example of how dimensions matter in real physics. One that Feynman worked on directly. In quantum field theory, particles are excitations of fields, and fields exist everywhere in space. The electromagnetic field, for instance, has a value at every point in space. That value can oscillate, and those oscillations are photons. Now here's the thing. When you calculate what happens in quantum field theory, you get infinities. You calculate the mass of an electron, and the math says it's infinite. You calculate the probability of a process, and the math says it's infinite. These infinities plagued physics for decades, until Feynman and others figured out how to deal with them through a process called renormalization. And here's where dimensions come in. The infinities in quantum field theory depend on the dimension of space. In some dimensions, the infinities are worse. In other dimensions, they're better. In exactly 4 space-time dimensions, which is what we have, 3 space plus 1 time, the infinities have a very specific structure. And that structure makes renormalization possible. The theory is renormalizable. In other dimensions, it wouldn't be. In 5 space-time dimensions, for instance, quantum electrodynamics is not renormalizable. The infinities can't be absorbed. The theory doesn't work. Feynman found this astonishing. The fact that our universe has exactly the right number of dimensions for quantum field theory to work. 4 space-time dimensions. Not 3, not 5. 4. Is this a coincidence, or is it a clue? Feynman didn't know. He'd say it's either an amazing accident or a deep principle we don't yet understand. But either way, it shows that dimensions matter. They're not just background. They're not just a stage where physics happens. They're part of the structure, part of what makes physics work. Let's talk about time, because time is a dimension too. Feynman emphasized this constantly. When we say space-time has 4 dimensions, we mean 3 spatial dimensions and 1 time dimension. Time is not just a parameter. It's a dimension in the same sense that space is a dimension. It's an independent direction. A direction you can move in, or at least a direction that varies independently of space. But time is different from space in crucial ways. You can move forward or backward in space freely. You can turn around. But time only goes one direction. You move forward through time. You can't turn around. You can't go backward, at least not in any way we understand. This asymmetry makes time special. It's a dimension, but a different kind of dimension than the spatial ones. Feynman would ask, why is time different? What makes it special? And the answer is subtle. In the mathematics of relativity, time and space are unified into space-time, but they enter the equations with opposite signs. Space contributes positively to the space-time interval. Time contributes negatively. This sign difference is what makes time different from space. It's what gives time its arrow, its directionality. But here's something wild. In quantum mechanics, Feynman discovered that you can treat time like space. In his path integral formulation, you sum over all possible paths a particle can take, not just through space, but through space-time. And in that formulation, time and space are on equal footing. You can even rotate between them, turn time into space and space into time, mathematically. And this rotation has physical consequences. It's how you calculate quantum effects. Feynman loved this, the idea that time is just another dimension, that the division between space and time is not absolute, that they're 2 aspects of a unified structure. And understanding this was key to unlocking quantum field theory, key to understanding how particles behave. Now here's something most people never think about. Dimensions don't have to be spatial or temporal. They can be anything. Any independent parameter is a dimension. Color, for instance, is a dimension in a certain sense. If you're describing a colored surface, you need spatial coordinates to say where you are, and you need color coordinates to say what color the surface is. The color space is its own dimension, separate from physical space. Or consider temperature. A weather map shows temperature as a function of position. Temperature is not a spatial dimension, but it varies across space. You can think of it as an extra dimension, a field defined on space. Every point in space has a temperature value. The space of all possible temperature distributions is infinite dimensional. Feynman understood this abstraction. He knew that dimensions are not limited to physical space. They're any independent variable. And this generalization is incredibly powerful. It lets you think about complex systems with many parameters as geometric objects in high-dimensional spaces. And then you can use geometric intuition to understand those systems. Let me give you one final example of Feynman's brilliance with dimensions, one of his most famous ideas. In quantum electrodynamics, you calculate the probability of a particle interaction by drawing diagrams. Feynman diagrams. Each diagram represents a possible way the interaction can happen, and you sum over all diagrams to get the total probability. Now here's the thing. Feynman diagrams are usually drawn in 2 dimensions. You have a horizontal axis representing space and a vertical axis representing time, and you draw lines representing particles moving through space-time. But Feynman emphasized that the diagram is not a picture of reality. It's a symbolic representation. The particles don't actually move along those lines in real space. Why? Because the lines represent paths in space-time, which is 4-dimensional. And you can't draw 4 dimensions on paper, so you project. You collapse 4 dimensions down to 2 for visualization. And in doing so, you lose information. The diagram is schematic. It's a mnemonic, a tool for organizing the calculation. But the real physics happens in 4 dimensions. Feynman was adamant about this. He'd tell students, don't confuse the diagram with reality. The diagram is a map. It's not the territory. The territory is 4-dimensional space-time. The map is 2-dimensional paper. Use the map, but remember what it represents. This distinction is crucial, because it's easy to mistake the representation for the thing itself, to think that particles really zigzag along lines the way they do in diagrams, but they don't. They exist in 4-dimensional space-time, and the diagrams are just a way to keep track of the math. All right, let's bring this all together, because we've covered a lot and I want to make sure the picture is clear. Dimensions are degrees of freedom, independent directions, ways that reality can vary. We live in a universe with 3 large spatial dimensions and 1 time dimension. But there might be extra dimensions, small and curled up, that we can't directly perceive. The number of dimensions determines the laws of physics. It affects how forces scale with distance, how structures can form, what patterns are possible. 3 spatial dimensions are special. They allow inverse square laws, stable orbits, complex structures. Fewer dimensions would be too simple. More dimensions would be too chaotic. At least for large dimensions. Small extra dimensions might exist without disrupting the physics we know. Dimensions aren't just mathematical abstractions. They're real, physical, measurable. We can test for extra dimensions in particle colliders. We can look for their effects in the behavior of gravity. We can use dimensional analysis to predict how systems scale. And we can use our understanding of dimensions to build models of reality that match what we observe. Feynman taught us how to think about dimensions, not by visualizing them all at once, which is impossible for higher dimensions, but by looking at slices, by understanding projections, by focusing on the properties that matter. He showed us that you don't need to see something to understand it. You just need to know how it behaves, how it affects the things you can measure. And that's the power of physics. Not just collecting facts, but building a framework for understanding. A way to take things you can't see, can't visualize, can't directly experience, and still make precise, testable predictions about them. Dimensions are the perfect example. You can't see 4 spatial dimensions, but you can calculate what would happen if they existed, and then you can look for those effects. And that's what science is. That's what Feynman dedicated his life to. Here's the deepest part. The universe is not required to make sense to your intuition. You evolved to navigate 3-dimensional space at human scales. Your brain is optimized for that. It's not optimized for understanding quantum mechanics or relativity or higher dimensions. Those things feel weird because they are weird, relative to everyday experience. But they're not weird relative to reality. They're just reality. And Feynman's gift was showing people how to accept that, how to let go of intuition when intuition fails, how to trust the math, how to follow the logic, how to test the predictions, and how to build a new kind of understanding, an understanding based not on what feels right, but on what actually is. So when you think about dimensions, remember this. You're not trying to visualize them the way you visualize a cube. You're trying to understand their properties, how they behave, what they allow, what they forbid. And once you understand that, once you grasp the logic, dimensions click. They make sense, not in the way a picture makes sense, but in a deeper way, in the way that mathematics makes sense, in the way that structure and pattern and consistency make sense. That's what Feynman taught us. That's what makes dimensions click. Not visualizing four-dimensional space, but understanding that 4 dimensions means 4 independent parameters, 4 degrees of freedom, 4 ways that reality can vary. And that understanding is more powerful than any visualization. Because it's true. It's accurate. It's how the universe actually works. We are creatures of 3 dimensions trying to understand a cosmos that might have more. And the fact that we can do this at all, the fact that we can build theories and make predictions and test them and refine them, that's extraordinary. We can't see the extra dimensions if they exist. We can't float outside space-time and look at its structure from the outside. But we can measure, we can calculate, we can deduce. And that's enough. That's Feynman's legacy, showing us that the human mind, limited as it is, can still grasp the fundamental structure of reality, that we can understand things beyond our direct perception, that dimensions, even extra dimensions, even higher dimensions, are not mysteries forever beyond reach. They're just another aspect of reality, another thing to measure, to study, to understand. So the next time someone asks you about dimensions, don't just say, up, down, left, right, forward, backward. Tell them what Feynman would tell them. Tell them that dimensions are freedom, that they're parameters, that they're the fabric of possibility itself, and that understanding them is understanding the shape of reality. Because that's the truth. That's what dimensions are. And once you see it, once it clicks the way Feynman made it click, you can never unsee it. The universe reveals itself not as a collection of objects in space, but as a geometric structure. A structure with dimensions, with curvature, with patterns. And we, tiny creatures on a tiny planet, have figured out how to read that structure, how to decode it, how to make it make sense. That's not just impressive, that's miraculous. And it's all thanks to people like Feynman who refused to accept "I don't understand" as a final answer, who pushed and questioned and explored until dimensions clicked, until the pieces fit, until reality revealed its secrets. And now those secrets are yours. You know what dimensions really are. You know why they matter. You know how to think about them. That's Feynman's gift to you. Use it well. But wait. There's one more thing, one more piece that Feynman would want you to know, because understanding dimensions isn't just about abstract geometry. It's about understanding measurement itself, about understanding how we know anything at all about the structure of space. Here's the question: how do you measure a dimension? How do you prove that space has 3 dimensions and not 2 or 4? It seems obvious. You can move in 3 independent directions, so there must be 3 dimensions. But that's circular reasoning. How do you know those directions are truly independent? How do you know there aren't hidden dimensions you're missing? Feynman had an answer. You measure. You do experiments. You check if the laws of physics match what you'd expect for a given number of dimensions. Here's a simple test. Take a sound wave. In 3 dimensions, sound spreads out as a sphere. The intensity decreases as 1 over distance squared because the energy spreads over the surface of a sphere, and that surface area grows as distance squared. But in 2 dimensions, sound would spread as a circle. The intensity would decrease as 1 over distance because the circumference of a circle grows linearly with radius. So you can measure how sound intensity decreases with distance. If it goes as 1 over distance squared, you're in 3 dimensions. If it goes as 1 over distance, you're in 2 dimensions. The dimension of space determines the behavior of waves. The same applies to light, to gravity, to any field that spreads through space. The way fields dilute with distance tells you the dimensionality of space. And we've measured this extensively. In every experiment we've ever done, fields behave exactly as they should in 3 spatial dimensions. The inverse square law holds. Space is 3-dimensional, at least on the scales we can measure. But here's the subtle part. These measurements only tell you about large dimensions. dimensions big enough that waves can spread through them. If there are tiny curled-up dimensions, dimensions smaller than the wavelength of light, then light can't probe them. They're invisible to this test. So we can confirm 3 large dimensions, but we can't rule out small extra dimensions. Not with this method. That's why physicists use particle colliders. Smash particles together at enormous energies. Give them enough energy to probe tiny distances. If there are extra dimensions, even small ones, high-energy particles can reach into them. And when they do, something strange happens. The particles gain extra momentum. Extra energy states. Resonances that shouldn't exist in 3 dimensions alone. No such resonances have been found yet. But the search continues. Each new experiment probes smaller distances, higher energies. And if extra dimensions exist, eventually we'll find them. Or we'll rule them out down to such small scales that they become irrelevant for physics. Either way, we learn something fundamental about reality. Feynman loved this aspect of science, the way theory and experiment work together. Theory predicts what extra dimensions would do. Experiment looks for those effects. And the conversation between theory and experiment drives progress. It's not about believing in extra dimensions or not believing. It's about testing, measuring, checking. And that's the scientific method. That's how we learn about dimensions. Not through pure thought, not through intuition, but through measurement, through observation, through checking our ideas against reality and letting reality have the final say. So here we are, at the end of this journey through dimensions. And what have we learned? We've learned that dimensions are more than directions. They're the structure of possibility itself, the framework within which reality exists. We've learned that 3 dimensions are special, but not necessarily unique. That extra dimensions might exist, curled up small, invisible, but real. We've learned how to think about dimensions we can't visualize, how to use slices and projections, how to work with abstract spaces and make them concrete through mathematics. We've learned that the laws of physics depend on dimensions, that forces scale differently, that structures behave differently, that everything changes when you change the dimensionality of space. And we've learned Feynman's greatest lesson. That understanding comes not from seeing, but from measuring, from testing, from building models and checking them against experiment, from following the logic wherever it leads, even if it leads somewhere strange, somewhere counterintuitive, somewhere your brain doesn't want to go. Because that's where the truth lives, in the places your intuition can't reach, in the structures your eyes can't see, in the geometry that underlies everything but reveals itself only through careful thought and precise measurement. Dimensions are there, in the fabric of space, in the laws of physics, in the behavior of every particle and wave and field. You just have to know how to look. And now you do. That's what Feynman gave us, the tools to look, the framework to understand, the confidence to explore, and the humility to let reality teach us, rather than insisting reality conform to our expectations. That's the shocking truth about dimensions. They're real, they're measurable, they're fundamental, and they're accessible. Not through mystical insight, not through visualizing the unvisualizable, but through physics, through mathematics, through the patient work of building theories and testing them. Feynman made dimensions click by showing us this path, by demonstrating that understanding doesn't require seeing. It requires thinking clearly, calculating carefully, testing rigorously, and accepting what the evidence shows, even when it's strange, especially when it's strange. So the next time you hear about dimensions, remember Feynman. Remember that dimensions are parameters, degrees of freedom, the shape of the space of possibilities, and remember that we can understand them, we can measure them, we can work with them, even when we can't see them. That's the power of physics. That's the beauty of Feynman's approach. And that's why dimensions click, not because they suddenly become intuitive, but because they become precise, testable, real. And once something is real, once you can measure it and calculate with it and make predictions about it, then you understand it. Even if you can't visualize it, even if it doesn't feel right. Understanding is not about feelings, it's about structure, about pattern, about the way things connect and relate and depend on each other. And dimensions are the ultimate example of structure, the framework within which everything else exists. The stage, except not really a stage because the stage is part of the play. The dimensions are part of reality, shaped by reality, shaping reality in turn. And we figured this out. Tiny humans on a tiny planet. We figured out the dimensional structure of the cosmos. Not completely, not finally, but enough to make predictions, enough to test them, enough to know we're on the right track. That's extraordinary. That's what Feynman celebrated, the power of the human mind to understand reality beyond direct perception. So take this understanding. Use it. Think about space not as a fixed background, but as a structure with dimensionality. Think about physics not as forces and particles, but as geometry and pattern. Think about reality not as what you can see, but as what you can measure and calculate and predict. That's Feynman's legacy. That's how dimensions click. And once they click for you, you see the universe differently. Not as a collection of stuff in space, but as a geometric structure, a pattern in space-time, a configuration in a high-dimensional space of possibilities. And you realize that understanding this structure, grasping this pattern, is what physics is all about. Welcome to Feynman's world, where dimensions make sense, where mathematics reveals reality, where measurement is the path to truth. It's a strange world, a counterintuitive world, but it's the real world. And now you have the tools to explore it. Time doesn't flow the way you think it does. Richard Feynman discovered something so strange about time that it won him a Nobel Prize, and most people still don't understand what he actually found. What he revealed wasn't just a mathematical trick. It was a fundamental truth about reality that breaks everything you thought you knew about cause and effect, about past and future, about the very nature of time itself. Here's the paradox. An electron moves through space. Simple, right? But according to Feynman's work, that electron doesn't just move forward in time. Sometimes it moves backward. Not metaphorically, not as a mathematical convenience, actually backward through time. And when an electron moves backward through time, we see it as something else entirely. We see it as antimatter. Let me be clear about what I'm saying. Feynman proposed that a positron, the antimatter version of an electron, is literally an electron moving backward through time. Think about that. The same particle, just traveling in the opposite temporal direction. And this isn't speculation. This idea is built into the mathematics of quantum electrodynamics, the theory that describes how light and matter interact. The theory Feynman won the Nobel Prize for developing. But wait, if particles can move backward in time, doesn't that create paradoxes? Doesn't that violate causality? Doesn't that mean the future can affect the past? Yes. And that's exactly what makes this so profound. The universe doesn't work the way your intuition insists it should. Time at the quantum level is not a one-way street. It's something far stranger. Let me start with what Feynman was trying to solve, because understanding the problem makes the solution even more remarkable. In the 1940s, physicists were stuck. They had quantum mechanics, which described particles beautifully. They had relativity, which described space and time. But when they tried to combine them, when they tried to describe how electrons and photons interact at high speeds, the math exploded. Literally, they got infinite answers. Nonsense. The equation said that an electron's mass should be infinite, that its charge should be infinite, that everything should be infinite. Obviously wrong. Scientists tried everything. They tweaked the equations, adjusted the assumptions, invented new mathematical tricks. Nothing worked. The infinities kept appearing. It was a crisis. The theory that should describe the most fundamental interactions in nature was completely broken. And then Feynman had an idea. A crazy idea. An idea so simple and so radical that it changed everything. He said, "What if we stop thinking about particles moving through space and time as a single path? What if, instead, a particle takes every possible path simultaneously? Every path, all at once. The electron goes straight. It zigzags. It loops back. It goes backward in time, forward in time, sideways through dimensions you can't even imagine. Every single possibility happens." Now, you're thinking that's absurd. If a particle takes every path, how does anything happen? How do we see the electron go from point A to point B? Here's Feynman's genius. Each path contributes to the final outcome, but they don't all contribute equally. Each path has a certain probability, a certain amplitude, and when you add up all the amplitudes from all the paths, most of them cancel out. They interfere destructively. The crazy paths, the ones that loop around or go backward, they mostly disappear when you sum everything up. But not entirely. Some of those bizarre paths survive. Some of them contribute. And that's where the magic happens. Because those paths that include backward time travel, those paths where the electron becomes a positron for a moment, those paths are necessary to make the math work. Without them, you get the wrong answer. With them, you get nature. Let me show you what I mean with a concrete example. Imagine two electrons approaching each other. They repel. You learned this in school, like charges repel. But how does that actually happen? One electron has to somehow know the other electron is there. They have to communicate. And they communicate by exchanging a photon. One electron emits a photon, the other absorbs it, and the momentum transfer causes them to push apart. But here's the problem. If you calculate this process using normal quantum mechanics, you get the wrong answer. The calculation doesn't match experiments. It's close, but not exact. There's a correction, a tiny additional effect that the simple picture misses. And when Feynman calculated this correction using his path integral method, accounting for all possible paths the particles could take, including paths where time runs backward, he got the exact right answer. Perfect agreement with experiment. Why? Because some of the paths involve one electron briefly traveling backward in time, appearing as a positron, and then coming forward again. These paths contribute to the interaction. They're part of reality. And if you ignore them, your prediction is wrong. Now watch this. Feynman didn't just use this idea for electrons and photons. He developed a complete framework, a new way of doing quantum mechanics. He invented what we now call Feynman diagrams. These are pictures, simple drawings with lines and vertices that represent all the possible ways particles can interact. And in these diagrams, time runs vertically. Particles moving up the page are moving forward in time. Particles moving down the page are moving backward in time. An electron going forward in time is drawn as a line with an arrow pointing up. A positron, the antimatter particle, is drawn as a line with an arrow pointing down. But here's the key insight. They're the same line, the same particle, just moving in different temporal directions. An electron moving backward through time is indistinguishable from a positron moving forward through time. They have the same mass, the same spin, opposite charge, exactly as you'd expect if time reversal flipped the charge. This is not just a mathematical convenience. This is Feynman telling you something deep about reality. Antimatter is matter moving backward through time. That's why antimatter exists. That's why it has opposite charge. That's why when matter and antimatter meet, they annihilate. They're not destroying each other. They're canceling temporal directions. One path going forward meets one path going backward, and they both disappear in a flash of energy. Let me tell you about the moment Feynman realized this. He was a graduate student at Princeton, working with John Wheeler, his PhD advisor. They were discussing the problem of self-interaction. An electron creates an electromagnetic field, and that field affects the electron itself. It's like the electron is pushing on itself. And when you try to calculate this, you get infinite answers. Wheeler suggested something radical. What if there's no electromagnetic field at all? What if the field is just a mathematical convenience, and what's really happening is that electrons interact directly with other electrons, including their future and past selves? Feynman took this idea seriously. He worked out the math, and he discovered that if you allow particles to interact with their own past and future, the infinities go away. But there's a price. You have to accept that information can flow backward in time. You have to accept that the future affects the past. You have to accept that causality, as you understand it, is not fundamental. This is where the paradox lives. In classical physics, in everyday life, causes precede effects. You drop a glass, then it breaks. The dropping causes the breaking. Time flows in one direction, from past to future, and causality flows with it. But in Feynman's quantum electrodynamics, this is not always true. At the quantum level, the distinction between cause and effect blurs. Future events can influence past events through these backward time paths. Now you might be thinking, okay, but we never see this in everyday life. We never see the future affecting the past. We never see effects preceding causes. And that's true. On human scales, time behaves normally. The future doesn't reach back and change the past. Why not? Because of interference. Remember, every path contributes, but most of them cancel out. The paths where large objects move backward in time, where macroscopic causality is violated, these paths interfere destructively with overwhelming probability. They wash out. Only the forward time paths survive on average. But at the quantum level, where we're dealing with single particles, individual electrons and photons, the backward time paths don't always cancel. Sometimes they survive. Sometimes they contribute measurably to what happens. And that's why quantum mechanics is weird. That's why particles can tunnel through barriers, why they can be in multiple places at once, why they can seem to know about the future. Because, in a sense, they do know about the future. They're exploring paths that include it. Here's something remarkable. Feynman's approach doesn't just work for electrons and photons. It works for everything. Every particle in the universe, every interaction, every force can be described using this path integral formulation. You sum over all possible histories, all possible paths through space and time, including paths that go backward, and out comes the probability for what you'll observe. This is one of the deepest principles in physics. It's called the principle of least action in its classical form, but Feynman elevated it to a quantum principle. Everything that can happen does happen, and nature averages over all possibilities. Let me show you why this matters beyond just electrons and positrons. Feynman's formulation gave us the tools to calculate processes that were impossible to calculate before. It gave us quantum electrodynamics, QED, the most accurate theory in all of science. When we use QED to calculate properties like the magnetic moment of the electron, we get agreement with experiment to 10 decimal places. 10. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. No other scientific theory even comes close to this level of precision. And it all comes from allowing time to run backward. From taking seriously the idea that particles can move into the past, that future and past are connected in ways we don't see at large scales. This is what won Feynman the Nobel Prize in 1965. Not just the path integral formulation, but the entire framework of quantum electrodynamics that he helped develop, which is built on these ideas. But here's where it gets even stranger. If antimatter is matter moving backward through time, then we should be able to flip this around. We should be able to describe any process involving antimatter as a process involving matter going the wrong way through time. And we can. Look at pair production. A photon with enough energy can spontaneously create an electron and a positron. Two particles appear from nothing. Where did they come from? Energy converted to mass. Okay, fine. But here's another way to see it. The photon doesn't create two particles. It creates one particle, an electron, that briefly moves backward in time before turning around and moving forward again. The moment when it's moving backward, we call it a positron. The moment when it turns around, we call it pair production. But from the particle's perspective, there's only one particle. It just takes a U-turn in time. Think about that. What we see as creation of matter and antimatter, the particle sees as just changing its direction through time. And when the electron and positron annihilate, turning back into photons, what's really happening? The electron reaches the point where it turned around, and time straightens out again. The loop closes. The particle stops its temporal detour and gets back on the forward path. This is not metaphor. This is not analogy. This is the actual mathematical description of what's happening in quantum electrodynamics. The equations don't distinguish between these interpretations. Both are equally valid. Both give the same predictions. Both describe the same reality. And that tells you something profound about time itself. Now let me tell you the really unsettling part. If electrons can move backward through time, if particles can take paths that connect future to past, what does that mean for free will? What does that mean for the idea that the future is open, undetermined, not yet decided? If the future affects the past, isn't the future already real? Doesn't that mean everything is predetermined? Here's where we have to be careful. Feynman's formulation doesn't say the future is determined. It says the future contributes to the present. All possible futures contribute. Every outcome, every branch, every possibility sends paths backward in time that interfere with the present. And when you sum over all these contributions, you get probabilities, not certainties. Probabilities. The future is real in the sense that it participates in defining the present. But it's not singular. It's not one definite thing that's already happened, and we just haven't gotten there yet. It's a superposition of possibilities, all of which exist in potential, all of which send influences backward. And the sum of all these influences determines what we observe now. Does that mean the present can affect the past? In a sense, yes. If you measure a particle now, you collapse its wave function, you force it to take a definite value, and that choice affects which histories contributed to its current state. You're retroactively selecting which paths through time were real. This is called retrocausality, and it's one of the most controversial ideas in quantum mechanics. Feynman didn't explicitly advocate for retrocausality, but his formulation allows it. The math permits influences to flow backward in time, and nothing in the theory forbids it. Here's an experiment that shows this. The delayed choice quantum eraser. You don't need to understand all the details, but here's the basic idea. You send photons through a double slit, and they create an interference pattern. This pattern tells you the photons behaved like waves, taking both paths simultaneously. But if you measure which slit the photon went through, the interference pattern disappears. The photon behaves like a particle taking only one path. Now here's the twist. You can delay the measurement. You can let the photon pass through the slits, let it hit the screen, and only then measure which path it took. You'd think this shouldn't matter. The photon already hit the screen. Its fate is sealed. But when you do this experiment, the interference pattern appears or disappears depending on whether you make the which path measurement, even though that measurement happens after the photon hit the screen. The future measurement affects the past behavior of the photon. This has been done. This is real experimental physics, not speculation. And Feynman's path integral formulation explains it naturally. The photon's path includes future interactions. The measurement you will make is part of the sum over paths. Future and past are entangled in the quantum description. Let me bring this back to Feynman himself, because understanding the man helps understand the work. Feynman was a maverick. He didn't think like other physicists. While his colleagues were working with complicated equations, drowning in mathematical formalism, Feynman was drawing pictures. He was asking himself, what's really happening? What does the electron actually do? And he trusted his intuition even when it led to crazy places. The story goes that when Feynman first presented his diagrams at a conference, the established physicists were skeptical. These pictures seemed too simple, too childish. Where was the rigorous mathematics? Where were the proofs? But Feynman's diagrams worked. They gave the right answers. And gradually, every physicist learned to use them. Today, Feynman diagrams are the standard language of particle physics. Every student learns them. Every paper uses them. They're fundamental. But what made Feynman's approach revolutionary wasn't just the diagrams, it was the philosophy behind them. Feynman believed that nature is fundamentally simple, that the complexity we see emerges from simple rules applied to all possibilities. He believed that if you can't explain something simply, you don't understand it. And he believed that time is more symmetric than our everyday experience suggests. Think about the equations of physics. They're almost all time reversible. If you have a valid solution, you can run time backward, and you get another valid solution. Newton's laws work equally well forward or backward in time. Maxwell's equations for electromagnetism are time symmetric. Even Einstein's general relativity is time reversible. The universe doesn't care which direction time flows. That's a deep clue that time symmetry is built into the fabric of nature. Of course, we experience time flowing in one direction. We remember the past, not the future. Eggs break, but don't spontaneously unbreak. Entropy increases. The arrow of time is real. But Feynman showed that at the fundamental level, at the level of individual particles, time's arrow is not absolute. Particles can go both ways, and the forward flow of time we experience emerges statistically from the sum over all those backward and forward paths. Here's another way to think about it. In classical physics, you solve for the future by knowing the present and applying the laws of motion. Initial conditions plus laws equals final state. Cause leads to effect. But in Feynman's formulation, you solve for the present by considering all possible pasts and all possible futures simultaneously. The past and future are inputs on equal footing, and what happens now is determined by the interference of all these possibilities. This is completely alien to how we think about time. We think of ourselves as moving through time, from past to future, making choices, causing effects. But from the Feynman perspective, we're part of a four-dimensional structure where past, present, and future are all equally real, all connected by quantum amplitudes, all participating in defining each other. Now, does this mean time travel is possible? Can we build a machine that sends information backward through time? The answer is subtle. At the level of individual particles, time reversal happens constantly. Particles take paths that go backward, that loop through time, that connect future to past. But these paths average out. They interfere. On large scales, causality is preserved not because backward time travel is forbidden, but because forward and backward contributions balance in such a way that macroscopic causality emerges. Could you exploit this? Could you arrange things so that a message propagates backward in time on a scale we could detect? Probably not. The interference is too effective. The cancellation is too complete. Quantum mechanics allows backward time paths, but it also enforces that they don't produce observable paradoxes. The universe is self-consistent. You can't change the past in a way that prevents the present from having been the past that led to the present. That's circular, but it's the truth. The universe is circular in time at the quantum level. Let me tell you about one more aspect of Feynman's work that connects to time. Renormalization. Remember those infinities I mentioned earlier? The ones that plagued quantum electrodynamics? Feynman found a way to get rid of them, not by changing the physics, but by carefully reorganizing the calculations. He showed that the infinities come from including contributions at arbitrarily short distances and high energies, and that these contributions can be absorbed into the definitions of mass and charge. You measure the electron's mass in experiments. That measured value already includes all the quantum corrections, all the effects of the electron interacting with its own field, all the virtual particles swarming around it. So you don't need to calculate the mass from first principles, you just use the measured value. The infinities disappear because you're not asking the theory to predict something you already know. You're asking it to predict new things, and those predictions are finite. This procedure is called renormalization, and it's one of the most powerful tools in physics. But it's also controversial because it feels like a cheat. You're hiding the infinities instead of explaining where they come from. Feynman himself was uncomfortable with it. He called renormalization a dippy process and said it's not mathematically legitimate. But it works. It gives the right answers. And sometimes in physics, getting the right answer is more important than mathematical purity. What does this have to do with time? Well, renormalization is all about integrating overall possible paths, including paths that go to arbitrarily short times, arbitrarily small distances. When you allow particles to interact at every possible scale, including the Planck scale where quantum gravity becomes important, you get infinities. Feynman's path integral approach makes these infinities explicit and shows how to handle them. Time, at the smallest scales, becomes fuzzy, uncertain, mixed up with space in ways we can't resolve with current theories. So here's the picture. At everyday scales, time flows forward. Cause precedes effect. The past is fixed, the future is open, but at quantum scales, time is more fluid. Particles explore paths going both directions. Future and past interfere. And at the smallest scales, near the Planck length and Planck time, space and time themselves might dissolve into something more fundamental, something we don't yet understand. Feynman gave us the tools to navigate this strange landscape. His path integrals, his diagrams, his entire approach to quantum field theory rests on taking time symmetry seriously, on allowing particles to go backward, on summing over all possible histories. And this framework has been so successful that we've extended it far beyond electrons and photons. We use it to describe quarks, gluons, the weak force, the Higgs boson, everything in the standard model of particle physics. Every prediction of the standard model uses Feynman's methods. Every calculation of how particles scatter, decay, or transform relies on summing over Feynman diagrams, including diagrams with loops that go backward in time. This is not abstract theory. This is the tool we use to design particle accelerators, to interpret experimental data, to discover new particles. When the Higgs boson was found at CERN in 2012, the analysis that confirmed it was a Higgs used Feynman diagrams. When we measure the properties of the top quark, we use Feynman diagrams. This is the working language of the field. And at the heart of it all is this paradox. Time runs backward. Particles are their own antiparticles moving the opposite direction through time. Future and past are connected. The universe sums over all possibilities, and what we observe is the interference pattern of histories that never happened but still contribute. Let me bring this to a close because we've covered a lot and I want to make sure the picture is clear. Feynman's Nobel Prize work revealed that time at the quantum level is not what we think. It's not a river carrying us from past to future. It's not an arrow pointing one direction. It's a dimension like space, and particles can move through it in both directions. When they move backward, we call them antimatter, but they're the same particles, just time reversed. This idea solves real problems. It makes calculations possible that were impossible before. It explains why QED works, why we can predict particle interactions with astonishing precision, why antimatter exists and behaves the way it does. But it also raises deep questions about causality, about determinism, about the nature of time itself. Does the future already exist? In some sense, yes, it participates in the present. Does the past change when we make measurements? In some interpretations, yes, we select which histories were real. Is time fundamentally different from space? Maybe not. Maybe time is just another dimension, and our experience of it flowing is an illusion, an artifact of entropy and memory. These are not settled questions. Physicists still debate the interpretation of quantum mechanics, the meaning of the wave function, the reality of retrocausality. Feynman's formulation is agnostic about these issues. It gives you the tools to calculate, but it doesn't tell you what's really happening. And maybe that's appropriate. Maybe the universe is quantum at its core, and our classical intuitions about what's really happening are simply wrong. Here's what I want you to take away from this. The universe is stranger than you imagined. Time doesn't work the way your experience tells you it does. Particles can move backward through time, and this is not speculation. It's part of our most successful physical theory. Feynman saw this. He built a framework around it. And he won the Nobel Prize for showing us that reality is weirder and more beautiful than common sense suggests. You'll never look at time the same way again. Every time you see matter and antimatter annihilate in a particle detector, remember, you're watching a particle loop through time. Every time you read about quantum entanglement or superposition, remember, you're seeing the universe sum over all paths, including impossible ones. Every time you wonder what time really is, remember Feynman's answer. Time is a dimension. Particles explore it in all directions. And we experience only the interference pattern of all these explorations. That's the paradox hidden inside Feynman's Nobel Prize work. Time runs backward. The future affects the past. Cause and effect blur at the quantum level. And yet from this strange foundation, we've built the most precise scientific theory ever created. We can predict nature with 10 decimal places of accuracy by assuming particles time travel. That's not intuitive. That's not obvious. But it's true. And here's the final thought I'll leave you with. Feynman showed us that the universe doesn't care about our intuitions. It doesn't care that time travel seems impossible. It doesn't care that causality feels fundamental. The universe follows its own rules, and our job as physicists, as thinking beings, is to discover those rules even when they violate everything we thought we knew. Feynman did that. He looked at time, really looked at it, and he saw that it could run both ways, and he had the courage to take that seriously, to build a theory on it, and to show that it works. We are living in the universe Feynman described, a universe where time is not what it seems, where particles are time travelers, where future and past are woven together in a quantum tapestry. And we figured this out. Tiny creatures on a tiny planet, using mathematics and experiments, unraveled one of the deepest secrets of time itself. That's remarkable. That's what physics is about. Not just collecting facts, but seeing through the illusion of everyday experience to the strange, beautiful reality underneath. Nothing can go faster than light. You've heard this before. It's one of those facts that everyone knows. 186,000 miles per second. 300 million meters per second, the cosmic speed limit. But have you ever stopped to ask why? Why does speed have a limit at all? What's stopping you from just going faster and faster forever? Your brain probably imagines something like a wall, like you hit some barrier in space and can't push through. Or maybe you think it's about engines, about not having enough power. But that's not it. Not even close. The truth is so much stranger, so much deeper. And Richard Feynman, one of the greatest physicists who ever lived, saw through to the heart of it. Let me show you what he found. Here's what most people think. They think the speed of light is just a really big number, a cosmic speed limit sign posted by the universe. But that's not what it is. The speed of light isn't just fast. It's not just the fastest thing we've measured. The speed of light is woven into the fabric of reality itself. It's not a speed at all. Not really. It's something else entirely. And once you see what it actually is, your understanding of the universe will never be the same. Let me start with something that will sound insane. The speed of light is the same for everyone. No matter how fast you're moving, no matter what direction you're going, no matter what. You could be standing still. You could be flying through space at 99% the speed of light. Doesn't matter. If you measure the speed of light, you always get the same number. Always. This is not obvious. This is not intuitive. This is completely insane. Think about it. Imagine you're standing on the side of a road, and a car drives past you at 60 miles per hour. Now imagine you're in your own car driving at 50 miles per hour in the same direction. How fast is that other car moving relative to you? 10 miles per hour, right? You subtract the speeds. That's how motion works. That's how everything in your daily life works. Velocities add and subtract. If you're moving toward something, it appears faster. If you're moving away, it appears slower. This is common sense. But light doesn't do this. Light breaks this rule completely. If you're standing still and you measure a beam of light, it's going 186,000 miles per second. If you're flying toward that same beam at 100,000 miles per second, you measure it again. What speed do you get? Still 186,000 miles per second. Not faster, not 286,000, the same, exactly the same. If you're flying away from the light at 100,000 miles per second, you measure it again. Still 186,000 miles per second. Not slower, the same. This is not a measurement error. This is not an illusion. This is reality. Light moves at the same speed relative to everyone, no matter how fast they're moving. And this fact, this one weird fact, breaks everything. It shatters all your intuitions about space and time and motion. Because if light always moves at the same speed, then something else has to give. Something has to be flexible. And what gives is space and time themselves. Here's what Feynman realized. Here's the key insight that changes everything. The speed of light isn't really about light. It's about the structure of space-time. It's about the relationship between space and time, between distance and duration. The speed of light is the conversion factor. It's the exchange rate between space and time. Let me explain what that means. You think of space and time as separate things. You think of space as the place where things are, and time as the thing that flows forward, second by second. But they're not separate. They're woven together. Einstein showed us this. Space and time are part of one unified thing called space-time, and the speed of light is the number that connects them. It tells you how much space equals how much time. Here's an analogy. Think about currency exchange. $1 and €1 are different, but they're connected by an exchange rate. You can convert dollars to euros and back. The exchange rate tells you how many of one equals how many of the other. The speed of light is like that. It's the exchange rate between space and time. It tells you how many meters of space equal how many seconds of time. And here's the crazy part. That exchange rate is built into the universe. It's not arbitrary. It's not something that could be different. It's a fundamental constant woven into the fabric of reality itself. Space and time are not separate currencies. They're two ways of measuring the same unified thing, space-time, and the speed of light is the number that relates them. Now watch this. If space and time are connected, if they're part of one thing, then when you move through space, you're also moving through time. Always. You're always moving through space-time at the same rate. Always. Every object in the universe, every particle, every person is moving through space-time at exactly the speed of light. Right now. You, me, everyone. We're all moving through space-time at light speed. Wait, what? How can that be? You're sitting still right now. You're not moving through space at light speed? That's true. You're not moving through space. You're moving through time. You're sitting still in space, so all your motion through space-time is directed along the time axis. You're moving through time at the maximum rate, which happens to be the speed of light. Here's the picture. Imagine space-time as a combination of two directions, space and time. Every object has a velocity through space-time, and that velocity is always the same magnitude, the speed of light, always. But you can point that velocity in different directions. You can point it all toward time, which means you're sitting still in space. Or you can point some of it toward space and some toward time, which means you're moving through space, but more slowly through time. The total always adds up to the speed of light. This is why nothing can go faster than light through space. Because if you're going at light speed through space, then all your motion through space-time is directed along the space axis. There's none left for time. You're using up all your motion budget on space, and since the total velocity through space-time is fixed, you can't go any faster. The speed of light isn't a speed limit, it's the speed. It's the only speed anything ever moves through space-time. Let me say that again because it's the most important thing. You're always moving through space-time at the speed of light. When you're sitting still, you're moving through time at light speed. When you're moving through space, you're diverting some of that motion from time into space. The faster you go through space, the slower you go through time, and the limit is reached when all your motion is through space and none through time. That's the speed of light. This is why time dilation happens. This is why clocks slow down when they move. It's not some weird effect. It's not magic. It's just geometry. When you move through space, you're tilting your velocity vector in space-time. You're pointing less of it toward time and more toward space, so you experience less time. Your clock ticks slower. Not because motion affects clocks, but because motion is literally movement through space-time in a different direction. Feynman understood this deeply. He had this incredible ability to see through the mathematics to the physical picture underneath. And what he saw was that the speed of light isn't really about light at all. Light just happens to be the thing that moves at this speed because light has no mass. Massless particles always move at the speed of light through space because they can't move through time. They have to put all their space-time motion into space. That's what it means to be massless. Massive particles like you and me, we move through time. We have to. Because we have mass, we can't put all our motion into space. Some of it has to be directed toward time. And the more mass you have, the more locked into time you are, the harder it is to redirect your motion toward space. Now here's where it gets really interesting. You know that famous equation, E equals mc squared? Energy equals mass times the speed of light squared. That equation is telling you something profound. It's telling you that mass and energy are the same thing. They're interchangeable. And the conversion factor between them is the speed of light squared. Again, the speed of light shows up as the fundamental conversion factor. But why squared? Why c squared? Here's why. The speed of light is the exchange rate between space and time, between distance and duration. But energy is about motion through space and time. It's about momentum and change. So when you convert between mass and energy, you need to account for both space and time. You need the speed of light twice. Once for space, once for time. That's why it's squared. E equals mc squared is telling you that mass is frozen energy. It's energy that's not moving through space, energy that's just sitting there moving through time. And when you want to release that energy, when you want to convert it into motion, you multiply by c squared. You use the speed of light as the conversion factor, twice. This is why nuclear weapons are so powerful. This is why the sun shines. Because when you convert even a tiny amount of mass into energy, you multiply by a huge number. The speed of light is big. The speed of light squared is enormous. A single kilogram of mass, if you could convert it completely to energy, would release 90 quadrillion joules. That's the energy of 21 megatons of TNT, from 1 kilogram, because c squared is that big. But let's get back to the speed limit. Because now you might be wondering, okay, I understand that the speed of light is fundamental, that it's woven into space-time, but why can't we break it? What actually happens if you try to go faster? Here's what happens. You can't. Not you can't because it's too hard. You can't because it's incoherent. It's like asking what's north of the North Pole. The question doesn't make sense. Let me explain. Remember, you're always moving through space-time at the speed of light. Always. That's fixed. That's not changeable. Now, when you accelerate, what you're doing is changing the direction of your motion through space-time. You're tilting your velocity vector. You're pointing more toward space, less toward time. But there's a limit to how much you can tilt. The limit is reached when you're moving entirely through space and not through time at all. That's the speed of light. Can you tilt past that? Can you point your vector beyond the space axis? No, because then you'd be moving backward through time, And that's not how causality works. The universe doesn't allow backward time motion for massive objects. The structure of space-time itself prevents it. But wait, you might say. What if I just keep accelerating? What if I keep pushing? I have a rocket, I have fuel, I keep firing the engines. Don't I keep speeding up? Yes, you do. But here's the catch. As you approach the speed of light, your mass increases. From the perspective of an outside observer, you get heavier and heavier. It takes more and more energy to accelerate you further. And as you approach light speed, your mass approaches infinity. This is not a practical problem. This is not an engineering challenge. This is a fundamental feature of reality. As you go faster, your energy goes into increasing your mass more than your speed. You can pump infinite energy into acceleration, and you'll never quite reach light speed, because all that energy keeps making you heavier, and heavier things are harder to accelerate. From your perspective inside the rocket, it feels different. You don't feel heavier. You just notice that the universe outside seems different. Distances contract. Time dilates. The stars ahead of you shift color. But you never feel like you're approaching a barrier. You never feel like you're hitting a wall. You just keep accelerating and the universe keeps changing around you. And you never quite reach that limit where you're moving entirely through space. Feynman had a beautiful way of explaining this. He said, "Imagine you're walking north. You can walk north as much as you want. But you can never reach the point where north stops making sense. You can walk to the North Pole, but even there, north still has meaning. It's the direction you were walking. The speed of light is like that. It's not a wall you hit. It's the limiting case of a process that never completes. You can approach it. You can get closer and closer. But you never arrive because arriving would mean leaving space-time entirely." Now let's talk about something most people get confused about. They ask, if nothing can go faster than light, how did the universe expand faster than light during the Big Bang? How can distant galaxies be moving away from us faster than light? Doesn't that break the rule? No, because the rule isn't about space expanding. The rule is about objects moving through space. Space itself can expand as fast as it wants. There's no speed limit on the expansion of space because space isn't moving through space-time. Space is space-time. Think about it this way. Imagine you draw two dots on a balloon. Now inflate the balloon. The dots move apart. But are the dots moving across the surface of the balloon? No. The surface itself is expanding. The dots are just being carried along. They're not moving through space. Space is expanding between them. That's what's happening with the universe. Distant galaxies aren't moving through space faster than light. Space itself is expanding between us and them. And space can expand at any rate. There's no limit. The speed of light limits motion through space, not the expansion of space itself. This is subtle. This confuses even smart people. But Feynman would have loved this distinction. He would have drawn a little diagram, shown you the difference, made it click in your mind. Because the key to understanding physics is knowing what categories things belong to. Galaxies moving through space? Speed limit applies. Space expanding? No limit. Here's another question people ask. Why is the speed of light this particular number? Why 186,000 miles per second and not something else? Why not 1,000,000 miles per second? Why not 1,000,000,000? And here's the answer. The number is arbitrary. It depends on what units you're using. Miles, meters, seconds, these are human inventions. If you measured in different units, you'd get a different number. What matters is not the number. What matters is the ratio, the relationship between space and time. In fact, physicists often use units where the speed of light is just 1, not 186,000, not 300 million, just 1. In these units, 1 second of time equals 1 light second of distance. Space and time have the same units. They're measured the same way, because they're the same thing, and the speed of light becomes just a conversion factor, like saying 1 foot equals 12 inches. It's not about the numbers, It's about the relationship. Feynman often worked in these units. He called them natural units. And in natural units, the speed of light is 1, and E equals mc squared becomes just E equals m. Energy equals mass. Period. No conversion factor needed because energy and mass are already in the same units. Because fundamentally they're the same thing. This reveals something profound. The speed of light isn't a property of light. It's a property of space-time itself. It's the fundamental exchange rate built into reality. And light just happens to travel at this speed because light is massless, because photons don't experience time, because they put all their motion through space-time into spatial motion. Now watch this. Everything I've told you so far leads to something even stranger. Something Feynman spent years thinking about. If the speed of light is the maximum, if nothing can go faster, then how does causality work? How do causes lead to effects? How does information propagate? Here's the answer. Causality propagates at the speed of light. Not faster, not slower. Exactly at the speed of light. When something happens here, it takes time for that event to affect things over there, and the time it takes is exactly the time it takes for light to travel that distance. The universe has a built-in delay, a speed limit on cause and effect itself. This is why relativity preserves causality. This is why you can't send information backward in time, because if you could move faster than light, you could create situations where effects precede causes, where you receive a message before it's sent, where you shoot your own grandfather. The speed limit protects the logical structure of reality. Feynman worked this out in detail. He showed that the equations of physics, the fundamental equations describing how particles interact, all respect this speed limit. Not because we built it in, but because the mathematics demands it. If you try to write down equations where causes can propagate faster than light, you get nonsense. You get contradictions. The universe doesn't allow it. Here's the deep part. The speed of light limit isn't a law we discovered. It's a consequence of the structure of space-time itself. It emerges from the mathematics of special relativity, from the requirement that physics be the same for everyone, regardless of how fast they're moving, from the insistence that causality be preserved. Einstein figured this out in 1905. He started with 2 simple postulates. First, the laws of physics are the same for everyone. Second, the speed of light is the same for everyone. From just these 2 ideas, he derived all of special relativity. Time dilation, length contraction, mass-energy equivalence, the speed limit. All of it, just from those 2 assumptions. And Feynman took it further. He showed how quantum mechanics fits into this picture. He developed quantum field theory, which describes how particles interact while respecting the speed limit. He invented Feynman diagrams, little pictures that show particles exchanging force carriers, photons and gluons and bosons, all propagating at or below the speed of light. Every interaction, every force, every cause and effect in the universe happens through particles moving at or below light speed. Gravity propagates at light speed. Electromagnetic forces propagate at light speed. The strong and weak nuclear forces propagate at light speed. Everything respects the limit, because the limit is built into the fabric of reality. But here's something that will really bend your mind. From a photon's perspective, from light's perspective, time doesn't pass at all. A photon emitted from a star 1 billion light years away, from its own perspective, arrives at your eye instantly. 0 time elapsed. Because the photon is moving at light speed through space, it's not moving through time at all. For the photon, departure and arrival are the same moment. This is what it means to move at the speed of light. You don't experience time. The entire history of the universe, from your perspective, happens in an instant. You exist in a timeless state, frozen at the moment of creation and destruction simultaneously. We can't experience this. We have mass. We move through time. We're locked into causality. But light, massless light, Experience is something completely outside our understanding, a state where time doesn't exist, where past and future collapse into a single moment. Feynman thought deeply about this. He wondered what it would be like to be a photon, and he realized you can't even ask the question coherently. A photon doesn't have a perspective. It doesn't have experiences. It doesn't have a reference frame in the usual sense. The mathematics breaks down. You can't do relativity from the photon's point of view because there is no photon's point of view. Time doesn't exist for photons, and without time, there's no experience, no perspective, no what it's like. This brings us to something crucial, something most people miss. The speed limit isn't about speed, it's about structure. It's about the geometry of space-time. It's about the relationship between cause and effect, between past and future, between what's possible and what's not. When you move faster through space, you move slower through time. When you move at maximum speed through space, you don't move through time at all. That's the limit. Not because you hit a wall, but because you've rotated your motion entirely into the spatial dimension. There's no more time direction to rotate into. You've used it all up. This is why you can't go faster. Not because of engineering, not because of power, but because going faster would mean moving backward through time. And backward time motion would break causality, would allow effects before causes, would create logical contradictions. And the universe doesn't allow logical contradictions. Reality is consistent with itself. Feynman once said, "Nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry." The speed of light is one of those threads. It weaves through everything. Relativity, quantum mechanics, causality, the structure of space-time itself. Pull on it and the whole tapestry reveals itself. You can't go faster than light because light speed isn't a speed. It's the shape of reality. It's the rate at which space-time itself flows. It's the fundamental conversion factor between space and time, between energy and mass, between cause and effect. You can't break it because you can't break mathematics. You can't break geometry. You can't break the logical structure of existence itself. And here's what makes this beautiful. Here's what Feynman loved about physics. We figured this out. Humans, tiny creatures on a tiny planet. We looked at the stars. We measured the speed of light. We noticed it never changes. And from that one weird fact, we unraveled the structure of space-time. We discovered that space and time are unified. That mass and energy are equivalent. That motion has a maximum not because of barriers, but because of geometry. We did this with mathematics, with careful experiments, with thought experiments and equations and an unwavering commitment to following logic wherever it leads. We can't go faster than light, but we can understand why. We can see the shape of the constraint. We can grasp the deep structure underneath. That's what physics is. Not just collecting facts, not just measuring numbers, but understanding the patterns, seeing how everything fits together, recognizing that the universe is mathematical, logical, consistent with itself. And we, made of atoms, animated by electrical impulses, we can comprehend it. Feynman spent his life teaching this. Not just the equations, but the understanding, the intuition, the sense of wonder that comes from seeing reality clearly. He knew that physics isn't about memorizing formulas. It's about seeing the world as it actually is, strange and beautiful and governed by principles we can understand. The speed of light has a limit because space-time is unified, because motion through space is rotation through space-time, because time and space trade off against each other, because causality must be preserved, because reality is consistent. And you, right now, are moving through space-time at the speed of light. All your motion directed through time because you're sitting still in space. Every second that passes is you traveling 1 light second through time. You're moving at the cosmic speed limit right now. You've been doing it your whole life. You just never realized it. That's the truth. That's what Feynman found. That's what will collapse your mind if you think about it deeply enough. Not that there's a speed limit, but that speed itself is an illusion. What's real is motion through space-time, and that motion has one rate. Always. For everyone. For everything. The speed of light isn't the maximum speed through space. It's the only speed through space-time, and we're all traveling it. Right now. Forever. Space and time are one. Motion and rest are relative. The speed limit is geometry. And reality is stranger and deeper and more beautiful than anyone imagined until Einstein and Feynman showed us the truth. The universe doesn't have a speed limit because someone posted a sign. The universe has a speed limit because of what the universe is. Space-time. Unified, consistent, mathematical, real. And we figured it out. That's the real miracle. That consciousness can understand the framework it's embedded in. That thought can grasp the structure of reality. That humans can know why speed has a limit and what that limit means and how it shapes everything we are and everything we'll ever be. That's physics. That's what Feynman gave us. Not just knowledge, but understanding. Deep, clear, beautiful understanding of the way things actually are. The speed of light isn't fast. The speed of light is the conversion factor between space and time, between energy and mass, between cause and effect. It's woven into reality itself. And nothing can exceed it. Not because of force, but because of logic, because of geometry, because of the structure of existence itself. That's the answer. That's the truth. That's what will collapse your mind if you let it. Speed has a limit because space-time is what it is. And what it is unified, consistent, and knowable. Feynman knew it. Einstein knew it. And now you know it too. There's a clock on my desk that hasn't worked in years. The second hand is frozen at the 14-second mark. And every time I glance at it, which is often because I forget it's broken, I get this tiny jolt of confusion. My brain expects movement. It expects time to be doing its thing. But the clock just refuses. Now here's what interests me. That broken clock is telling the correct time twice a day. At exactly 3 minutes and 14 seconds, it's perfect. The rest of the day? Total liar. But here's the thing that keeps me up at night. Maybe time itself is the broken clock. Maybe it's not moving at all, and we're the ones who are confused, expecting something that was never really there. What if time doesn't exist the way you think it does? What if you've been living your whole life according to a clock that's fundamentally broken? I know that sounds crazy. You're probably thinking, come on, Feynman, of course time exists. I can feel it passing right now. I'm getting older. My kids are growing up. The sun rises and sets. And you're right. You do experience all those things. But experiencing something and understanding what it actually is are two very different things. You experience the sun rising every morning, but you know the sun isn't actually moving. You are, spinning on a planet hurtling through space. Your experience and the reality underneath it don't always match up. And that's what we're going to talk about today. Not just what time feels like, but what it actually is. And more importantly, why it exists at all. Because once you understand that, really understand it, not just intellectually but in your bones, everything changes. The way you experience your life, the way you think about your past and your future, the anxiety you carry about running out of time, the regret you hold about wasting it, all of it shifts. And I don't mean that in some fluffy, inspirational way. I mean it literally. The physics of time, when you really get it, is more liberating than any self-help book you've ever read. So here's what I want to do with our time together. First, I'm going to show you what time actually is, according to the best physics we have. Not the simplified version you learned in school, but the real thing, explained clearly enough that you'll actually understand it. Second, I'm going to help you see why you feel time the way you do, and why that feeling, as powerful as it is, misleads you about the nature of reality. And third, I'm going to give you some practical ways to live with this understanding, not just to know it, but to actually use it to reduce your suffering and increase your sense of freedom. Because here's the thing, most people get completely wrong about time. They think it's a river carrying them forward, and their job is to swim faster, pack more experiences in, optimize every single minute of every single day. That's exhausting. And worse, it's based on a fundamental misunderstanding of what time is. The truth that physics reveals is far stranger and, honestly, far more beautiful than that. Time isn't a thing that happens to you. It's a relationship between things, including you. You're not trapped in time's current. You're part of the structure itself. And once you see that clearly, the whole game changes. The anxiety about wasting time starts to dissolve. The fear of death doesn't go away. I'm not going to lie to you and say physics makes you immortal, but it softens into something more manageable, something you can hold without it crushing you. The constant pressure to always be productive, to always be making the most of your time, loses its grip on you, because you realize that the premise was flawed from the beginning. So that's what we're doing here. This isn't philosophy, though we'll touch on it. This isn't self-help, though you might feel helped. This is physics, real, rigorous, mathematical physics, applied to the one question that actually matters to you as a living, breathing, worried human being. How should I live? What does the nature of time tell me about how to be alive? Let me start with a story. Actually, let me start with a thought experiment, because that's how I like to think about these things. Picture yourself standing on a train platform. You're waiting for your train, you're bored, maybe you're checking your watch, wondering why trains are never on time. And then another train, not yours, comes blasting through the station at high speed. It doesn't stop, just rushes past in a blur of metal and motion and that distinctive sound trains make when they're really moving. As it passes, you glance through one of the windows and you see someone sitting there, perfectly calm, reading a book. They're not gripping the armrests, they're not bracing themselves against the speed. From their perspective, they're just sitting still, enjoying their book, while the world rushes past outside. Now here's the question that matters. Who's moving? You'd say the train, obviously. You're standing still on the platform. The train is the thing in motion. But here's the thing that'll start to crack open your understanding of reality. From the perspective of that person reading the book, you're the one moving. They're sitting peacefully in their seat, and you and the entire platform and everyone on it are rushing past them in the opposite direction. And here's the part that really matters. You're both right. There's no objective answer to who's moving. Motion is relative. It depends entirely on your frame of reference. There's no privileged position in the universe where you can stand and say, this is true motion, this is true stillness. It's all relative to something else. Now, you might think, okay, fine, motion is relative. I learned that in school, so what? Here's the so what. If motion is relative and time is intimately connected to motion, which it is, in ways we're going to explore, then time must be relative too. And that completely destroys the picture of time you've been carrying around in your head your whole life. You think time is flowing forward, carrying you from past to future at a steady, universal rate. That feels as obvious as the ground beneath your feet. But what if time, like motion, is relative? What if now isn't a universal moment that everyone in the universe shares, but something that depends on where you are and how fast you're moving? This isn't speculation. This isn't philosophy. Einstein proved this more than 100 years ago. If you're moving fast enough relative to me, your now is literally different from mine. The thing you think is happening right now on a distant star, say Alpha Centauri, our nearest neighbor, already happened from my perspective. Or it hasn't happened yet. It depends on whether you're moving toward that star or away from it and how fast. Think about what this means. When you say right now, You're not describing an objective feature of the universe. You're describing your personal, local experience in your specific frame of reference. There is no universal now. There's no cosmic present moment that ties everything together. Your now is yours, mine is mine, and they only approximately overlap because we're both sitting relatively still compared to the speed of light. So when you say, I don't have enough time, what you really mean is, I don't have enough my time as I experience it, in my body, moving at my speed through space. But time itself? It's not running out. It's not even flowing. It just is, laid out like a landscape, and you're moving through it, experiencing it sequentially, moment by moment. And that panic you feel, that scarcity mindset about time, it's real. I'm not dismissing it. But it's about your experience, not about some objective truth of the universe. The universe doesn't care that you feel rushed. The universe isn't counting down. You are. And there's a big difference between those two things. Which raises the obvious question, if time isn't what I think it is, what is it? And why do I experience it so powerfully if it's not some objective feature of reality? Let me tell you another story. Imagine you're reading a novel. A really good one, the kind you can't put down. You're on page 157. The main character just made a terrible decision. You can see the disaster coming, but they can't, and you're reading as fast as you can because you need to know what happens next. Your heart's actually racing. You're emotionally invested in this character, in what's going to happen to them. But here's the thing that's obvious but easy to forget when you're caught up in the story. The book already exists in its entirety. Page 158 is already written. Page 200, page 350, the ending where everything either comes together or falls apart. It's all already there, bound together between the covers. You're just reading it in sequence, one page at a time. Now, the character in the story doesn't know this. From their perspective, the future is genuinely uncertain. They're making choices, facing consequences, not knowing how it'll turn out. Their experience is of genuine openness, genuine possibility. The past is fixed. Those things already happened to them. The future is unknown. And they're living in this knife-edge present, this now where anything could happen. But from your perspective as the reader, their entire life is already complete. Their whole story, from birth to death, exists simultaneously in the book. Their now is just wherever you happen to be reading at this particular moment. And if you flip ahead, which you might do even though it feels like cheating, you can see their future. You can know how it ends while they're still struggling through the middle. This is called the block universe model, and it's what a lot of modern physics points toward. The idea is that past, present, and future all exist simultaneously, like pages in a book or frames in a film. The flow of time, that powerful feeling you have of moving from past to future, is just you experiencing the pages in order. But the pages themselves? They're all already there. They exist together, eternally, in what physicists call the block of space-time. Now, I can feel you resisting this. You're thinking, no, that can't be right. The future doesn't exist yet. It hasn't happened. It's open, it's uncertain, it's full of possibilities. And I understand that resistance because I feel it too. It goes against every fiber of our lived experience. We feel like we're creating the future with our choices, not just reading a script that's already written. But here's what I want you to sit with, even though it's uncomfortable. Maybe both things are true. Maybe the book is already written, and your reading of it is still genuine. Maybe the future exists in the block of space-time, complete and unchangeable, and your experience of choosing and creating is still real. Think about watching a movie you've already seen. You know how it ends. You know the character is about to make a mistake. You know who dies. You know whether they get the happy ending. But you still feel the emotions, don't you? You still cry at the sad parts. You still laugh at the jokes. You still feel tension during the scary scenes, even though you know everything turns out okay in the end. The emotional journey is real, even though the outcome is fixed. Your experience of the movie matters even though the film itself doesn't change, based on how you feel about it. The story affects you even though you can't affect the story. Maybe that's what life is like. Maybe your entire timeline, from the moment you were born to the moment you'll die, exists as a complete structure in the block universe, unchangeable and eternal. And maybe your experience of living through it, moment by moment, feeling like you're making real choices and creating real outcomes, is also completely real. Those two things might not be contradictory. They might just be different perspectives on the same reality. From outside, looking at the whole structure, your life is complete. From inside, living through it, your life is unfolding. Both are true. Both matter. And here's why this matters for how you actually live. If you can hold both perspectives at once, something shifts in your relationship to anxiety and control. Because the part of you that's desperately trying to control the future, to make sure everything turns out okay, to avoid all the bad things you're afraid of, that part can relax a little. Because the future is already what it is. The book is already written. You're going to read the pages you're going to read. But that doesn't make you passive. That doesn't mean nothing matters. Because the you that exists in the structure, the you that's written into the story, that you is acting, choosing, feeling, living, the character in the novel doesn't stop being a character just because the book is complete. In fact, they're only a character because the whole story exists. Without the structure, without the complete arc from beginning to end, there's no story at all. So maybe time's existence isn't about flow or freedom or control. Maybe it's about structure. The structure that lets you have experiences at all. Without time, there's no story, no arc, no journey from ignorance to understanding, from loneliness to connection, from fear to courage. Time exists so that you can have a narrative, so that your life can mean something, so that one moment can lead to another, and that sequence can add up to something we call a self, a person, a life. But if time is just structure, why does it feel like it's slipping away? Why do you experience it as loss? Why does every birthday feel like theft? Every ended relationship like proof that you're running out of chances, every year that passes like evidence that you're wasting your one precious life? That's the question we need to answer, because the feeling is so powerful. It dominates your experience. Even if I've convinced you intellectually that time isn't what you thought it was, you still feel it as scarcity, as pressure, as countdown. So where does that feeling come from? Let me try to explain this as clearly as I can. Time is not a thing. I know that sounds weird because we talk about it like it's a thing all the time. We say, I don't have time, as if time is something you could possess or run out of, like water in a cup. We say time flies or time drags, as if time is an object with variable speed. We even imagine it visually, as a river flowing or an arrow shooting forward. But time isn't a thing. It's a measurement. Specifically, it's a way of measuring change. And that's the key to understanding everything else. Think about how you know time has passed. How do you actually know? You look at a clock, and the hands have moved. The sun has crossed the sky. Your stomach has gone from full to empty. A thought arose in your mind and then dissolved. Something changed. That's the only way you ever know time has passed, because you observe that something is different now than it was before. Now here's the crucial question. If nothing changed, and I mean nothing, not a single atom in the entire universe moved or vibrated or decayed, would time still be passing? How would you know? From what perspective could you even measure it? You couldn't. Time only exists as a measure of change. It's not a container that events happen inside of. It's not a river that carries events along. It's the pattern of events themselves, the relationship between one state of the universe and another state of the universe. Without change, the concept of time becomes meaningless. Here's a thought experiment that might make this clearer. Imagine you're in a pitch-black room. You can't see anything. And let's say, somehow, magically, your body has been frozen in such a way that you have no sensations, no heartbeat, no breathing, no thoughts arising and passing. You're just suspended, aware somehow, but experiencing absolutely nothing changing. How long are you in that room? Is it a second? An hour? A year? From your perspective, there's no way to tell. Without any change, internal or external, there's no way to mark one moment as different from another. And if moments aren't different, if there's no way to distinguish now from then, does time even exist for you in that scenario? I'd argue it doesn't. Time requires change. It is change, measured and quantified. And this is why meditation works, by the way. When you sit in meditation and quiet your mind, when you reduce the constant stream of thoughts and sensations, time seems to slow down or even stop. You're not actually stopping time. You're reducing the number of changes you're aware of. And since time is just change measured, fewer changes equals less experienced time. This is also why time seems to speed up as you get older. When you're a child, everything is new. Every day contains thousands of novel experiences, new sensations, new learnings. Your brain is encoding change constantly. So subjectively, time feels long because you're experiencing so much change. But as you age, you fall into routines. You've seen it all before. Your brain starts to filter out the repetitive stuff, stops encoding it as carefully. Less perceived change equals faster feeling time. So when you feel like you're running out of time, what you're actually running out of is change capacity. You're worried you won't get to experience all the changes you want. Falling in love again, building something meaningful, seeing your children grow up, learning that skill you've been putting off, traveling to that place you've always dreamed about. That's a real fear. But it's not about time disappearing into the void. It's about you wanting more experiences, more changes, more richness than your biological lifespan allows. And that's a different kind of problem. That's about values, about what you prioritize, about how you choose to spend your limited change capacity. It's not about time itself being scarce. Time just is. Change just happens. The question is, what changes do you want to be part of? What patterns do you want your piece of the universe to make? Now let me tell you about something called the arrow of time, because this is where it gets really interesting and really weird. If time is just a measurement of change, why does it only go in one direction? Why can you remember the past but not the future? Why do eggs scramble but never unscramble? Why does a glass shatter into pieces, but those pieces never spontaneously reassemble into a glass? This is one of the deepest mysteries in physics, and the answer is going to surprise you. Here's the weird part. The fundamental laws of physics, the equations that govern how particles interact, how forces work, how energy moves through the universe, are reversible. If you filmed a particle interaction at the quantum level and played the film backward, it would still obey the laws of physics. There's nothing in the basic equations that says time has to flow forward. And yet, obviously in everyday life, time has a direction. You age, you don't unage. Buildings crumble, they don't uncrumble. The universe expands, it doesn't contract. Well, not yet, anyway. There's a clear arrow pointing from past to future, from ordered to disordered, from low entropy to high entropy. Entropy. That's the key word. It's a measure of disorder, of randomness, of how many different ways you can arrange things. And the universe tends toward higher entropy over time, not because there's some law forcing it to, but because, and this is beautiful, there are just way more disordered arrangements than ordered ones. Let me give you an example. Imagine you have a deck of cards in perfect order, all the spades together, ace through king, then hearts, diamonds, clubs, perfectly sorted. That's one specific arrangement. Now you shuffle the deck. What are the odds it ends up in that same perfect order again? Astronomically low. Why? Because there's only one perfectly ordered arrangement, but there are billions and billions of disordered arrangements. The vast majority of possible arrangements are not that perfect sequence, so when you shuffle, you're almost certainly moving from a rare, ordered state to a common, disordered state. Not because disorder is trying to happen, but because disorder is just statistically way more likely. There are more ways to be disordered than to be ordered, so disorder is what you tend to get. That's entropy. That's why scrambled eggs don't unscramble, not because it's impossible, the laws of physics don't forbid it, but because the odds of all those molecules happening to move in exactly the right way to separate the yolk from the white, again, are so spectacularly low that you could wait longer than the age of the universe and never see it happen. And that's why time has an arrow. The universe is constantly moving from less probable configurations to more probable configurations, from order to disorder, from low entropy to high entropy. And we experience that directionality as the passage of time, as the movement from past to future. Here's the emotional truth of this. You can't go back. You can't undo. The mistakes you made, the relationships you ruined, the time you feel you wasted, the person you were before the trauma or the loss or the betrayal, those are in the past, locked into high entropy states that you can't reverse. The deck is shuffled, the glass is shattered, the egg is scrambled. And that's painful. That might be one of the most painful aspects of being human, the irreversibility of time. You can't get a do-over. You can't rewind. You can't go back to that moment before everything changed and choose differently. But here's the thing. That's also liberating, because it means you don't have to carry the burden of somehow fixing the past. You can't unbreak the glass, no matter how desperately you want to, no matter how much you regret breaking it in the first place. It's done. The entropy has increased. The state has changed. Your job isn't to reverse it. Your job isn't to somehow reconstruct what was. Your job is to be here, now, in this current state, and to decide what to do with the pieces. Maybe you sweep them up and throw them away. Maybe you make a mosaic. Maybe you leave them on the floor as a reminder. But you don't spend your energy trying to unshatter the glass, because physics itself tells you that's not how time works. The arrow points forward, always. Now let me blow your mind a little more. I told you that time is relative, that your now isn't universal. Let me explain what that actually means, because it's stranger than you think. Right now, as you're listening to me, you experience this moment as the present. It feels immediate, happening now, while the past is gone and the future hasn't arrived yet. And if I asked you whether some event on a distant star, say a supernova on Alpha Centauri, is happening now or in the past or in the future, you'd think there's a definite answer to that question. Either it's happened already, or it's happening now, or it will happen later. Right? Wrong. According to relativity, the answer depends on how you're moving. If you're sitting still relative to me, we might agree about which events are simultaneous with our current moment. But if you start moving, say if you get on a spaceship and accelerate toward Alpha Centauri, events that were in your future suddenly shift into your present. And if you turn around and accelerate away from it, those same events shift back into your future. The speed and direction of your motion through space literally changes which events you consider to be happening now. Your now is not a universal slice through the universe. It's a personal, local, motion-dependent thing. This is called the relativity of simultaneity, and it completely destroys the idea of a universal present moment. There's no cosmic now that everyone shares. Your now is yours. Mine is mine. They overlap approximately because we're moving slowly relative to each other, but they're not the same thing. And for someone moving near the speed of light relative to us, their now could include events that are in our distant past or distant future. Think about what this means for your life. When you say, I need to be present, you're really saying, I need to pay attention to my now, my specific, local, personal experience of this moment, in this body, moving at this speed through space-time. You can't be present for the whole universe. You can't experience everyone else's now. You only have access to your own. And that's not a limitation. That's the entire structure of reality. Your now is your access point to existence. It's the only place you can ever be. So stop trying to live in some imagined universal present, some objective now that doesn't exist. Just be here in your own weird, local, specific, motion-dependent slice of space-time. That's all you've got. And it's enough. So we've established that time isn't what you thought it was. It's not a river, not a container, not a thing at all. It's a measurement of change, it has a direction because of entropy, and it's relative to your motion through space. But none of that answers the big question. Why does time exist at all? Why is there this dimension, this structure, this framework for change? Why not just have a static universe where everything exists but nothing happens? And here's my answer. Because without time, nothing could happen. There'd be no change, no cause and effect, no relationships, no experiences, no consciousness. The universe would be a frozen block of existence. Everything present all at once, but nothing moving, nothing interacting, nothing becoming. Time is the dimension that allows for process. It's the axis along which things unfold, where causes lead to effects, where potential becomes actual, where stories have beginnings, middles, and ends. Space gives you the where, the layout, the positions, the distances between things. Time gives you the when, the sequencing, the ordering, the unfolding. And together they give you the what, actual events, actual experiences, actual existence. Think of it like this. Imagine a vinyl record. If you just look at the record sitting on a table, it's a flat disc with grooves. The grooves contain all the information. The entire song is encoded there, complete and whole. But until you put it on a turntable and let the needle move through the grooves in sequence, you don't get music. You get a static object with potential. Time is like the needle moving through the grooves. It's what transforms potential into actual experience. The grooves, the structure, are always there, complete and unchanging. But the music only exists as you move through them, as you experience them sequentially, moment by moment. And that's what time does for the universe. It transforms the static structure of space-time, the complete, eternal block universe, where everything exists at once, into lived experience. It lets you have a journey. It lets there be a story. It lets one moment lead to another, and that sequence means something. So when you ask, why does time exist at all? The answer is, so you can exist. Not you as a static object, a frozen sculpture, a point in space, but you as a process, you as a story, you as someone who changes and grows and makes mistakes and learns from them and loves and loses and loves again. Time is the gift that makes experience possible. And yes, it also makes loss possible, and aging, and death, and regret. You don't get to cherry-pick. If you want the joy of watching your child take their first steps, you get the grief of watching them leave home. If you want the growth that comes from overcoming challenges, you get the decay that comes from entropy. If you want the love, you risk the heartbreak. That's the deal. That's what time gives you. Not unlimited chances, not eternal youth, not the ability to hold on to the good moments forever. It gives you change. It gives you process. It gives you the possibility of meaning, because meaning requires sequence, requires before and after, requires cause and effect. And maybe that's okay. Maybe once you really understand that trade-off, you stop resenting time. You stop treating it like an enemy, like something stealing your happiness. You start seeing it as the very condition of happiness, the structure that makes any kind of meaningful experience possible at all. But here's the thing I really want you to get, the thing that changed my relationship to my own existence. You are not a thing that exists in time, like a boat floating on a river. You are time. You're made of time. Your consciousness, your identity, your sense of self, they're all temporal structures, patterns of change unfolding across the dimension of time. Think about what you means. You point to your body and say, "This is me." But which version of your body? The body you had as a child? That's gone. Those cells have been replaced. The body you have now? It's already changing, already becoming the body you'll have tomorrow. The body you'll have when you're old? That doesn't exist yet. So, you isn't really a physical object. It's a continuity, a thread, a pattern that persists through change. It's the story that connects the child you were to the adult you are to the elder you'll become. It's memory linking moments together, creating the illusion of a single, solid, continuous self. But each of those moments is gone. The child you were doesn't exist anymore except as a memory, as information encoded in your current brain structure. And the person you'll be tomorrow doesn't exist yet. The you that feels so solid, so real, so permanent, that's actually just a pattern of change unfolding in time. You are not in time. You are made of time. You are a temporal pattern, a four-dimensional structure stretching from your birth to your death, and the you that you experience at any given moment is just one cross-section of that larger structure. Here's the paradox. This should be terrifying. If you're just a pattern of change, if there's no solid, unchanging you at the core, if you're just a process unfolding in time, then who are you, really? What happens when the process ends? Where do you go when time stops changing your particular pattern? But here's the flip side, the freedom that comes with this understanding. If you are time, if you are change itself, then you can't escape it and you don't need to fight it. You stop trying to freeze the good moments, to make them permanent. You stop trying to rush through the hard moments, to skip to the good parts. Because you understand that the moments aren't things happening to you. They are you. They're the substance of your existence. You are the journey, not the traveler. You are the music, not the listener. You are the change itself. And once you accept that, really accept it, not just intellectually but in your body, the fear starts to lessen. Because you stop fighting against your own nature. You stop treating time like an enemy that's trying to steal your life. And you start recognizing that time is your life. It's not the container you exist in. It's what you're made of. Let me give you some practical ways to work with this understanding. Because I don't want this to just be an interesting intellectual exercise. I want it to change how you actually live. First, for the next week, I want you to stop checking the clock obsessively. I know that's hard. We're trained to be clock watchers, to constantly monitor how much time has passed, how much time we have left. But try this instead. Pay attention to change. When you're with someone you love, don't think, "I have 30 minutes before I need to leave for my next thing." Instead, notice. Their expression just changed. They laughed and the energy in the room shifted. The light coming through the window is different than it was a moment ago. A thought arose in your mind, and now it's passing, being replaced by another thought. Attune yourself to the actual texture of experience, the specific, granular, moment-to-moment shifts that are happening constantly. Because that's what time actually is. It's not the numbers on your watch, it's the changes happening in and around you. And here's what happens when you do this. You stop experiencing time as a scarce resource that's slipping away. You start experiencing it as a quality, as the aliveness of reality shifting and moving and being. You're not tracking quantity anymore. Minutes, hours, days. You're experiencing quality, the richness of change itself. This breaks the scarcity mindset. Because how can you run out of change? Change is always happening. Every single moment contains it. You might run out of heartbeats, you might run out of days, but you can't run out of the fundamental reality of things being different from one moment to the next. Second, every time you catch yourself thinking, "I'm wasting time," I want you to stop and ask, what changed during this period? Maybe you just scrolled social media for an hour. Your initial judgment is, wasted time, unproductive. I should have been working or learning or doing something meaningful. But wait, what actually changed? Your mood shifted. You learned something, even if it was trivial. You saw images that sparked associations in your mind. Neurons fired in patterns they haven't fired before. Your body rested. Your brain processed background information. Time passed through you, as it always does, and you experienced it. Was that waste? Or was that just life? Just being a human with a brain and a body that sometimes needs rest, that sometimes wants distraction, that sometimes processes information in ways that don't look productive, but are still part of the pattern of you? Here's the reframe. You can't waste time because time isn't a resource you possess. It's the dimension in which you exist. The question isn't, am I using time well? The question is, am I experiencing my life or am I numb to it? And sometimes experiencing your life means resting. Sometimes it means doing nothing. Sometimes it means scrolling mindlessly because your brain is tired and needs low stimulation input. That's not waste. That's life being lived, change happening, you existing as a temporal pattern. This removes the guilt. You're allowed to rest. You're allowed to do things that don't optimize your productivity. You're allowed to exist without justifying every moment, because you're not here to use time efficiently. You're here to be time, to be the pattern of change itself. And patterns include variation, including periods of rest, including rhythms of activity and stillness. Third practice. Once a day, take 60 seconds to visualize your entire life as a complete structure. I want you to imagine it like a sculpture, like a four-dimensional object stretching from your birth to your death. See your childhood at one end. You're small, learning, growing. See this present moment somewhere in the middle. You're here, listening, thinking. See your eventual old age and death at the other end. All of it existing simultaneously, like a complete story, like a sculpture in space-time. Why does this help? Because when you're anxious about the future, or regretful about the past, you're collapsed into your local, personal now. You're experiencing time as scarcity, as pressure, as countdown. But when you zoom out and see the whole structure, the urgency softens. You realize it's all already there, in the block universe. Your future self, whether they succeed or fail, whether they find peace or keep struggling, whether they're happy or sad, already exists in the structure. You're just experiencing it page by page, moment by moment. And that's okay. That's how stories work. This doesn't make you passive. Your future self exists because you acted, because you chose, because you participated in the unfolding of your pattern. But it takes away the desperate grasping, the fear that you're going to somehow miss your life, or do it wrong, or run out of chances. The structure is what it is. You're reading the story you're reading, and that can be deeply comforting. Fourth practice. When you're stuck or anxious, don't ask, "What should I do?" Ask, "What wants to change right now?" Maybe it's your posture. You've been sitting tensely and your body wants to stretch. Maybe it's the conversation you're avoiding. It wants to happen, and the tension of avoiding it wants to resolve. Maybe it's just your breath. It wants to deepen, to slow down, to bring you back into your body. Time is change. When you align yourself with what's naturally trying to shift, you stop resisting the flow. You become part of the process instead of fighting against it. You stop trying to control every variable and start dancing with what wants to happen. This dissolves paralysis. Because you're not looking for the right answer anymore, the perfect choice that will optimize every outcome. You're just noticing what's already in motion and letting it happen. You're being time instead of trying to manage it. These practices aren't complicated. They're simple, but they're profound because they shift you from treating time as an external force you need to battle or optimize or escape, to recognizing time as what you are. And when you are what you are, when you stop fighting your own nature, life gets a lot easier. So let's bring this together. Let's see where we've been and what it means for how you walk out of here and live your life differently. Time isn't a thing. It's a measurement of change, a relationship between states of the universe. It has a direction because entropy increases, because disorder is more probable than order, because you can't unscramble an egg. It's relative to your motion through space. Your now is personal, local, not universal. And it exists so that you can exist, so that experience is possible, so that there can be stories and meanings and journeys instead of just a frozen, static block of matter. And you're not trapped in time. You are time. You're a four-dimensional pattern of change stretching from birth to death, and the you that you experience at any moment is just one cross-section of that larger structure. Your consciousness is temporal. Your identity is temporal. Your very existence is inseparable from the dimension of time. So what does that mean for the anxiety you started with? The feeling that time is running out, that you're wasting your life, that you're not doing enough, not being enough, not making the most of your limited days? Here's what I want you to understand. That anxiety is real. I'm not dismissing it. It comes from a deep, true recognition that your pattern is finite, that there's a beginning and an end to your particular structure in space-time. You're not going to live forever. You're not going to get infinite chances. And that's genuinely sad. It's genuinely scary. But the anxiety is based on a misunderstanding. You're not running out of time because time isn't a resource that depletes. What you're running out of is change capacity, the number of different states your body and mind can move through before the pattern ends. And that is limited. But it's limited in the way a song is limited. There are only so many notes, only so many measures, and then it ends. Does that make the song less beautiful? Does that make the experience of listening to it less meaningful? Number. If anything, it makes it more precious because you know it's temporary. You know you can't hold on to it. You have to experience it while it's happening and then let it go. Your life is the same. It's a song, a pattern, a structure in time. And it ends. That's not a flaw. That's not something to fight against or deny or solve. That's the nature of temporal existence. Everything that has a beginning has an end. Every pattern that starts eventually stops. And the freedom comes when you accept that. When you stop trying to escape the fundamental structure of reality and start living inside it fully, present to the changes as they happen, not grasping for permanence that was never possible in the first place. You started this video thinking time was an enemy, something stealing your youth, limiting your potential, counting down to your end. But time isn't the enemy. Time is the condition of your existence. Without it, there's no you. Without it, there's no love, no growth, no meaning, no experience. Time is the price of admission to life. And yes, that price includes loss and aging and death. But the alternative is non-existence. The alternative is the frozen block universe with no experience, no journey, no story. I'll take time. I'll take the change. I'll take the temporary, finite, beautiful, heartbreaking experience of being a pattern that unfolds and then ends. Because that's what consciousness is. That's what it means to be alive. So here's what I want you to remember. And I mean really remember, not just intellectually, but in your body, in your bones. You are not running out of time. You are made of time. And every moment you experience, every change, every breath, every shift in light or thought or feeling is you being alive. That's not time passing you by. That's you existing as you were always meant to exist. You're not broken. You're not behind. You're not doing it wrong. You're exactly where you are in the structure, experiencing the page you're on, living the moment that's available to you right now, and that's enough. That's all it ever needs to be. Enough. If something I said here landed for you, if something shifted even a little, even just a small crack in the way you've been thinking about time and your life, let me know in the comments. Tell me what changed, because that's what we're doing here, you and me. We're noticing change together. We're sharing it. We're being alive in this strange, temporary, beautiful structure called time. And if you want more of this, more physics made human, more big questions explored with honesty and clarity and care, subscribe to this channel. Because I'm not going anywhere. Well, I am. Technically, we all are, moving forward through space-time at 1 second per second, experiencing our patterns moment by moment. But you know what I mean. I'll be here, making these videos, thinking about these questions, as long as my pattern allows. Thank you for spending your time, your change, your experience, your precious, finite awareness here with me. Thank you for being curious. Thank you for being open to having your understanding shifted. Thank you for being the pattern that you are. Now go live the next moment, and the next one, and the next one, not because you have to optimize them or make them perfect or prove your worth, but just because they're yours. They're your experience. They're your part of the structure, and that's the only reason you ever needed. You think you live in space. You think you're sitting in emptiness right now, with objects scattered around you. A chair here, a table there, air molecules floating between them. You think space is the stage, and matter is the actors. But that's completely wrong. And Richard Feynman knew it. Here's what you actually live in. You live in fields, everywhere, all around you, passing through you. Right now, as you sit there, you are immersed in electromagnetic fields, gravitational fields, quantum fields that fill every cubic centimeter of what you call empty space. These aren't abstractions. These aren't mathematical conveniences. These are real, physical things. More real, in some sense, than the solid matter you think you're touching. Let me show you what I mean. When you push on a table, you think your hand is touching the table. Solid matter touching solid matter. But that's not what's happening. Your hand is made of atoms. The table is made of atoms. And atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be a marble at the center. The electrons would be tiny specks orbiting near the outer walls. Everything in between? Nothing. Empty. So when you push on the table, your hand's atoms get close to the table's atoms, and the electromagnetic fields around those atoms repel each other. Field pushes against field. You never actually touch anything. Ever. The force you feel is fields interacting. Feynman loved showing people that their intuitions about reality were fundamentally wrong, and the field concept was one of his favorite examples. Let me take you back to the beginning. For a long time, scientists believed in action at a distance, the idea that objects could affect each other across empty space with nothing in between. The sun pulls on the earth, no physical connection, just gravity reaching across millions of miles of vacuum. Newton himself hated this idea. He knew his equations worked. He could predict planetary orbits perfectly, but the mechanism bothered him deeply. How does the sun know the earth is there? How does gravity cross empty space instantaneously? For over 100 years, nobody had a better answer. Then came Michael Faraday. Faraday wasn't a mathematician. He couldn't write fancy equations. But he had incredible physical intuition. He did experiments with magnets and electricity, and he noticed something strange. When you move a magnet near a wire, electricity flows in the wire. When you run electricity through a wire, it creates magnetism around the wire. Faraday couldn't accept action at a distance. He thought there had to be something in between, something filling the space, something that carried the force from one place to another. He called it a field. Imagine putting a magnet on a table and sprinkling iron filings around it. The filings arrange themselves in beautiful curves, swooping from one pole of the magnet to the other. Those curves aren't just a pattern. According to Faraday, they reveal something real. The magnetic field exists in the space around the magnet. The field is there, invisible but present, and the iron filings align with it, showing us its shape. James Clerk Maxwell took Faraday's intuition and turned it into mathematics. He wrote down equations that described how electric and magnetic fields behave. And when he worked through the math, something incredible happened. The equations predicted that electromagnetic fields could create waves that travel through empty space at a specific speed. Maxwell calculated that speed. It came out to exactly the speed of light. In that moment, Maxwell realized what light actually is. Light is an electromagnetic wave, a ripple in the electromagnetic field propagating through space. The field is the medium. Now, here's where it gets interesting. These electromagnetic waves carry energy. You can feel this. Stand in sunlight and you feel warmth. That warmth is energy carried by electromagnetic waves from the sun. The waves traveled 93 million miles through the vacuum of space. Nothing material made that journey. No particles, no substance. Just the field, oscillating, carrying energy across emptiness. If the field is carrying energy, then the field must be something. Energy doesn't exist in nothing. Energy requires a physical system to contain it. Think about a radio. How does a radio work? A radio station sends out electromagnetic waves. Those waves propagate through space. Your radio's antenna detects the waves, converts them to electrical signals, and you hear music. But what's actually happening? At the radio station, electrons are being pushed back and forth in an antenna. This creates a disturbance in the electromagnetic field. That disturbance spreads outward as a wave. The wave reaches your antenna. The field disturbs the electrons in your antenna, making them move. That motion becomes the signal that produces sound. At no point did anything travel from the station to your radio. The field was already there, filling all of space. The station just created a wave in the field, a ripple, and that ripple propagated to you. Now, Feynman would push this further. There are other fields, too. There's a gravitational field. Every massive object creates a gravitational field that fills all of space. The Earth's gravitational field extends to the Moon, to Mars, to the edge of the solar system, and beyond. Getting weaker with distance, but never quite reaching zero. You exist in Earth's gravitational field right now. You also exist in the Sun's gravitational field, the Moon's gravitational field, every planet's field, every star's field. All these fields overlap. The same cubic centimeter of space contains multiple fields at once. But here's where Feynman really shines. He'd tell you about quantum fields. In quantum field theory, fields are the only real things. Particles are just excitations in fields. Let me explain what that means. You think an electron is a tiny ball, a little particle of matter. But it's not. An electron is a ripple in the electron field. The electron field fills all of space, everywhere. And when the field gets excited in a particular way, we detect what looks like a particle. The particle is the field oscillating. Every electron in the universe is an excitation of the same field. One field, many ripples. And it's not just electrons. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. Every particle we've ever detected is actually a field doing something interesting. This is the picture Feynman worked with. Reality is made of fields filling all of space, and what we call particles are just these fields vibrating in quantized ways. This raises a question. If particles are field excitations, what happens when particles interact? What happens when an electron and a photon collide? Feynman invented a way to visualize this. Feynman diagrams. These are pictures that show how fields interact. An electron moving through space is really the electron field oscillating along a path. When it emits a photon, the electron field couples to the electromagnetic field, creating an excitation in the electromagnetic field. The diagram shows this as lines connecting and splitting. But what's really happening is fields exchanging energy. And here's something Feynman emphasized. When you do the calculations with quantum field theory, you get the most accurate predictions in all of science. Quantum electrodynamics, the theory of how electrons and photons interact, has been tested to absurd precision. Calculations agree with experiments to 10 decimal places. 10. No other theory comes close. Why does it work so well? Because it's describing reality correctly. Now, let me address something that probably bothers you. You're thinking, okay, fields exist, but they're in space, right? Space is the container, and fields are the contents. But that's not quite right either. Because of relativity, Einstein showed that space and time are connected. They're part of a single structure called space-time. And fields exist in space-time. But space-time isn't just a passive stage. Space-time itself is dynamic. It curves, it bends, it responds to matter and energy. In fact, Einstein's general relativity describes gravity as curvature of space-time. And what causes that curvature? The presence of matter and energy. But matter is really field excitations, so fields curve space-time. And curved space-time affects how fields behave. They're coupled together in a feedback loop. Here's what Feynman would want you to understand. You don't live in space with objects in it. You live in a dynamic, fluctuating, interconnected structure of fields and curved space-time. Every point in this structure has values for multiple fields. The electromagnetic field has a certain strength and direction. The electron field has a certain amplitude. The gravitational field has a certain curvature, and these values change from point to point. They evolve in time. They interact with each other. Let me give you an example that makes this tangible. You're probably familiar with magnets. When you hold two magnets close to each other, you feel a force. If the poles are aligned the right way, they push apart. You can feel the repulsion in your hands. Now, what's pushing? There's empty space between the magnets, nothing visible. But there's a magnetic field. The field from one magnet extends into space. The field from the other magnet extends into space. Where the fields overlap, they interact. And that push is transmitted to your hands as a force you can feel. Feynman had a beautiful way of thinking about this. He'd say, when you do physics, you have a choice. You can think about forces acting at a distance. Object A affects object B across empty space. Or you can think about fields. Object A creates a field. The field fills space. Object B responds to the field at its location. Both approaches give the same answer mathematically. But the field approach is deeper, because the field actually has physical properties. You can put energy into the field. You can measure the field's strength. The field can exist even when the sources aren't there anymore. The field is an independent entity. Here's a concrete example. Imagine you have a charged particle. It creates an electric field around itself. Now, you suddenly move the particle. The field near the particle changes immediately, but the field far away doesn't know yet. Information about the particle's new position has to propagate outward. It travels as a wave in the field at the speed of light. Until that wave reaches a distant location, the field there is still responding to where the particle used to be. The field has a life of its own. It's not just a mathematical description of forces between objects. It's a physical thing that evolves according to its own equations. Now, quantum fields add another layer of strangeness. In quantum mechanics, fields fluctuate. Even in what we call empty space, quantum fields are never perfectly still. They're always jittering, oscillating, creating temporary particle-antiparticle pairs that pop into existence and annihilate. These are called virtual particles. They're quantum fluctuations of the field. And these fluctuations have measurable effects. They change the energy levels of atoms. They create forces between metal plates in a vacuum. This is the Casimir effect. Two metal plates in empty space attract each other because the quantum field fluctuations between the plates are different from the fluctuations outside. The vacuum itself exerts pressure. Feynman worked extensively on these quantum effects. He developed techniques to calculate them. And what he found is that the vacuum, what we think of as empty space, is actually a seething foam of quantum activity, fields fluctuating wildly at tiny scales, creating and destroying virtual particles constantly. The vacuum has energy. It has structure. This is hard to visualize because we can't see fields directly. We only see their effects. We see particles, objects, forces. But underlying all of that are fields. Let me try another approach. Think about waves on water. You see a wave moving across a pond. What's actually moving? Not the water. The water molecules mostly move up and down. The wave is a pattern, a disturbance traveling through the medium. The medium is water. The disturbance is the wave. Now apply this to electromagnetic waves. Light is a wave. What's the medium? The electromagnetic field. What's the disturbance? Oscillations in the field's strength. But unlike water waves, which need water, the electromagnetic field doesn't need a medium. The field is the medium. It exists on its own. Feynman emphasized this point repeatedly. Fields are not abstractions. They're not just mathematical tools. They're real physical entities with energy, momentum, and dynamics. When you turn on a flashlight, you create electromagnetic waves. Those waves carry energy. That energy is stored in the electromagnetic field. Now here's something that might bother you. If fields fill all of space and multiple fields overlap, doesn't that mean every point in space is infinitely full? Sort of. Every point in space-time has a value for every field. The electromagnetic field has a value there. The electron field has a value there. The quark fields have values there. All the values coexist. The fields don't exclude each other. They pass through each other. They superimpose. And at any moment, the state of reality is given by specifying all the field values at all points. Feynman loved pointing out how weird this is. He'd say, "You think you understand the world. You think it's made of objects. But when you look closely, objects dissolve into fields. You can't point to a location and say the electron is here. The electron field is everywhere. It just has different amplitudes at different locations. And when you measure the electron's position, you're really measuring where the field is most strongly excited. The measurement creates a localized result, but before the measurement, the field was spread out. This is quantum mechanics. Here's another way to think about it. You've probably heard of wave-particle duality. Light sometimes behaves like a wave, sometimes like a particle. Electrons sometimes behave like particles, sometimes like waves. This wave-particle duality confused physicists for decades. But field theory resolves it. Everything is a field. Fields can have wave-like excitations. They can also have particle-like excitations. It's the same entity, just different behaviors depending on how you interact with it. Feynman actually won the Nobel Prize for his work on quantum electrodynamics, the quantum field theory of electromagnetism. He developed a mathematical technique called path integrals that made calculations possible. And what the calculations showed is that when a particle goes from point A to point B, it doesn't take a single path. It takes all possible paths simultaneously. The field explores every possible route, and these paths interfere with each other quantum mechanically. The result is the behavior we observe. Let me bring this back to something concrete. Your body is made of atoms. Those atoms are made of electrons and quarks. Those electrons and quarks are excitations of quantum fields. The forces holding your atoms together, the electromagnetic forces, are mediated by the electromagnetic field. Without fields, there would be no structure, no stability, no matter as we know it. You are a pattern in fields, a highly organized, complex pattern, but fundamentally, fields are what you're made of. Here's something else Feynman taught us. Fields have inertia. If you try to change a field quickly, the field resists. This resistance is where mass comes from, in a sense. When you push on an object, you're accelerating its particles, but those particles are field excitations. Accelerating them means changing the field configuration. And the field doesn't want to change. It has inertia. That inertia is what we experience as mass. So mass itself is a property of fields. Let me go deeper. The Higgs field. You've probably heard of it. The Higgs boson was discovered in 2012, but the Higgs boson is just an excitation of the Higgs field. And the Higgs field does something remarkable. It fills all of space with a non-zero value everywhere. And when other fields interact with the Higgs field, they acquire mass. The more strongly a field couples to the Higgs field, the more massive its particles are. Without the Higgs field, electrons would be massless. They'd zip around at the speed of light. There'd be no atoms, no chemistry, no us. Feynman didn't live to see the Higgs boson discovered, but he understood the concept. He knew that fields are fundamental and that interactions between fields create the richness of physical phenomena. And he knew that our intuitive picture of reality is just a convenient fiction. Now let's talk about forces. You experience 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In the field picture, all of these are mediated by fields. Electromagnetism is mediated by the electromagnetic field. The strong force is mediated by gluon fields. The weak force is mediated by W and Z boson fields. And gravity is the curvature of space-time itself. Feynman spent a lot of time thinking about gravity. He tried to reconcile it with quantum mechanics. It's still an unsolved problem. We have quantum field theories for the other forces, but not for gravity. Gravity resists quantization. But Feynman believed that ultimately, gravity would also be understood as a quantum field. Gravitons, hypothetical particles of gravity, would be excitations of the gravitational field. We haven't detected gravitons. We might never be able to. But theoretically, they should exist. And here's the beautiful part. We figured this out. Humans, starting from basically nothing, built up this understanding. Faraday with his intuitions, Maxwell with his equations, Einstein with his relativity, Feynman with his quantum calculations. We went from thinking space is empty to realizing it's permeated by fields. We went from thinking particles are fundamental to realizing fields are fundamental. We took our everyday experience, which is completely misleading, and through experiment and mathematics uncovered the truth. Feynman loved teaching this. He loved showing people that the universe is not what it seems, that the solid table is mostly empty space held together by fields, that particles are field excitations, that forces are field interactions. He loved the fact that nature is stranger than we imagine, and that we can discover that strangeness through science. Now, you might be wondering, does this matter? Does it change anything to know that you live in fields rather than empty space? Practically, maybe not. You still sit in chairs. You still turn on lights. The everyday world works the same way, but conceptually, it changes everything. It means the universe is not made of things. It's made of processes, fields evolving, interacting, creating temporary patterns that look like particles. Those patterns are us. We're not objects in space. We're disturbances in fields, ripples in the quantum foam. Feynman wouldn't want me to get too poetic about this. He'd say, look, the equations work. The predictions match experiments. That's what matters. But even Feynman appreciated the beauty of the picture, reality as a tapestry of interacting fields, everything connected through overlapping field configurations, everything dynamic, everything fundamentally unified in the structure of quantum field theory. Here's the deepest part. When you look at an object, you think you're seeing something separate from yourself, something out there. But in the field picture, there's no clear separation. Your electromagnetic field overlaps with the object's electromagnetic field. The photons bouncing off the object and hitting your eye are excitations of the electromagnetic field that connects you and the object. The field is continuous. Where do you end and the object begin? There's no sharp boundary, just field values changing smoothly in space. This doesn't mean you are the object. You're still a distinct pattern, but the separateness is less absolute than it seems. The universe is not made of isolated things. It's made of interconnected field configurations. This is what Feynman understood, and it's what he tried to teach. The universe is not a collection of objects. It's a unified field structure, and we are part of that structure, not observers looking at it from outside, participants embedded within it. When you understand fields, you understand that space is not emptiness. Space is dynamic and rich. Every point filled with field values, every moment filled with quantum fluctuations, every interaction mediated by fields exchanging quanta. You don't live in space, you live in this, in fields, always. And that's not philosophy, that's physics, tested, verified, true. I'm going to tell you something embarrassing. I'm a physicist. I've calculated quantum probabilities, worked on atomic bombs, taught at Caltech, and I spent years being confused about mirrors. Not in a, curious way. In a this doesn't make any damn sense way. I'd stand there moving my left hand, watching the mirror me move their right hand, and I'd think, why right? Why not up? What's special about left-right? Then one day, I'm not kidding, I'm watching a kid play with a toy car, and the kid holds it up to a mirror, and the car doesn't look backwards to him. And that's when I realized, I've been asking the wrong question my entire life. The mirror never changed. I changed. Something inside my perception flipped, not outside. And understanding what flipped is maybe the most clarifying thing I've ever learned about being human. Now, you've lived with mirrors your entire life, but you've probably never understood what they actually do. And that misunderstanding reveals something profound about how you experience everything. Most people think this is a quirky physics question. It's not. It's about the invisible ways your mind constructs meaning, creates perspective, and builds your sense of self from assumptions you never examine. Here's the core pain. You've been told reality is objective and straightforward, but then you encounter something as simple as a mirror, and suddenly the rules seem arbitrary. Why left-right but not up-down? It feels like the universe is gaslighting you. That confusion? It's pointing to something deeper. Your brain constantly builds models of reality, and when those models clash with each other, you feel disoriented without knowing why. This video will show you that mirrors don't flip anything. Your mind does. And once you understand exactly what your mind is doing and why, you'll never see perception the same way. You'll gain a tool for recognizing when you're imposing human-centered assumptions on a neutral universe. This isn't just about mirrors, it's about learning to catch yourself in the act of creating reality. Every other explanation either gets lost in technical jargon or hand-waves the answer. I'm going to walk you through the actual mechanism, using your body, your imagination, and simple thought experiments until you feel the moment when the flip happens inside your own mind. No tricks, no shortcuts, just clarity. Let me take you back to that moment with the kid and the toy car because it's important. I was at a friend's house and their son, maybe 7 years old, was playing with this little red sports car. He was making engine noises, driving it along the coffee table, the whole thing. Then he noticed the mirror on the wall, and he held the car up to it. He looked at the reflection, looked at the car in his hand, looked back at the reflection, and then he said something that stopped me cold. It's the same car. Now, to me, standing there watching, the car in the mirror looked backwards. The front was facing the opposite direction. If there was writing on the side, it would have been reversed. But to this kid, it was the same car. He wasn't seeing a flip. He was seeing his car reflected. And I realized in that moment that the flip I was seeing, the reversal I was so convinced was real, was something I was adding. I was bringing an expectation to the mirror that the kid wasn't bringing yet. So I got curious. I asked him, "Does the car look different in the mirror?" And he thought about it for a second and said, "Yeah, it's over there instead of here." That's it. That's all he saw, a positional difference. The car was in his hand, and there was also a car image behind the glass. But he wasn't seeing left become right. He wasn't confused about directions. He was just seeing a reflection. Now, when I held up my hand to the mirror, I immediately saw left and right swap. When I raised my left hand, the mirror me raised what looked like their right hand, and I'd been seeing that my whole life, taking it for granted as something the mirror does. But watching this kid, I realized he wasn't making that translation yet. He hadn't learned to project personhood onto the reflection, to imagine it as another being with its own left and right. And that's when it hit me. The flip happens when you turn the reflection into a person. When you see the image in the mirror and automatically think, that's someone facing me. Because when someone faces you in real life, when you stand face to face with another person, and they raise their right hand, you see it on your left side. That's just perspective. Two people facing each other have opposite orientations. Their rights and lefts are reversed relative to each other. But here's the thing. When you do that with a mirror, you're comparing two different things. You're comparing your actual left hand with what you imagine is the reflection's right hand. You're attributing leftness and rightness to an image that doesn't actually have those properties. An image doesn't have a left side, it's just light arranged in a pattern. So let me take you through this step by step, because once you see it, you can't unsee it, and it's glorious. Imagine you're standing in a room, and there's another person standing across from you, facing you. You raise your left hand. From your perspective, your hand is on the left side of your body. From their perspective, looking at you, your hand appears on their right side. That makes sense, right? You're facing opposite directions. Your left is their right. There's no mystery here. Nobody says, whoa, that person got flipped. You just say, we're facing each other. Now imagine that person is standing behind a window, a big glass window. You're on one side, they're on the other. You raise your left hand. They raise their right hand. Same thing as before. You're facing each other through glass. Still no flip. Still just two people with opposite orientations. Now, and this is where it gets interesting, make that window reflective. Turn it into a mirror. You're still standing there, and now instead of seeing through to another room, you see your own reflection. You raise your left hand, and the reflection raises what looks like its right hand. But here's the critical question. What changed? The geometry didn't change. The light paths didn't change. You're still looking at an image of someone facing you. The only thing that changed is your interpretation. With the window, you knew it was another person. With the mirror, you know it's you, but you still interpret it as a person facing you, as another being with its own perspective. And that's where the trouble starts, because it's not another being. It's not a person inside the mirror with their own left and right. It's a pattern of light. But your brain doesn't see it that way. Your brain sees a face, and when your brain sees a face, it immediately assigns personhood, perspective, agency. It creates a mental model of another self. Here's what your brain does automatically without asking permission. It imagines you walking forward into the mirror, passing through the glass, and then turning around to face back out. Like you went through a doorway and turned 180 degrees. And when you imagine that rotation, you rotate around your vertical axis, the axis running from your head to your feet, because that's how you turn around in real life. You don't do a cartwheel. You don't roll sideways. You pivot on your feet, spinning around the up-down axis. And when you mentally rotate yourself that way, 180 degrees around the vertical, your left and right swap, but your up and down stay the same. That mental rotation is where the flip comes from, not from the mirror, from your imagination. Let me prove it to you with a thought experiment. Stand up right now, or imagine standing up. Face an imaginary mirror. Raise your left hand. The mirror you raise is what looks like their right hand. You see the flip. Now, I want you to imagine a different rotation. Instead of spinning around your vertical axis like you're turning around, imagine rotating around your left-right axis, like you're doing a cartwheel or a front flip. Imagine your head going down and your feet going up, rotating forward until you're upside down. If you rotated into the mirror that way, what would change? Your left would still be on the left. Your right would still be on the right. But your head would be where your feet were, and your feet would be where your head was. Up and down would be flipped, not left and right. The mirror didn't change. The reflection didn't change. The only thing that changed was which axis you used to imagine rotating yourself into the mirror. And depending on which axis you choose, different directions appear to flip. Now try another one. Imagine rotating around your front-back axis, like you're a rotisserie chicken, rolling sideways. If you did that rotation into the mirror, you'd end up lying on your side, and from that orientation, the mirror, you wouldn't look flipped at all in certain ways. The point is, the flip isn't a property of the mirror, it's a property of the mental rotation you're performing. And here's the beautiful, strange thing. You don't choose that rotation consciously. Your brain does it automatically. It's so fast, so deeply wired, that you don't even notice it's happening. You look in the mirror and instantly, in a fraction of a second, your brain says, "That's me," turned around, and it picks the vertical axis because that's the axis you use to navigate the world. Think about it. When you turn around in real life, you rotate around your vertical axis. When someone calls your name from behind, you spin around that axis to face them. When you walk through a doorway and want to go back, you rotate around that axis. Gravity holds you upright. Your head stays up, your feet stay down, and left and right swap every time you turn. You've done this rotation thousands and thousands of times. It's built into your motor memory, your spatial reasoning, your sense of how bodies move through space. So when your brain sees a face facing you, it immediately models it as a person who rotated around their vertical axis to face me, even if that face is your own. Even if it's just a reflection, the brain doesn't stop to ask whether this is a real person or an image, it just runs the model. And the model says, vertical rotation, left-right swap, up-down stays the same. That's why mirrors seem to flip left and right, but not up and down. Not because of anything the mirror is doing, because of the specific mental rotation your brain automatically performs. Now, let me tell you about what the mirror actually does, because this is where physics comes in, and it's going to blow your mind with how simple it is. A mirror reverses depth. That's it. That's the only thing it does. It flips front and back, not left and right, not up and down, just front and back, in and out. Near and far. Here's how it works. When light bounces off your face, it travels toward the mirror in straight lines. Photons leave your nose, your eyes, your forehead. Every point on your face is sending out light. That light hits the mirror, and the mirror reflects it back. The angle of incidence equals the angle of reflection. If light hits the mirror at a 30-degree angle, it bounces off at a 30-degree angle on the other side. Perfect, predictable, no tricks. Now, when that reflected light reaches your eyes, your brain interprets it as coming from behind the mirror. If you're standing 1 meter in front of the mirror, the image appears to be 1 meter behind the mirror. Your brain traces the light rays backward in straight lines, and those lines converge at a point behind the reflective surface. That's called a virtual image. It's not really there. No light is actually behind the mirror. But it looks like it's there because of the way the light paths work out. So here's the key. The image behind the mirror is the same distance behind the mirror as you are in front of it. If you're 3 feet away, the image looks like it's 3 feet deep. The mirror has taken the dimension of depth, the front-to-back axis, and reversed it. Points that were closer to the mirror on your side appear farther from the mirror on the image side. Points that were farther away appear closer. Front becomes back becomes front, and that's it. That is the only transformation the mirror performs. Everything else, all the left-right confusion, comes from how you interpret that reversed depth. Let me give you a concrete example. Take a piece of paper and write a word on it. Let's say you write the word mirror in big letters. Now hold that paper up facing you. You see mirror, nice and clear. Now turn the paper around so the writing faces the mirror. What do you see in the reflection? You see the word backwards. O-R-R-I-M. Why did that happen? Did the mirror flip the letters left to right? No. You flipped the paper front to back. You physically rotated it 180 degrees around the vertical axis so that the writing, which was facing you, now faces the mirror. You reversed its depth. The surface that was facing toward you is now facing away from you, toward the mirror. And the mirror is just showing you that reversed surface. It's like a rubber stamp. When you carve a stamp, the letters are reversed on the stamp itself. When you press the stamp onto paper, the image comes out reversed again, which makes it readable. The stamp has to be backwards for the print to be forward. The mirror is showing you the stamp, the surface that's actually facing it, and that surface is backwards because you turned it backwards when you held it up. Now here's where it gets really interesting. Take that same piece of paper with mirror written on it, and this time, don't turn it around. Just hold it up facing you, and look at its reflection in the mirror while looking past the paper. The reflection shows the back side of the paper, the blank side. There's no text visible because the text is facing you, not the mirror. But what if the paper was transparent? What if you wrote on a clear sheet of plastic? Now hold it up facing you. You see mirror correctly. Look at it in the mirror. You still see mirror correctly because you're seeing through the transparent sheet to the text, which is facing you. The mirror shows the back of the sheet, but the text is visible through it, and it hasn't been flipped because you didn't flip the sheet. Okay, now write mirror on the transparent sheet and then turn it around so the writing faces the mirror. Now, what do you see in the reflection? The text looks backwards. Why? Because you reversed the sheet's depth. The writing, which was facing forward, now faces backward, and you're viewing it from behind. You're seeing the back side of each letter. This is what I mean when I say the mirror only reverses depth. It shows you the surface that faces it. If you turn something around, if you reverse its front and back, the mirror will show you that reversed surface. But the mirror itself didn't do the reversing. You did. The mirror is just being honest. Now let's get back to you, standing in front of the mirror, looking at your reflection. You haven't physically turned yourself around. You're still facing the mirror. So why does it look flipped? Because of the mental rotation I talked about earlier. You're imagining yourself turned around, even though you haven't actually turned around. You're comparing your actual body, facing forward, with your left hand on your left side, with an imaginary version of yourself that's been rotated 180 degrees around the vertical axis. And when you do that imaginary rotation, your left becomes your right. But here's the thing. That imaginary rotation is just one possibility. You could imagine rotating around a different axis, and then different directions would appear flipped. The mirror doesn't force you to imagine any particular rotation. Your brain chooses the vertical rotation because it's the most familiar, the most natural, the one that matches how you actually move through the world. Let me tell you what happens when you actually lie on your side and look in a mirror, because I tried this, and it's wonderful. I lay down on my left side on the floor, propped my head up on my hand, and looked at a mirror on the wall. And suddenly the flip changed. It didn't look like left and right were reversed anymore. It looked like up and down were reversed. My head, which was on the left side of my body, appeared in the mirror on the right side of the mirror me's body. But the top of my head, which was pointing toward the ceiling, still appeared to point toward the ceiling in the reflection. Why did this happen? Because I changed my orientation relative to gravity, and my brain changed which rotation it imagined. When I'm lying on my side, my brain doesn't model the mirror me as upright and facing me. It models it as lying on the opposite side, and to get from my orientation to that orientation, you'd rotate around a different axis, around the front-back axis instead of the up-down axis. And when you rotate around that axis, different directions swap. This blew my mind because it proved that the flip isn't objective. It's not a property of the mirror or even of the reflection. It's a property of my mental model, of the story I'm telling about how I could move from where I am to where the reflection appears to be. And that story changes depending on context, on my orientation, on which rotation feels most natural given how I'm positioned. So let's dig deeper into this idea of left and right, because it's stranger than you think. Left and right are not like up and down. Up and down are defined by the earth. Down is the direction gravity pulls. Up is the opposite direction. These are absolute, objective. If you and I are standing in the same room, we agree on which way is up and which way is down, no matter where we're positioned or which direction we're facing. But left and right, those depend entirely on your body. Your left is the direction of your left hand. Your right is the direction of your right hand. If you turn around, your left and right turn with you. They're relative to your orientation. And here's the really weird part. Left and right are symmetrical on your body. You have 2 eyes, 2 ears, 2 arms, 2 legs, arranged in a mirror image pattern across the midline of your body. If you draw a vertical line down the center of your face, the left side is basically a reflection of the right side. Not perfectly, but close enough. But your top and bottom? Not symmetrical at all. Your head is nothing like your feet. Your mouth is nothing like your knees. Your body has a built-in asymmetry along the up-down axis. You're directional. You have a front and a back, a top and a bottom. And these are not interchangeable. This is important because it explains why you use your body to define left and right, but not up and down. Up and down are given to you by the world. Left and right are given to you by your own symmetry. You are your own compass for horizontal directions. And because left and right are defined by your body, they swap when you imagine your body in a different orientation. When you mentally rotate yourself 180 degrees around the vertical axis, your body's left-right axis flips relative to the room. What was on your left is now on your right, but up and down, which are defined by gravity, don't flip. The earth didn't rotate with you. So when you look at a mirror and imagine yourself turned around inside it, you're asking, if I were over there, facing back at myself, which direction would be my left? And the answer is, the opposite of your current left. Because you've mentally rotated your body, and left-right is relative to your body. But then you ask, if I were over there, which direction would be up? And the answer is, the same as your current up. Because up is not relative to your body. It's relative to the earth, and the earth didn't change. This is the asymmetry that creates the paradox. You're mixing 2 different reference frames, body-centered directions and earth-centered directions, and treating them as if they're the same kind of thing. But they're not. Let me give you another way to think about it. Imagine you're an alien who doesn't have a symmetrical body. Maybe you're shaped like a cone, with a point on top and a wide base on the bottom. You have no left or right side. Your body is rotationally symmetrical around the vertical axis. You can spin around and you'd look the same from every angle. Now you look in a mirror. Do you see a left-right flip? No, you can't, because you don't have a left or right. You see a front-back flip. The point that was facing forward now appears to face backward in the reflection. But there's no confusion about left and right because those concepts don't apply to you. But if you're a human with a bilaterally symmetrical body, you do have left and right, and you use them constantly to navigate and describe the world. And so when you see an image of a body, even your own body reflected, you immediately assign it left and right, based on where you imagine its hands would be. And that assignment depends on how you imagine the body oriented. The mirror isn't doing anything special to left and right. You are. You're the one creating those labels, projecting them onto the image, and then getting confused when the labels don't match the way you expect. Now let's talk about the most beautiful part of all this. The mirror reveals something profound about how your mind works. It shows you that you're constantly building a model of the world, and that model includes not just objects and positions, but perspectives and identities. When you look at the mirror, you don't see photons bouncing off a reflective surface. You see a person. You see yourself, but as if you were someone else. You create an imaginary other, a second consciousness looking back at you from behind the glass. And you do this instantly, automatically, without any effort or awareness. This is what humans do. We see faces and we create minds. We look at patterns of light and shadow and we see intention, emotion, perspective. We can't help it. It's so deeply wired into us that we do it even when we know, intellectually, consciously, that there's no other mind there. You know the reflection isn't thinking. You know it's not a separate being, but you can't stop your brain from treating it like one. And because you treat it like a separate being, you imagine what it would be like to be that being. You imagine their perspective. You imagine their left and right. You imagine how they would see you. And in doing that imagining, you mentally rotate yourself, and that rotation creates the flip. This is empathy. This is theory of mind. This is the cognitive machinery that lets you understand other people, predict their actions, cooperate and communicate, and build societies. It's one of the most powerful abilities humans have, and the mirror paradox is what happens when you point that ability at yourself. You try to model yourself as an other. You try to take a third-person perspective on your own first-person experience, and your brain gets tangled up because you're both the observer and the observed. You're trying to be in two places at once, in your body and in the imaginary body behind the mirror. And the only way your brain can make sense of that is to imagine one of you rotated relative to the other. And the rotation it picks, the vertical rotation, is the one that feels most like walking toward the mirror, passing through it, and turning around to look back. It's spatial. Kinesthetic. It maps onto the movements you make with your actual body. When you think about walking into another room and facing back the way you came, you rotate around your vertical axis. So that's the rotation your brain uses when it models the mirror self. But here's the profound thing. None of this is necessary. The mirror doesn't require you to imagine another self. It doesn't demand that you model it as a person facing you. That's something you add. That's something your mind creates out of pure, powerful, beautiful habit. You could look at the mirror and just see patterns of light. You could see it as pixels of color, arranged in a shape that correlates with your body but isn't your body. You could see it the way a camera sees it, as data, as information, with no perspective, no left or right, no self looking back. But you don't, because you're human. And being human means seeing people everywhere, even in your own reflection. It means creating stories about perspective and identity, and what it would be like to be someone else. It means taking the raw material of light and building from it a social world, a world of minds and intentions and relationships. The mirror paradox isn't a bug in your perception. It's a window into how perception works. It's a glimpse of the machinery underneath, the way your brain takes ambiguous sensory data and constructs from it a coherent, meaningful experience. And the construction it builds is so seamless, so automatic, that you mistake it for reality itself, until something like a mirror shows you the seams. Let me tell you about another moment when I saw those seams. I was teaching a class at Caltech, and I was trying to explain symmetry in physics. I was talking about how the laws of physics don't change if you flip everything left to right. It's called parity symmetry. If you ran an experiment, and then you ran the exact same experiment but with everything mirrored, every particle on the left now on the right, every rotation reversed, the experiment would play out the same way. Nature doesn't have a preference for left versus right. Except it turns out it does. There are certain particle interactions, weak nuclear force interactions, where parity symmetry is violated, where left and right are not equivalent. This was discovered in 1956, and it shocked the physics world because we'd assumed symmetry was fundamental. But here's what's important. Even though the weak force violates parity, the violation is tiny. For almost everything in your everyday life, for mirrors, for light, for the way objects move and bounce and reflect, left and right are completely symmetrical. The universe, at the scale you experience it, truly doesn't care about left versus right. And yet you care. Deeply. You have a left hand and a right hand, and they're different to you. You have a dominant hand. You have a side of the bed you sleep on. You give directions using left and right. These directions are meaningful to you because they're anchored in your body, in your experience, in your sense of self. So there's this beautiful tension. The universe is, mostly, symmetrical, but you are not. You live in a symmetrical world but experience it asymmetrically because of your body's structure. And that asymmetry is what makes left and right feel real and important, even though they're arbitrary. The mirror reveals this tension. It holds up the universe's indifference to left and right, the perfect symmetry of reflected light, and forces you to confront it with your own deeply felt sense that left and right matter. And in that confrontation, you see the flip. You see the mismatch between the world as it is and the world as you experience it. And this, to me, is one of the most important things you can learn, that your experience is not the same as reality. Your experience is a model, a construction, a story your brain tells based on sensory input, prior expectations, and evolutionary pressures. That doesn't make it false. The model is incredibly useful. It works. It lets you navigate, survive, thrive. But it's not complete. It's not objective. It's a human-centered slice of a much larger, stranger reality. And when you see the seams, when you catch your brain in the act of building the model, like you do with the mirror paradox, you get a glimpse of what's beyond the model. You see the photons, the geometry, the pure information before your mind shapes it into left and right, self and other, person and image. That glimpse is clarity. It's freedom. It's the beginning of real understanding. Now I want to give you something practical, something you can do right now, today, to start seeing these seams in your own perception. Stand up. Face a mirror, a real one, or just imagine one. Raise your left hand. Watch the reflection raise what looks like its right hand. Feel that familiar flip. Now here's the practice. Catch yourself in the act of imagining the rotation. Notice the split second when your brain says, "That's me, but turned around." Notice the moment when you project personhood onto the image, when you create the imaginary other in the mirror. It happens fast. It's subtle, but once you start looking for it, you'll see it. You'll feel it. There's a moment, a tiny, almost imperceptible moment, when your mind does the work of flipping, of comparing, of creating left and right for the reflection. And when you catch that moment, you realize, I'm doing this, not the mirror, me, my imagination, my mental model. That realization is powerful because it extends beyond mirrors. Once you start noticing how you create perspective, you start noticing it everywhere. You start seeing how much of what you call reality is actually your mind's interpretation. Someone doesn't respond to your text, you feel ignored. But wait, did they ignore you, or are you projecting intent onto their silence? Are you creating a story about what their silence means, just like you create a story about what the mirror image's right hand means? You face a choice, left or right, option A or option B. But wait, are those the only options, or are you imposing a binary frame onto a situation that might have more dimensions? Are you stuck in left-right thinking when maybe there's an up-down or a front-back you haven't considered? You look at someone else's life and think, they're so lucky, or they have it easier. But wait, are you imagining yourself rotated into their position around the vertical axis, keeping your up and down the same? Are you assuming their reality works like yours, just flipped? Or are they oriented in a completely different way that you can't see from your perspective? These are mirror questions. They're questions about where you end and where the world begins, about what's objective and what's projected, about which parts of your experience are reflecting reality and which parts are reflecting your own mind back at you. And the practice, the daily, moment-to-moment practice, is to keep asking, to stay curious, to notice when you're flipping, when you're rotating, when you're creating an imaginary other, and then getting confused by your own creation. Here's another practice. Teach this to someone else. Find a friend, a kid, a co-worker. Tell them you want to show them something strange about mirrors. Guide them through the thought experiments I've shared with you. Have them raise their hand and watch the reflection. Ask them which direction flipped. Ask them why left-right and not up-down. Then walk them through the rotation. Have them imagine spinning around their vertical axis, then around their horizontal axis. Show them that the flip changes depending on which axis they choose. Watch their face when they get it. When they see that the mirror isn't doing the flipping, they are. That moment, when someone else sees it, is pure joy. Because you're not just sharing information, you're sharing a perspective shift. You're helping someone escape a confusion they didn't even know they were in. You're showing them the seams in their own perception, and in doing so, you're giving them a tool for seeing more clearly. And here's why teaching matters. When you explain something to someone else, you understand it at a deeper level. You have to find the right words, the right examples, the right metaphors. You have to anticipate their questions and confusions. And in doing that work, you clarify it for yourself. You see it from new angles. You discover aspects of it you hadn't noticed before. I've been teaching physics for decades, and I learn something new every time I explain a concept to a student, because their confusion points me toward something I've been taking for granted. Their questions reveal assumptions I didn't know I was making. And when I find the explanation that works for them, when I see the light bulb turn on, I feel it turn on in me too. So teach, share, explain, not to show off, not to prove you know something, but to deepen your own understanding and to free someone else from confusion. That's what this is about. That's what thinking is about. Not accumulating knowledge, but sharing clarity. And while we're talking about practice, here's one more. Start asking, where's the mirror here? When you encounter confusion in other areas of your life, you have a conflict with someone. You think they're wrong, they think you're wrong. Where's the mirror? Are you both looking at the same situation from opposite perspectives, each seeing the other as flipped, each thinking your own orientation is the correct one? Can you step back and see that both of you are just different viewpoints on the same neutral geometry? You feel stuck in a pattern. Same problems, different day. Where's the mirror? Are you rotating around the same axis every time, trying the same mental flip, expecting different results? What if you rotated around a different axis? What if you approached the problem from up-down instead of left-right? You judge yourself harshly. You see flaws, mistakes, failures. Where's the mirror? Are you looking at yourself as an imaginary other, comparing your inside experience to your outside appearance, creating a flip that makes you seem worse than you are? What if you looked at yourself without the rotation, without the projection, without creating that second self to judge you? These questions won't solve every problem, but they'll help you see where you're adding complexity that doesn't need to be there, where you're creating confusion by imposing a frame that doesn't fit, where you're flipping something in your mind and then blaming reality for the flip. The mirror paradox is a metaphor for so much of human experience. We encounter a neutral world, and we project onto it our own structure, our left and right, our front and back, our sense of self and other. And then we forget we did the projecting. We mistake our map for the territory. We think the flip is out there when it's in here, and the beautiful thing, the hopeful, powerful, liberating thing, is that once you see it, you can't unsee it. Once you catch yourself creating the flip, you start to see all the other flips you create, all the other ways you impose your perspective on reality, and then forget you did it. And that awareness doesn't make you detached or cynical. It doesn't mean nothing is real. It means you have more freedom, more choice, more power to navigate your experience consciously instead of being buffeted by confusion you don't understand. You're not trapped by the mirror. You're not gaslit by the universe. You're just human, with a human mind, doing what human minds do. Building models, creating meaning, projecting perspective. And now you can see yourself doing it. You can watch the construction in action. You can appreciate the incredible sophistication of your own perception, while also recognizing its limits. That's wisdom. Not knowing everything, but knowing what you're doing, knowing how your mind works, seeing the tools you use to navigate reality and understanding when those tools are helping and when they're hindering. Let me bring this back to where we started. I told you about the kid with the toy car, how he saw the reflection as just the same car over there. No flip, no confusion, just a straightforward reflection. And I wondered, when did I lose that simplicity? When did I start seeing a flip that isn't there? The answer is, when I learned to model other people, when I developed theory of mind, when I started imagining what it's like to be someone else, to see from their perspective, to have their orientation. That's a developmental milestone. Kids learn it around age 3 or 4. Before that, they're egocentric, not in a selfish way, but in a literal way. They can't easily imagine someone else's viewpoint. They assume everyone sees what they see, knows what they know. But then something shifts. They start to understand that other people have different perspectives, that someone standing across from them sees the room from a different angle, that someone can look at the same object and see it differently. And that's when mirrors start to feel flipped, because now when you look at your reflection, you don't just see an image, you imagine a perspective, you create an other, you model the reflection as having its own viewpoint, its own left and right. So the confusion, the paradox, is actually a sign of cognitive sophistication. It's proof that you can imagine multiple perspectives at once, that you can mentally rotate yourself into someone else's position, that you have empathy in the deepest sense. The kid with the toy car will grow up and start seeing the flip. And when he does, it'll mean his brain has developed a powerful new capability. He'll be able to understand people better, cooperate more effectively, navigate social situations with more nuance. But he'll also lose something. He'll lose the simplicity of seeing things as they are, without the overlay of imagined perspectives and projected identities. And maybe, just maybe, by understanding the mirror paradox, by seeing how and why the flip happens, he can get some of that simplicity back. Not by regressing to a childlike egocentric state, but by evolving to a more conscious, aware state, where he can hold both perspectives at once, the direct experience of the reflection and the imagined experience of the other. That's the goal. That's the transformation I'm offering you. Not to choose between seeing the flip or not seeing it, but to see it and understand it, to experience it and also to see through it, to live in your human perspective, while also recognizing it as a perspective, not as absolute truth. This is what it means to be awake, to be conscious, to be free. Not to escape your human nature, but to understand it so deeply that you can work with it instead of being confused by it. You started this video thinking mirrors were weird. Now you know, mirrors are perfectly simple. They reverse depth. That's all. The weirdness is in you, in your magnificent, powerful, sometimes confusing mind that builds entire worlds out of reflected light. And there's nothing wrong with that weirdness. It's what makes you human. It's what lets you connect with other people, imagine other possibilities, create art and science and meaning from the raw material of sensation. The confusion isn't a flaw, it's a feature. It shows you how hard your brain is working, how many layers of interpretation and imagination it's adding to create the seamless experience you call reality. And now that you see it, now that you understand it, you have a choice. You can keep living inside the model, taking it for granted, getting confused when it seems to contradict itself. Or you can step back, see the model as a model, appreciate it for what it is, and navigate reality with more clarity and less confusion. The mirror isn't lying to you. The universe isn't tricking you. You're just noticing the moment when your mind builds perspective from nothing. And that noticing, that awareness, is the beginning of real understanding. You don't need to take anyone's word for anything. You can figure it out yourself. You can see through your own illusions. That's what thinking is. That's what freedom is. You came here confused about mirrors, But what you're leaving with is something bigger, a lens for seeing how your mind works, a practice for catching yourself in the act of creating reality, a reminder that you're more powerful than you think, not because you control the outside world, but because you have insight into your own inner world, into the machinery that builds your experience. And that insight doesn't just apply to mirrors, it applies to everything. Every moment when you feel confused, when reality seems contradictory, when the universe seems to be breaking its own rules, that's an opportunity, an invitation to look closer, to ask what you're assuming, to notice which axis you're rotating around, to see where you're projecting and where you're perceiving. This is the practice of a lifetime. Not something you do once and then you're done, but something you return to again and again. Every time you look in a mirror, every time you encounter confusion, every time you want to see more clearly. If this video helped something click for you, if you felt that little spark of clarity when the paradox dissolved, do me a favor and hit the like button. It tells YouTube that this kind of deep, weird exploration is worth showing to more people. And if you want more videos like this, where we take something you thought you understood and reveal the hidden strangeness underneath, subscribe. Because there's so much more to explore. Every assumption is a door. Every paradox is an invitation. Drop a comment and tell me, what's another everyday thing that you've always found confusing but never questioned? I read every single one, and honestly, your questions are the best part of this whole thing. They show me what people are curious about, where the confusion lives, what matters to you, and that helps me figure out what to explore next. Thanks for sticking with me through this. It means something to me that you spent this time thinking deeply about something as simple as a mirror. Most people don't do that. Most people accept confusion as just part of life. But you didn't. You wanted to understand, and that curiosity, that willingness to look closer, to question, to think, that's the most valuable thing you have. Now go look in a mirror and notice. Notice the moment when your brain creates the flip. Notice the imaginary rotation. Notice the other you're projecting into the glass. And smile because you just caught yourself building reality. You just saw the seams in your own perception. And once you see them, you can't unsee them. And that's a gift. That's clarity. That's freedom. Welcome to seeing more clearly. Welcome to understanding your own mind. Welcome to the beginning of real wisdom.
There's a symmetry in the laws of physics that's almost perfect. Almost. You can run most equations backward and forward and they work just fine. Electrons, gravity, motion, time doesn't care which direction you point. Except for one thing. One tiny, stubborn exception that breaks the whole beautiful pattern. And that exception? It's everywhere. It's in your coffee getting cold. It's in your body aging. It's in every breath you take. The universe has a direction, and it's not because of some cosmic rule written in the sky. It's because of cups breaking. And that changes everything about what's possible. Now, I know what you're thinking. You've heard about time travel. You've seen the movies, read the stories, maybe even read some pop science articles about wormholes or rotating black holes or quantum this and that. And somewhere in the back of your mind, you've got this idea that time travel is impossible right now, sure. But maybe someday, with the right technology, with some clever trick we haven't thought of yet, maybe then we could do it. Maybe then we could go back. And I'm here to tell you something that might disappoint you at first, but I promise by the end of this, it's going to give you something better than false hope. Time travel backward isn't a matter of engineering. It's not waiting for better technology. It's not about finding enough energy or discovering some loophole in the equations. It's impossible in a much deeper, much more fundamental way. And the reason why tells us something profound about what it means to be alive, to remember, to exist in this universe at all. See, you've been lied to. Not by the science fiction writers. They're just trying to tell good stories. And I love a good story. You've been lied to by the way we talk about physics itself. We make it sound like time is just another dimension, like space. We say space-time as if time is just another direction you could walk in if you had the right vehicle. We talk about Einstein and relativity and bending space-time, and we make it sound like the only thing stopping you from visiting yesterday is that we haven't figured out the trick yet. But that's not the real barrier. The real barrier is something you witness every single day of your life and never think twice about. It's something so ordinary, so mundane, that it's invisible. And yet, it's the most powerful force governing your entire existence. It's called entropy. And entropy is why you can't go home again. Not metaphorically, literally, physically, thermodynamically. Let me tell you what entropy really is, and why it matters more than anything else when we talk about time. Entropy is often described as disorder, and that's fine as far as it goes. But it's not quite right. Entropy is really about possibilities. It's about how many different ways the atoms and molecules in a system can be arranged, while still looking basically the same from the outside. High entropy means there are a lot of ways to arrange things. Low entropy means there are very few ways. Think about it like this. You've got a bedroom. When it's perfectly clean, everything in its place. That's low entropy. There's basically one way for it to be that clean. Everything in exactly the right spot. But a messy room? There are millions of ways for a room to be messy. Clothes on the floor here, or over there, or draped on the chair, or half under the bed. Books scattered this way, that way, any which way. You see what I'm saying? There are vastly more messy configurations than clean ones. That's entropy. That's the difference between special and generic, between ordered and disordered, between rare and common. And here's the thing about the universe. It's always, always, always moving from special configurations to generic ones, from rare to common, from ordered to disordered, from low entropy to high entropy. Not because there's a law that says, thou shalt increase entropy, but because it's a statistical fact. If you have a system that can be in a million different states, and only one of those states is organized, then random changes are going to push you toward the other 999,999 states. Every single time. It's just math. It's just probability. This is what we call the second law of thermodynamics, and it's the closest thing physics has to an absolute certainty. Entropy increases, disorder increases, the special becomes generic. The organized becomes chaotic. And this right here, is the arrow of time. This is why time has a direction, not because of some mystical property of time itself, but because the universe started out in an incredibly special, incredibly low entropy state, the Big Bang, and it's been evening out ever since. We're living in the aftermath of that initial specialness, watching it slowly, inexorably dissolve into randomness. Now here's where it connects to time travel, and here's where your heart might sink a little bit, but stay with me. To travel backward in time, really backward, not just to look at old photographs or remember things, but to actually go back and exist in a previous moment, you would need to reverse entropy. Not just for you, but for everything you interact with. You'd need every molecule of air you displaced to find its way back to where it was, every photon of light that bounced off your body to return to its source, every sound wave you created to unpropagate, every bit of heat you generated to flow backward into you. You'd need the entire universe, or at least your entire causal past, to run in reverse. And here's the statistical reality of that. It's not impossible the way a law forbids something. It's impossible the way flipping a coin 1 billion times and getting heads every single time is impossible. Could it happen? Technically, yes. Will it happen? No. Not in the lifetime of the universe. Not in 1 trillion lifetimes of the universe. The odds are so monumentally, incomprehensibly against it that calling it impossible is actually being generous. Let me make this concrete for you because I think abstractions don't really hit you in the gut the way they should. Let's talk about something simple, something you've seen happen 1,000 times and never thought about. Let's talk about a cup breaking. Picture this. I'm standing in my kitchen one morning, and there's a ceramic cup sitting on the edge of the counter. It's blue, hand-painted, one of those cups you pick up at a craft fair and use every day until it becomes part of your routine. I reach for it, my hand fumbles. I'm not fully awake yet, you know how it is, and the cup tips over the edge. For a fraction of a second, it's in free fall, and my brain registers what's about to happen, but my hand can't move fast enough to catch it. And then it hits the tile floor, and it shatters. Not just breaks, shatters, into 47 pieces. I know because I counted them when I was sweeping up. Now, in that moment, something irreversible happened. And I don't mean irreversible in the sense that it would be hard to glue it back together, though it would be. I mean irreversible in a much deeper sense. The universe just moved from one configuration, cup whole, sitting on the edge of the counter, to a different configuration, cup broken, 47 pieces scattered across the floor. And here's the thing, there are vastly, overwhelmingly, incomprehensibly more ways for a cup to be broken than for it to be whole. Think about it. When the cup is whole, all the molecules have to be arranged in one very specific pattern. The clay particles have to be bonded in exactly the right way. The shape has to be maintained. There's basically one way for it to be that specific cup. But broken? Oh, there are so many ways to be broken. 47 pieces, or 48, or 46. Big pieces here, small shards there. Scattered in this pattern or that pattern. Rotated this way or that way. Even at the molecular level, the crack patterns could go a million different ways. The number of possible broken configurations is astronomically larger than the number of whole configurations. So when the cup falls and shatters, what's really happening is that it's transitioning from a rare, special, low-entropy state, wholeness, to one of the vastly more common, generic, high-entropy states, brokenness. And statistically, overwhelmingly, the universe always makes that transition, from special to generic, from low entropy to high. That's the arrow. That's time's direction, expressed in ceramic shards on a kitchen floor. Now here's where it gets really interesting. After the cup breaks, I'm standing there looking at the pieces, and I have this feeling. You know the feeling. It's not just annoyance or regret about losing the cup. It's something deeper. It's the immediate visceral knowledge that I will never drink from that cup again, that this is permanent, that something is gone. And that feeling, that sense of irreversibility, that's not just emotion, that's your nervous system registering a truth about thermodynamics. That's you feeling the arrow of time. Because here's what would have to happen for that cup to spontaneously reassemble. All 47 pieces would have to, by random thermal motion, happen to move in exactly the right directions, at exactly the right speeds, and collide in exactly the right orientations to bond back together. The shattered molecular bonds would have to happen to reform in precisely the original configuration. The kinetic energy of the impact would have to flow backward out of the scattered pieces and into the cup as a whole, lifting it up off the floor and setting it gently back on the counter. Every sound wave from the crash would have to converge back on the impact site. Every tiny bit of heat generated by the friction and deformation would have to flow backward. What are the odds of this happening? Well, let's think about it. We're talking about billions of molecules, all of which would have to spontaneously coordinate their motion in the right way. If we calculated the actual probability, we'd get a number so small you couldn't write it down with all the atoms in the observable universe as digits. It's not just unlikely. It's so unlikely that it defines what we mean by impossible. And yet, and this is the beautiful, strange thing, the fundamental laws of physics don't actually forbid it. Newton's laws of motion work just as well backward as forward. If you could reverse the velocity of every single particle in the universe at once, the cup would reassemble. The coffee would flow back into it, and time would run backward, and you'd never know it, because your brain would run backward too, and you'd unremember the whole thing. The equations don't care. The equations are symmetric. So where does the asymmetry come from? Where does the arrow of time come from, if not from the laws themselves? It comes from the initial conditions. It comes from the fact that the universe started in a very special, very low entropy state at the Big Bang. And ever since then, it's been exploring all the vastly more numerous high entropy states available to it. We're riding the wave of that initial specialness dissolving into genericness, And that wave only goes one direction because there are so many more generic states than special ones. Let me give you another way to think about this because I want you to really feel the weight of these numbers. Imagine you've got a deck of cards and it's in perfect order. Ace of spades, two of spades, three of spades, all the way up through the suits in sequence. That's a low entropy state. There's one way to be in that exact order. Now you shuffle the deck once. How many possible shuffled arrangements are there? The answer is 52 factorial. That's 52 times 51 times 50 times 49, all the way down to 1. If you calculate it out, it's about 8 times 10 to the 67th power. That's an 8 followed by 67 zeros. To give you a sense of how big that number is, if you shuffled a deck of cards once per second, every second since the Big Bang, that's about 13.8 billion years, you would have done about 4 times 10 to the 17th shuffles. You wouldn't even be close to exploring all the possible arrangements. Not even remotely close, you'd have sampled a tiny, infinitesimal fraction of the possibility space. And here's the kicker. If you shuffled randomly, what are the chances you'd ever see that original ordered arrangement again? Essentially 0. Not actually 0, but so close to 0 that the difference doesn't matter. That's your life. That's every moment you've ever lived. You're starting from a relatively ordered state, a living body, organized cells, structured memories, coherent thoughts, and every passing moment is a shuffle. Molecules mix and don't unmix. Cells divide and age and die. Neural pathways fire and change. Memories form and fade. You're constantly transitioning from the relatively special configuration you were a moment ago to one of the vastly more numerous configurations available to you in the next moment. And statistically, overwhelmingly, you never ever shuffle back to a previous state. The arrow of time is just the fact that there are more ways to be shuffled than to be ordered. This is what's happening in your coffee cup right now as it cools. The hot coffee molecules are spreading their energy out into the room, into the air, into the ceramic. There are vastly more ways for that energy to be spread out than concentrated in the liquid. So it spreads. It always spreads. It never spontaneously unspreads and makes the coffee hot again. Not because heat can't flow from cold to hot. It can, in principle, but because the number of molecular configurations where it does that is so vanishingly small compared to the number where it doesn't, that you'll never, ever see it happen. And this is happening in your body, too. Right now, as you sit there listening to me, your cells are burning glucose, generating heat, creating entropy. You're radiating warmth into the world. You're breathing out carbon dioxide that will never spontaneously reassemble into oxygen and sugar. You're aging. Your telomeres are shortening. Your proteins are degrading. Your DNA is accumulating tiny errors. You're moving from the special ordered state of youth to the more generic disordered state of age. And eventually you'll move to the most generic state of all, which is death. Which is just the state where your body's molecules are no longer organized enough to maintain the patterns we call life. This sounds grim, I know. It sounds like I'm telling you that everything is falling apart and there's nothing you can do about it. And in a sense, that's exactly what I'm telling you. Everything is falling apart. The technical term is heat death. Eventually, the universe will reach maximum entropy, where every bit of energy is evenly distributed, where there are no more gradients, no more differences, no more organization, and therefore no more life, no more thought, no more anything. Just a thin, cold, uniform soup of particles that will persist for eternity without change. That's where the arrow of time is pointing. That's the ultimate destination. But before you sink into existential despair, let me tell you why this is actually beautiful. Why this is actually the most important thing you could possibly understand about being alive. Because here's the thing. Without the arrow of time, without entropy, you couldn't exist at all, not even in principle. Memory requires the arrow of time. Think about what it means to remember something. It means that some event in the past caused a change in your brain. Neurons fired, connections strengthened, proteins were synthesized, and that change persists into the present. That's a record. That's information stored in the physical structure of your brain. But creating that record requires energy. It generates heat. It increases entropy. Memory only works in one direction because recording is thermodynamically irreversible. If time ran backward, your memories would unform, the proteins would unsynthesize, the neural connections would unstrengthen. The record would be erased. You wouldn't experience going backward through time because you wouldn't remember the future you came from. You'd just be in the past experiencing it forward for the first time again. There's no such thing as remembering forward. Memory is fundamentally asymmetric in time, and it's not just memory. Causation itself requires the arrow of time. We say that A causes B, that striking a match causes it to light, that dropping a cup causes it to break. But what we really mean is that A comes before B in time, and A's occurrence makes B more likely. The arrow of causation points the same direction as the arrow of time, and both of them point in the direction of increasing entropy. The match lights because combustion is a high entropy process. The cup breaks because there are more ways to be broken. So here's the profound thing. You are not separate from the arrow of time. You are a manifestation of it. Your ability to think, to remember, to experience one moment following another. All of that is the arrow of time expressing itself through the particular organization of molecules we call your body and brain. You are a temporary eddy in the universal flow from order to disorder. A little pocket where complexity and organization arise for a brief while before dissolving back into the general chaos. And the fact that you can know this, can understand this, can reflect on your own temporariness. That's maybe the most beautiful and strange thing in the entire universe. Now let's bring this back to time travel, because I want you to see why all of this makes backward time travel not just difficult but meaningless in a deep way. Imagine you had a time machine. Imagine you could somehow generate enough energy, manipulate space-time in the right way, and transport yourself physically to the year 1995. What would that mean? What would that look like? Well, first, you'd have to reverse the entropy of your entire body. Every cell would have to unage back to its 1995 configuration. Every memory you've formed since then would have to unform. You'd arrive in 1995 with no knowledge of anything that happened after, because those memories are physically encoded in neural structures that didn't exist in 1995. So the you that arrives wouldn't be the you that left. It would be the you from 1995, experiencing 1995 for the first time. There's no sense in which you've gone back because the information that constitutes your present self can't exist in that past state. But it's worse than that, because you're not thermodynamically isolated. You're constantly exchanging energy and particles with your environment. So, to put you back in 1995, we'd also have to put back every bit of air you've breathed since then, every photon that's bounced off you, every sound wave you've created. We'd have to reverse the entropy of everything in your causal past, which is, basically, the entire universe. We'd have to unburn every log that's been burned, unmix every drink that's been stirred, unbreak every cup that's been broken between now and 1995. And even if we could do that, even if we had the godlike power to reach into the universe and set every particle's velocity in reverse, what would happen is that the universe would run backward for A, while we'd reach 1995, and then what? It would just keep running backward unless we stopped it. And if we stopped it and let it run forward again, it would just re-evolve forward toward the present. You wouldn't experience any of this as time travel. You'd just experience time running forward from 1995 onward, same as before, with no memory of the future, because that information doesn't exist in the 1995 state. Do you see what I'm getting at? Time travel backward is not just technologically impossible. It's conceptually incoherent given what we know about entropy and information. The past is not a place you can visit, because the past is not a place. It's a configuration of matter and energy that no longer exists. It's been scrambled. It's been mixed. It's been incorporated into the high entropy present. The information that defined that moment has been radiated away as heat, dispersed into the environment, lost forever to the randomness of thermal motion. You know what the past really is. It's a memory. It's a low-fidelity record stored in your brain, in photographs, in written documents, in geological strata, in the cosmic microwave background radiation. But it's not the thing itself. The thing itself is gone. It's become something else. And there's no way to unbecome, no way to unscramble the egg, no way to reassemble the broken cup, no way to extract the original signal from the noise it's dissolved into. And here's where we get to something I think you need to hear, something that might actually come as a relief, even though it sounds harsh at first. You cannot go back to who you were. You cannot unsay the words you said. You cannot unmake the choices you made. You cannot return to the version of yourself that existed before the trauma, before the loss, before the mistake, before the change. That person is gone, not metaphorically, thermodynamically. The specific configuration of molecules and memories and neural patterns that made you that person. You have become someone else, and you will keep becoming someone else with every passing moment, and there is no mechanism in physics that will reverse this. Now, I know that might hurt to hear, especially if you're carrying regret, if you're haunted by the past, if you're wishing desperately that you could go back and do things differently. But here's the thing. The impossibility of return is what makes the present matter. If you could go back, if you could always undo, if you could constantly revise, then nothing would ever be real. No choice would ever be final, no moment would ever be precious, no loss would ever mean anything because you could always recover what was lost. The arrow of time gives weight to your life. It makes your choices matter because they can't be unmade. It makes the people you love precious because you won't have them forever. It makes this moment, this specific, unrepeatable configuration of matter and energy we call now, the only place where anything real can happen. The past is gone. The future doesn't exist yet. All you have is this, and paradoxically, that limitation is what makes this meaningful. Let me tell you about something I think about a lot. It's about ice cubes. You drop an ice cube in a glass of warm water, and you watch it melt. The cold spreads out through the liquid. The crystalline structure breaks down. The sharp edges soften and disappear. Within a few minutes, it's gone. Just slightly cooler water, slightly more of it. The ice cube has become something else. Now I want you to imagine that process running backward. The water suddenly getting colder in one spot. The molecules spontaneously arranging themselves into a perfect lattice. The ice cube forming out of nothing, growing, becoming solid and clear and cold. Can you picture it? No, you can't. Not really. Your brain rebels against it. It knows at some deep intuitive level that this is wrong. That water doesn't do this. That time doesn't flow that way. And here's what I find beautiful about this. Your intuition is correct. You know something true about the universe that no one had to teach you. You've internalized the second law of thermodynamics just by living in a world governed by it. You've watched things melt and mix and break and cool over and over your whole life and never once seen the reverse, and your brain has learned the pattern. The arrow of time is not an abstract concept to you. It's a felt reality. It's in your bones. Children know this too. You show a child a video of a glass breaking and then play it backward, and they laugh. They know it's wrong. They know glasses don't jump back together. They haven't studied physics. They haven't learned about entropy. They just know the way you know which direction is down. The arrow of time is that fundamental. It's part of the basic grammar of reality, and yet most of us spend our lives fighting against it, wishing we could go back, wishing we could undo, wishing we could stop the ice from melting, the coffee from cooling, the body from aging, the moment from passing. We're nostalgic for the past and anxious about the future, and we're never quite here, in the present, which is the only place time's arrow is actually pointing. But here's what I want you to understand. The fact that you can't go back is not a limitation to be overcome. It's the structure of reality itself. And once you really accept that, once you stop fighting against it, something shifts. You start to see that the present moment is not a way station between the past you're mourning and the future you're worried about. It's the only moment that exists. It's where you actually are, and it's where you have the only power you'll ever have, the power to choose what you do with this specific, irreversible configuration of now. There's a question people ask me sometimes, especially after they've been reading pop science articles about quantum mechanics. They say, but what about particles going backward in time? What about antimatter being regular matter moving backward through time? What about quantum entanglement and time-symmetric equations and all that stuff? And it's a good question. It's true that at the quantum level, things get weird. Particles can exist in superposition, effects can appear to precede causes, and the mathematics of quantum mechanics is largely time-symmetric. But here's the thing. Quantum weirdness doesn't save you from entropy. It doesn't give you a back door to the past. Because the moment you try to use quantum effects to do anything macroscopic, anything involving human-scale objects like your body or a time machine, you run into decoherence. The quantum superposition collapses. The system becomes classical, and classical systems obey thermodynamics. They increase entropy. They have an arrow of time. You can't hide in the quantum realm to escape entropy, because you're not a quantum system. You're a huge, macroscopic collection of trillions of particles that are constantly interacting with the environment, radiating heat, exchanging photons, generating information. You're about as far from a closed, reversible quantum system as it's possible to be. You're an open, irreversible thermodynamic system. And for open thermodynamic systems, the arrow of time is absolute. Even if somehow, through some miracle of technology or cosmic coincidence, you could arrange for your particles to quantum tunnel backward through time, you'd arrive without your memories, without your identity, without anything that makes you you, because all of that is stored in macroscopic structures that can't tunnel. You'd be a collection of atoms in the past with no coherent organization. Not a person, not a consciousness, just scattered matter that happens to have the same particles you have, but not in any configuration that means anything. The more you think about it, the more you realize that asking, can we travel back in time, is kind of like asking, can we unstir the milk from the coffee? In principle, if you knew the exact position and velocity of every molecule and could precisely manipulate them all, you could do it. But in practice, the information about which molecules were milk and which were coffee is lost. It's radiated away as heat. It's dispersed into noise. It's gone. And no amount of clever engineering can recover information that's been lost to entropy. This is what physicists mean when they talk about information loss. It's not that the information ceases to exist in some abstract sense. The molecules are all still there, somewhere. It's that the information becomes inaccessible. It gets scrambled into correlations that are too complex, too dispersed, too degraded to be reconstructed. The signal disappears into the noise, and once it's gone, it's gone. There's no undo button in thermodynamics. Now I want to talk about something that might seem like a tangent, but I promise it's not. I want to talk about regret, because I think regret is what happens when you bump up against the irreversibility of time at a human level. Regret is the feeling of wanting to go back, of wishing you could undo, of desperately yearning for a past configuration that no longer exists. And here's what physics tells us about regret. It's based on a misunderstanding of what time is. When you regret something, you're implicitly imagining that there's a version of the past that could be accessed and changed. That if only you had a time machine, if only you could go back, you could fix it. You could choose differently. You could save what was lost. But the past isn't a place where different choices are waiting to be made. It's a configuration that has already dissolved into the present. The choice you made is part of the causal chain that led to the you sitting here right now. You can't extract it without unraveling everything that came after, including yourself. This doesn't mean you can't learn from the past. It doesn't mean you can't wish things had gone differently. But it does mean that the past is not an option. It's not on the table. The only thing on the table is what you do next, in this moment with the configuration you've got. And that's actually incredibly freeing once you let it sink in. Because if you can't go back, then you're released from the burden of trying. You don't have to spend your energy wishing for the impossible. You don't have to torture yourself with counterfactuals about how things could have been different. They couldn't have been different because different would require a different past, and the past is fixed, not by decree, but by entropy. It's scrambled, it's mixed, it's gone. What you can do, the only thing you can do, is accept the present configuration and decide what you're going to build with it going forward. Because the future is not yet determined. The future is the space of all possible configurations you could evolve into from here, and while entropy guarantees that overall disorder will increase, it doesn't specify the path. There are many ways to increase entropy. Some of them involve creating beauty, meaning, connection, order in local pockets even as the universe as a whole becomes more disordered. You are one of those local pockets. You are a temporarily organized system extracting energy from your environment and using it to build structure, to grow, to think, to create, to love. And yes, eventually that organization will break down. Your body will fail, your consciousness will end, the molecules that make you will disperse and become parts of other things. That's entropy. That's the arrow. That's the price of having been alive at all. But right now, in this moment, you have the astonishing privilege of being a pattern that knows it's a pattern. A temporary ordering of matter that can reflect on its own temporariness. A tiny, brief violation of the universe's general trend toward disorder. And what you do with that, what you create, what you love, what you contribute to the other temporary patterns around you, that matters. Not because it will last forever. Nothing lasts forever. But because it's happening now in the only time that exists. Let me tell you about one more thing, and then I want to give you something practical, something you can actually do with all of this. I want to talk about Einstein because people always bring up Einstein when we talk about time. And yes, Einstein showed us that time is relative, that it flows at different rates depending on velocity and gravity, that simultaneity is not absolute, that space and time are woven together into a four-dimensional fabric that can bend and warp. And this is all true. It's been confirmed by countless experiments. GPS satellites have to account for relativistic time dilation, or they'd give you wrong directions. We've measured time passing slower on mountaintops than in valleys. We've seen particles live longer when they're moving fast. Time is definitely not the simple, universal, ticking clock Newton thought it was. But here's what Einstein didn't give us. He didn't give us a way to reverse entropy. He showed us that different observers can disagree about the order of events, that time can stretch and compress, that you can take different paths through space-time. But all of those paths still point from low entropy to high entropy. The arrow of time persists even in relativity. Your clock might tick slower if you're moving fast, but your coffee still cools, your body still ages, your memories still form in one direction only. There are solutions to Einstein's equations that allow for closed time-like curves, paths through space-time that loop back on themselves so that you could, in principle, travel into your own past. Wormholes, rotating black holes, certain exotic configurations of matter and energy. These are mathematically valid solutions. But they all require conditions that probably don't exist in our universe, and even if they did, they don't solve the entropy problem. You'd still be a thermodynamic system increasing entropy as you move along your world line, even if that world line loops back. And there's something deeper, something that makes me skeptical that these solutions are physically real, even if they're mathematically allowed. Because if backward time travel were possible, even in principle we'd expect to see evidence of it. We'd expect to see entropy decreasing in places. We'd expect to see cups spontaneously reassembling. We'd expect to see time travelers from the future showing up in our past. And we don't. We never have. The arrow of time is unbroken everywhere we look. Maybe there's a consistency principle in the universe, that forbids closed time-like curves. Maybe the quantum vacuum fluctuations in the loops make them unstable. Maybe information conservation prevents it. We don't know for sure. But the evidence of our senses, the evidence of every experiment ever done, is that time flows one way. From past to future, from order to disorder, from birth to death, from the Big Bang to the heat death. And there are no exceptions. So where does that leave us? What are we supposed to do with this knowledge that the past is inaccessible, that time only goes forward, that entropy always increases, that nothing lasts, that everyone we love will die, that every work will crumble, that the universe itself will eventually run down into cold, dark nothing? Here's what I think. I think we're supposed to be here, fully here, in this moment, because this moment is the only place you actually exist. The past version of you is gone. It's been recycled into the present you, and the future version of you doesn't exist yet. All that exists is this breath, this heartbeat, this thought, this specific, unrepeatable, irreversible configuration of matter and energy that is you, right now, aware of itself. And being here, really being here, means accepting that you can't control the direction of time. You can't stop the entropy increase. You can't prevent the losses that are coming, but you can choose what you do within the constraints you have. You can choose what kind of order you create in your local pocket of the universe before it dissolves. You can choose how you treat the other temporary patterns around you. You can choose what meaning you make out of your brief existence. Let me give you some things you can actually do. Some practices that come out of understanding entropy and irreversibility, not as depressing limitations, but as the very structure that makes your life meaningful. First, notice irreversibility. Pay attention to it. Watch an ice cube melt in a glass of water. Really watch it. See how the sharp edges soften, how the cold spreads, how the boundary between ice and water blurs, and then disappears. Notice that this process only goes one direction. The water never spontaneously freezes back into a cube. Let this train your intuition. Let it remind you that the universe has a direction and you're moving in it, always, whether you like it or not. Do this regularly, once a day or once a week. Find some irreversible process, coffee cooling, sugar dissolving, bread toasting, ice melting, and watch it. Be present with it. Let it teach you about time. Let it teach you about impermanence, not in an abstract philosophical way, but in a direct, sensory way. This is what time looks like. This is what never going back feels like. This is reality. Second, make peace with closed doors. Think of one thing from your past that you wish you could change, one moment you wish you could return to, one choice you wish you could unmake, one person you wish you could see again. Feel the longing. Let yourself feel it fully, and then say to yourself, that configuration is gone, not metaphorically. The specific arrangement of molecules and energy and information that made that moment is now scattered across the universe in a trillion pieces. I cannot recover it. I cannot go back. And that's not because I'm weak or because I'm not trying hard enough. It's because going back is thermodynamically impossible. And then, this is the crucial part, let yourself grieve the loss without trying to fix it, because you can't fix it. The loss is real. The past is really gone, and pretending otherwise or holding out hope for some impossible reversal just keeps you from being where you are, which is here, in the present, in the only moment where you have any power at all. Third, practice presence through physics. When you notice yourself lost in nostalgia or regret, mentally rehearse this: the past is high entropy now. It's been scrambled, it's been mixed into the present. I can't extract it, but I can choose what I do with this present configuration. I can choose where I put my attention, how I spend my energy, what order I try to create in my local environment before entropy claims it too. This isn't toxic positivity, this isn't pretending the past doesn't matter. It's acknowledging that the past has become the present, and the present is where your life actually is. You're not in yesterday. You're not in last year. You're here. And here is where everything real happens. Fourth, create deliberately while knowing nothing lasts. This might be the hardest and most important one. Make something this week knowing it will eventually be destroyed. It could be anything. A meal that will be eaten. A sandcastle that the tide will erase. A drawing that will fade. A conversation that will be forgotten. A moment of kindness that will ripple out and eventually dissipate into the noise of the world. Let yourself feel the poignancy of its temporariness. Let yourself create it beautifully anyway, because this is what it means to be alive in a universe governed by entropy. You're not building monuments. You're not creating eternal things. You're making temporary eddies of order in the stream of chaos. And that's enough. That has to be enough. Because it's all there is. The universe is running from order to disorder, from the Big Bang to the heat death, from low entropy to high. And you're a brief flicker of consciousness in the middle of that vast unwinding. But you're a flicker that can know what it is, a pattern that can appreciate other patterns, a temporary ordering that can love other temporary orderings. And for a little while, before entropy reclaims you, you can make choices that matter precisely because they can't be unmade. So here's what I want you to take from all this. Time travel isn't impossible because we haven't discovered the trick yet. It's impossible because the past is not a place. It's a dissolved configuration. The broken cup doesn't just refuse to reassemble out of stubbornness. It refuses because there are vastly more ways to be broken than whole, and the universe always explores the more numerous possibilities. You can't go back because back has become now. The atoms that made your childhood self are still here, but they've been shuffled. They've been breathed and eaten and dispersed. Some of them are in you. Some of them are in other people. Some of them are in the air and the soil and the ocean. The pattern that was you at 7 years old is gone. Not tragically, thermodynamically. And the you that you are right now is also temporary. Tomorrow's you will be a different configuration. Slightly aged, slightly changed, a few more memories formed, a few more cells replaced. You're not a fixed thing traveling through time. You're a process, a pattern that persists for a while by constantly replacing its parts, like a whirlpool in a stream. The water that makes the whirlpool is always changing, but the pattern remains for a time, until it doesn't. This is what the broken cup reveals. Not just that time has a direction, but that you are that direction. You are the arrow. You are the process of order becoming disorder, of specialness becoming genericness, of life becoming death. And knowing this, really knowing it, doesn't make life meaningless. It makes every moment precious, because it's unrepeatable, irreplaceable, and irreversible. You're not broken for living in a universe where everything tends toward brokenness. You're alive. You're conscious. You're here. And here is miraculous enough. You know what I think about sometimes? I think about the fact that the atoms in my body were once inside stars. They were forged in nuclear furnaces billions of years ago, scattered across space in supernova explosions, condensed into planets, cycled through oceans and atmospheres and countless living things before they became part of me. And someday they'll be part of something else. The carbon in my cells will be in plants, in soil, in other animals, in the air. The pattern that is me will dissolve, but the matter will persist, endlessly recycled in the great thermodynamic flow. I find this comforting in a strange way. I'm not separate from the universe. I'm a temporary configuration the universe is trying on, and when this configuration ends, when entropy claims me like it claims everything, I'll return to the pool of possibility. My atoms will be shuffled back into the deck, and maybe somewhere down the line some of them will be part of another consciousness, another pattern that briefly knows itself before dissolving back into the whole. This is the only immortality that's real. Not the immortality of the soul, not the immortality of fame or legacy, but the immortality of matter and energy, endlessly transforming according to the laws of physics. You can't preserve yourself, you can't freeze the moment, you can't go back, but you can participate fully in the transformation. You can let yourself be part of the flow instead of fighting against it. And maybe that's what wisdom is, not knowing how to escape time, but knowing how to be in it. How to accept the irreversibility without becoming paralyzed by it. How to create and love and strive even though everything you build will eventually fall apart. How to be a temporary ordering of matter that celebrates its own temporariness. The broken cup teaches this better than any philosophy. It shatters and it stays shattered, and you clean up the pieces, and you go on. You don't spend the rest of your life wishing you could glue it back together. You accept that it's gone, and you use a different cup. Because there are other cups. There are other moments. The universe is constantly offering you new low-entropy states to care about, new things to love, new ways to create order before chaos reclaims it. This is what it means to be alive, to be a pattern that knows it won't last. To create anyway, to love anyway, to matter anyway, not despite entropy, but because of it. Because the arrow of time gives weight to your choices, finality to your actions, preciousness to your moments. Without it, nothing would mean anything. With it, everything means something, at least for now, at least while the pattern holds. So here we are. Here you are, in the only moment that exists. The past is gone, scrambled into the present by the relentless increase of entropy. The future doesn't exist yet, just a space of possibilities waiting to be collapsed into actuality. And right now, right here, you have a choice. Not about whether to move forward. You're moving forward whether you like it or not. That's what time does. But about how you move forward. What you create. What you love. What you contribute to the brief, beautiful, temporary order that is human civilization, human consciousness, human life. You're not broken for wanting to go back. You're human. But you can't go back because back has become now, and now is where everything real is. Now is where you are. And that's not a consolation prize. That's the whole game, the only game there is. So let me leave you with this, a kind of mantra, if you want to call it that. Something you can say to yourself when you're feeling the weight of irreversibility, when you're mourning the past, when you're wishing desperately that you could undo or redo or return. You can't go back, not because you're powerless, but because back is a myth. The past is not a place. It's a dissolved pattern, and you are not broken for living in the only moment that exists. You're awake, you're here, and here is where everything real happens. The arrow of time points forward because there are more ways to be ahead than behind, more ways to be broken than whole, more ways to be changed than unchanged. And you are the arrow. You are the change. You are the temporary ordering that knows it's temporary. And that's not a tragedy. That's the human condition. That's what it means to be alive in a thermodynamic universe. So be alive, right now, in this moment, because this moment is all you've got. It's all anyone's got. And it's enough. It has to be enough, because physics says there is no alternative. Now, if this changed something in you, if you're seeing time differently now, if you're feeling the weight and the freedom of irreversibility settling into your bones, I want to hear about it. Drop a comment and tell me about a moment you wish you could return to, and what it feels like to realize you can't. Not because I'm trying to make you sad, but because I think there's something healing in naming it, in acknowledging that the past is really gone and we're all here together in the present, trying to figure out what to do with our brief, beautiful, irreversible lives. And if you want more of this, more physics that matters, more science that touches the heart of what it means to be human, subscribe, hit the like button if this resonated, because I'm here trying to explain the universe in a way that doesn't just inform you, but transforms you in a way that lands not just in your head, but in your lived experience. The universe has a direction, you're moving in it, and you can't go back. But forward is where all the possibility is. Forward is where your life is, so go there, be there, create there, love there, matter there, in the only direction that exists, in the only time there is, right now. Thank you for being here with me. Now go live in the only moment that's real.
Let me draw something impossible on an imaginary blackboard. Here's our universe. All of it, every galaxy, every bit of space. Now I'm going to draw a circle around it. Done. Simple, right? But I just broke physics. Because the moment I drew that circle, I created an inside and an outside. I gave the universe a boundary. But boundaries exist in space, and space is what we just circled. So where did I draw the line? Not in space. There is no there. I just used a piece of chalk and ordinary grammar to create something that can't exist. And yet you understood what I meant. Your brain made a picture. This is the problem. Our language, our visualization, our every instinct is designed for a world with edges, with here and there, with inside and outside. But the universe doesn't care about our design. What I'm about to show you is how to think in a way your brain wasn't built for. You've been asking the wrong question your entire life. Not because you're not smart enough, but because language itself is the trap. Every documentary you've ever watched, every article you've read, every late-night conversation you've had about what's beyond the universe, all of them reinforce this fairy tale that reality is a container with an inside and an outside, that existence is a place you could theoretically leave if you just had a fast enough spaceship or the right mathematical equation. This video isn't going to give you a neat answer you can repeat at parties to sound clever. Instead, it's going to dismantle the entire scaffolding of how you think about boundaries, existence, and yourself. Here's the core pain I want to address because I know you feel it. When you think about cosmic questions like this, you feel small, you feel lost. The universe becomes this massive, cold thing that has nothing to do with you, and you're just this accident, this tiny consciousness waiting around in insignificance until you blink out. And everyone tells you to find meaning despite the void, to make peace with your smallness, to be brave in the face of your own irrelevance. But that's backwards. That's completely backwards. What you're going to walk away with today is an entirely inverted understanding. The universe doesn't have edges because the very concept of inside versus outside only exists because you do. Consciousness isn't a tiny accident in a vast machine. It's the very thing that makes vast and machine and accident possible as concepts in the first place. You're going to stop feeling like you're staring at something alien and separate, and you're going to start recognizing that the mystery of out there and the mystery of in here are the same mystery. You'll gain what I call the observer's relief, the understanding that you're not separate from the question. This isn't comforting in some cheap, feel-good way. It's disorienting first, then liberating. And it'll change how you see everything from your morning coffee to your own mortality. What makes this different from everything else you've encountered? Most explanations either dumb things down into fairy tales, parallel universes as soap bubbles floating in some cosmic bathtub, or they hide behind mathematics so dense you can't feel anything through it. I'm going to do neither. We're going to use thought experiments, paradoxes, and stories that make the weirdness feelable, not just theoretically understood. And I'm going to show you why the weirdness isn't a bug in reality. It's a feature of consciousness trying to look at itself. So stay with me. This is going to get strange, but strange in a way that makes more sense than what you've been told is normal. Let me tell you about a night in Los Alamos in the late 1940s. I was working on the atomic bomb project. Classified work, tense atmosphere, everyone moving around with secrets they couldn't share even with their closest friends. The whole place had this oppressive weight to it, like we were all carrying something too heavy and too dangerous and we couldn't put it down. I needed to get away, not physically. I couldn't leave the compound, but mentally. I needed to feel small in a good way, not in the crushing way that work made me feel small. So one night I snuck away to this tiny observatory they had on the mesa. Nothing fancy, Just a decent telescope and a lot of darkness. New Mexico has some of the darkest skies you'll ever see, especially back then before light pollution ate up half the stars. I lay down on my back on the observation platform, didn't even use the telescope, just stared up at the Milky Way smeared across the black like someone spilled cream, and I had this thought I couldn't shake. If I look far enough out there, am I looking at the past? And the answer is yes, obviously. Light takes time to travel. The stars I was seeing weren't there now in any meaningful sense of the word now. I was seeing where they were hundreds, thousands, millions of years ago. Some of those stars were already dead, but their light was still traveling toward my eyeball, carrying a message from a sender that no longer existed. Then I had another thought, and this one made my stomach drop. What if I could see infinitely far, not limited by light speed or the age of the universe or the sensitivity of instruments, just pure, infinite vision? Would I see the beginning of everything? Would I see the edge? Or would I see something impossible? Would I see the back of my own head? Not literally, of course, but conceptually. If space curves back on itself the way Einstein's equations suggest it might, if time and space are woven together into this single fabric, then out there and back here might not be separate destinations at all. The universe might be more like a Klein bottle than a box. You know what a Klein bottle is? It's this impossible shape where the inside and the outside are the same surface. You can travel along it forever and you never leave. You never find an edge, because the geometry doesn't support edges the way our intuition demands. I felt simultaneously infinite and impossible lying there under those stars, like I was a loop of consciousness trying to step outside itself, but always finding itself still inside. And that's when I realized the question, what's beyond, assumes a geometry that might not exist. It assumes there's a place to stand outside the universe looking in, or inside looking out. But what if there's no outside? What if the question itself is broken? I didn't sleep well that night. Not because I was scared, but because I was exhilarated. I'd found the edge of my own thinking, and it turned out the edge was imaginary. The prison bars were made of grammar. But if there's no edge, you're probably thinking, what happens when the universe expands? What's it expanding into? Hold that question. It's going to get weirder before it gets clear. Let me tell you a parable. Imagine a civilization of perfectly flat beings living on a two-dimensional surface, like drawings on a sheet of paper, except they're alive and conscious. They can move forward, backward, left, right, but up and down don't exist in their experience. They're not just restricted from going up. The direction itself is meaningless to them. They don't have a word for it. They can't imagine it. It's not a limitation of their bodies. It's a limitation of their reality. One day, a Flatlander genius asks a dangerous question. What's beyond our world? The others think she means beyond the edges of their known territory. Uncharted lands, distant continents, so they send expeditions. But she clarifies. No, I mean what's beyond the surface itself? What's on the other side of existence? The others laugh. Some get angry. There is no other side. They tell her. There's just more surface or there's nothing. Those are the only two options. You're talking nonsense. You're confusing people with meaningless questions. But the genius insists. What if our entire reality is curved? What if it's embedded in something we can't perceive? What if beyond isn't ahead of us in any direction we can point, but in a direction we don't have words for, that we can't even conceive of? They think she's lost her mind. But here's the thing. You and I, watching this as three-dimensional beings, we can see what they can't. Their surface might be a sphere. They walk in what they experience as a straight line forever, and they come back to where they started. There is no edge. There is no beyond in their vocabulary. But there is a third dimension all around them that gives context to their curvature. They just can't point to it. They can't walk to it. They can't measure it with their tools. It's not in their space. It's orthogonal to their space. Now here's where it gets personal. We're the flatlanders. When we ask what's beyond the universe, we might be asking about a direction, a dimension, a category of existence that isn't out there in space, in any sense we can visualize. It might be orthogonal to every dimension we experience. And just like the flatlanders can't visualize up, we might not be able to visualize whatever contains or contextualizes our universe. Not because it's not there, but because our consciousness is shaped by the dimensions we're embedded in. And this isn't defeat. This isn't cause for despair. Think about how you'd feel if you could somehow communicate with a flatlander. You wouldn't feel superior in some cruel way. You'd feel curious, amused, compassionate. You'd want to help them understand, even knowing they fundamentally can't visualize what you're describing. Now flip it. What if something relates to us the way we relate to flatlanders? Not as gods, not as supernatural beings, but simply as perspectives that exist in a geometry we can't access. Does that make you feel small? It shouldn't. It should make you feel curious. Because the question shifts from what's out there beyond me to what is the shape of the reality I'm embedded in? And that's a question you can actually work with. So if we can't visualize it, can we at least understand the logic of it? Can we think our way to what we can't see? Let's find out. When I was a kid, maybe 9 or 10 years old, I got obsessed with infinity. Not in a fun way, in a way that kept me up at night, made me anxious, made me feel like I was going to fall through the floor of reality. I'd try to imagine the biggest number, and then I'd add 1, and I'd realize there was no biggest number, and my mind would just spiral. I felt like I was going crazy. My father noticed. He was good at noticing when I was chewing on something I couldn't swallow. One day he took me into the bathroom. We had this old bathroom with small square tiles on the floor, white with black grout, very regular, very orderly. He asked me, "How many tiles do you see?" I counted. Maybe 200, something like that. "Now imagine this floor goes on forever in every direction," he said. "No walls, no end, just tiles forever. Is there a middle tile?" I thought about it. "No," I said. "Every tile could claim to be the center because there's no edge to measure from." "Exactly," he said. "Now imagine the universe is like that. No edge. Every galaxy is in the middle. So when you ask what's beyond, you're imagining walls that don't exist." I felt a little better, but then I asked him, "But this bathroom does have walls. I can see them. You can imagine an infinite floor, but you can't build one. Does that mean infinity is fake? Does it mean it's just in our heads?" And he said something I didn't understand until much later. He said, "Does it mean infinity is fake, or does it mean reality doesn't care what you can build?" That question sat in me for years, because here's the thing. Infinity isn't a place you get to at the end of counting. It's not a destination. It's a category. And treating it like a place you could reach if you just counted long enough is a grammar mistake. It's using a word that applies to journeys and applying it to something that isn't a journey at all. Same with beyond the universe. It's not a location. It's a grammar mistake. We're using spatial language, beyond, outside, edge, to talk about something that might not have spatial properties in the way we need it to for those words to mean anything. Let me break this down more carefully, because this is where most people's brains start to rebel, and I want you to stay with me through the rebellion. Everyone's heard that the universe is expanding, right? It's in every documentary, every science class. The universe is getting bigger. Galaxies are moving apart. Space itself is stretching. And immediately, you can't help it, your brain pictures a balloon inflating into a room. The balloon is the universe. The room is whatever it's expanding into. That picture feels so right, so obvious, that you don't even question it. But here's the problem. There's no room. Space itself is what's expanding. It's not expanding into anything. It's just, and this is the weird part, more space coming into existence, not occupying some pre-existing void, because voids are spatial too, just more space where there wasn't more space before. Let me give you a better picture. Imagine you're on an infinite grid of graph paper. Infinite in all directions, no edges. Every second, the distance between grid lines doubles. You don't move. There's nowhere to move to, because every point on the grid is expanding away from every other point. But everything gets farther apart. That's expansion without an edge, without an outside, without a container. Now here's the thing that makes people's heads hurt. If space is expanding, what about the space it's expanding into? And that question, that perfectly reasonable-sounding question, is exactly the trap, because it assumes space needs a container. But containers exist in space. You can't put space inside space. That's circular. That's like asking what time it was before time existed. The question uses the thing it's asking about as a precondition for the question. The universe doesn't expand into anything because anything implies space, and space is what we're talking about. It's the only in there is. There's no outside, because outside is a spatial concept, and we're talking about the totality of space itself. And this is where the container metaphor completely breaks down. The universe isn't a snow globe. It's not in anything. And your brain hates this because your brain evolved to navigate a world of containers. Boxes, rooms, caves, territories with boundaries. Your survival depended on knowing what's inside the safe zone and what's outside in the danger zone. So your brain defaults to container logic for everything, but reality doesn't care about your defaults. Let me push this further. Imagine there is an edge. Just pretend with me for a second. You build a spaceship. You travel to the edge of the universe. What happens? Do you hit a wall? Okay, what's the wall made of? Walls are physical objects. They occupy space. They have two sides, so there's space on both sides of the wall, which means you haven't reached the edge yet. The edge is beyond the wall. All right, what if there's no wall? What if there's just nothing on the other side? A true void. Absolute emptiness. Well, voids are still spatial. Nothing still occupies 3 dimensions of emptiness. You can measure the void. You can say it's a meter wide, 2 meters, 1 billion light years. It has geometry. So again, you haven't left space. You're still in it. You see the problem? Every time you try to construct an edge, you end up with space on both sides. The concept of edge smuggles in the thing it's supposed to be the edge of. So what's the alternative? One possibility is that space curves back on itself, like the surface of a sphere. If you're an ant walking on a ball, you can walk in a straight line forever. You'll never hit an edge. You'll never fall off. But you're also not walking an infinite distance. Eventually you come back to where you started. The surface is finite but unbounded. Finite means you can measure it. This sphere has a surface area of such and such. Unbounded means there's no edge. There's nowhere you're not allowed to go. And this is hard to visualize in 3 dimensions because we're stuck inside 3 dimensions. But mathematically it works. The universe could have a finite volume but no boundary. You could travel forever and never leave, never find an edge, but also never travel an infinite distance. Does that make sense? It doesn't have to feel intuitive. It just has to be logically consistent. And it is. The math works. Whether it describes our actual universe is an empirical question we're still working on, but the point is, it's possible to have a universe with no edge, no outside, no container, and no infinity. It's just a different geometry than the one your brain assumes. Now I want to talk about something that's going to sound like a detour, but I promise it's not. I want to talk about observation and consciousness and why you can't separate the question from the asker. In quantum mechanics, and I spent a good chunk of my life working on quantum mechanics, trying to make sense of it, trying to make it make sense to other people. There's this thing called the observer effect. It's been misunderstood and mystified and turned into all sorts of nonsense, So let me be clear about what it actually means. Observation changes outcomes. Not because we're magical, not because consciousness has some spooky power over matter, but because observation means interaction, and interaction is physical. When you measure something, you have to touch it, with light, with particles, with fields, whatever, and that touching is a physical event. It changes the system. There's no such thing as a view from nowhere. There's no such thing as looking without affecting. And here's the deeper point. You can't ask what the universe is like when nobody's looking. That question presupposes a perspective outside all perspectives. It presupposes that reality has some definite objective state independent of any interaction, and that consciousness is this separate thing peeking in from outside. But you can't peek in from outside. You're made of the universe. Your consciousness is a pattern the universe is doing. When you ask what's beyond the universe, you're imagining standing outside it, looking back at it like you're looking at a house from the street. But you can't stand outside it. There's no street. There's no vantage point external to existence. You're inside existence by definition, and asking what's outside is like a wave asking what's outside the ocean. Now here's where this gets really interesting, and maybe a little uncomfortable. You are the universe looking at itself and being confused by what it sees. The question, what's out there, is really, what am I in disguise? Because there's no separation. The thing doing the asking and the thing being asked about are the same thing, and that question, what am I, doesn't have an answer you can observe from outside, because you're the observer. You can't step outside yourself to look at yourself objectively. Oh, you can look at your body, your thoughts, your patterns, but the thing doing the looking is always one step back, always unobserved. It's like trying to see your own eyes without a mirror. The seer can't see itself seeing. So the mystery of what's beyond the universe and the mystery of what you are, same mystery. Both are asking about the boundary between inside and outside, observer and observed, subject and object. And both are discovering that the boundary is a useful fiction, not a fundamental reality. Now, why does this matter? Why am I telling you this? Because you've been walking around feeling like you're this tiny, irrelevant speck in a vast, indifferent machine. And I'm telling you that's backwards. You're not a speck. You're not irrelevant. The universe doesn't have meaning without observers, and you're one of them. You're the means by which the universe knows itself. You're how matter becomes aware of matter, how space contemplates space, how existence asks why there's existence. That's not a small thing. That's not irrelevant. That's so significant it's almost unbearable. Let me make another distinction that's going to help clarify things. There's a difference between infinite and unbounded, and most people use those words interchangeably, but they're not the same. Infinite means endless. You can keep going forever. There's no limit to how far you can count, how far you can travel, how much there is. Unbounded means no edges. There's nowhere you're not allowed to go, no barrier you hit, no place where you fall off the map. These are not the same thing. The surface of Earth is unbounded but finite. You can walk forever without hitting a wall. There's no edge to the Earth's surface. But you're not walking an infinite distance. You're looping. You can measure the total surface area. It's big, but it's not infinite. Same thing could be true of the universe. It might be finite in volume, but unbounded in structure. You could travel forever without hitting an edge, but the total volume might be measurable. That's not a contradiction. That's just geometry we're not wired to visualize. And here's the thing. Accepting this is like accepting you can't see infrared light. It's not a defect in reality. It's not a limitation of truth. It's a limitation of your perceptual hardware. Your eyes are built to detect a narrow slice of the electromagnetic spectrum. Everything outside that slice is invisible to you, but it's not less real. It's just real in a way you're not equipped to perceive. Same with higher dimensional geometry, with curved space, with unbounded finitude. Your brain is built to navigate 3 dimensions of space and 1 dimension of time using intuitions that work at human scales. Asking it to visualize curved space-time is like asking your ear to see colors. It's the wrong tool for the job. But you can understand it logically. You can work with it mathematically. You can recognize when your intuition is failing and trust the tools that work better. And that's not a defeat. That's an expansion. That's growing beyond the limits you were born with. Now let me throw another wrench in the works. What if beyond isn't a spatial concept at all? What if it's temporal? Everyone wants to know what's beyond the edge of space, but hardly anyone asks what's beyond the edge of time, what's before the Big Bang. And the moment you ask that, you realize the question is broken, because time started with the Big Bang. Before is a time word. It assumes time is already running. If time hasn't started yet, there's no before. There's no prior moment. It's like asking what's north of the North Pole. North is defined by the gradient toward the pole. Once you're at the pole, north doesn't point anywhere. The concept stops applying. Same with before and the beginning of time. Now here's the really weird part. Time and space aren't separate. Einstein showed us this. They're woven together into a single fabric called space-time. You can't have space without time or time without space. They're aspects of the same thing. So if time started with the Big Bang, so did space. There's no space before the Big Bang because there's no before the Big Bang, which means asking what's outside space is also asking what's outside time. And consciousness exists in time. Thought happens in time. The very act of asking a question unfolds in time. So trying to think outside the universe is trying to think outside the preconditions of thought itself. It's like asking a fish to imagine what life is like outside of wetness. Wetness isn't just the fish's environment. It's the condition that makes fishness possible. You can't separate the fish from the water and still have a fish. Same with consciousness and space-time. You can't separate consciousness from the framework it exists in and still have consciousness. Does that mean the question is meaningless? Not exactly. It means the question is pointing at something real, the limits of our conceptual framework, but it's pointing with tools that don't work outside the framework. It's like trying to measure love with a ruler. The ruler's a fine tool. Love is a real thing. But you're using the wrong tool for the job. Now I need to talk about something that pop science loves, that gets thrown around in every discussion of this topic, and that actually doesn't help at all. The multiverse. The idea is that there are infinite universes, or at least a huge number of them. Every quantum possibility branches off into a new universe. Or every region of space is its own universe, separated by cosmic inflation. Or mathematical possibility itself generates universes for every possible set of physical laws. There are different versions of the multiverse idea, but they all share this basic feature. Our universe isn't alone. It's part of a vast collection. And people love this because it feels like an answer. It feels like progress. What's beyond our universe? Other universes. What are they in? A multiverse. Problem solved. Except it's not solved. You've just kicked the can down the road. What's the multiverse expanding into? What's beyond the multiverse? What contains the collection? You've multiplied the question, not answered it. Now, multiverses might exist, I'm not saying they don't. There are legitimate physical theories that predict them, and some of those theories make testable predictions about our universe that we're starting to check. But as an answer to the boundary problem, to the question of what's beyond, they fail completely. Because either all those universes are embedded in some larger space, which just has the same problem we started with, or we redefine universe to mean everything, all the universes together, in which case we're back where we started. We've just renamed the thing we're confused about. The multiverse isn't a solution, it's a distraction. It lets us feel like we've made progress when we've actually just moved the mystery one level up and slapped a new label on it. And I think that's worth saying clearly because there's so much hype around multiverses, so much breathless speculation, and it can make you feel like you're missing something if you don't find it satisfying, but you're not missing anything. The dissatisfaction you feel is appropriate. The question isn't answered, it's just dressed up in fancier language. So where does that leave us? I've spent all this time telling you what doesn't work, what's broken, what's confused. Let me tell you what does work. What works is humility. Not the self-flagellating kind where you decide you're too stupid to understand, but the kind where you recognize that reality is under no obligation to fit inside your skull. The universe is bigger than your capacity to visualize it. That's not a flaw in you. That's not a flaw in the universe. It's just a fact. What works is curiosity without demand. You can ask what's beyond the universe and hold the question lightly, playfully, without needing it to resolve into an answer you can picture. You can let the question change you without it giving you closure. What works is recognizing that the question itself is an act of consciousness, and consciousness is the thing we understand least. We can map galaxies billions of light years away. We can predict the behavior of particles we've never seen, but we can't explain how a hunk of meat generates the feeling of being someone. We can't explain how neurons firing creates the experience of redness, or the taste of chocolate, or the ache of loss. And maybe those two mysteries, what's beyond the universe and what is consciousness, aren't separate. Maybe they're two sides of the same question. Maybe the reason we can't step outside the universe is the same reason we can't step outside our own experience of being. Maybe the boundary we're looking for isn't out there in space. It's right here in the gap between the observer and the observed, the knower and the known, the question and the answer. I don't know if that's true, but it feels true. It feels like the kind of thing that, when you really let yourself feel it, changes how you move through the world. Now let me give you something practical, something you can actually do with all of this. Next time you're outside at night, look at the stars. But don't think I'm looking out at the universe. That's the default thought, and it makes you feel separate, small, outside looking in. Instead, think I'm inside the universe, and it's looking at itself through me. Feel how that shifts things. You're not a spectator anymore. You're not separate from what you're observing. You're a fold in the fabric. You're the universe doing the thing that universes do when they get complex enough, becoming aware of themselves. It's vertiginous at first. It feels too big and too small at the same time, like you're going to dissolve or explode. But if you stay with it, it settles. And what it settles into is something like belonging. Not belonging in the sense of being welcomed into a club, but belonging in the sense of being a part of something you can't be separated from. You're not in the universe the way a marble is in a jar. You're in the universe the way a wave is in the ocean. You're made of it. You're a shape it's taking temporarily. And when you dissolve back into it, you're not going somewhere else. You're going home. Try that perspective flip regularly. Not as a meditation or a spiritual practice necessarily, but just as a different way of seeing. Like putting on glasses that correct for a distortion you didn't know you had. Here's another thing you can do. Sit quietly somewhere you won't be interrupted. Close your eyes. Try to find the edge of your consciousness. Where does you stop and not you begin? Is it your skin? Well, you can feel your skin from the inside and the outside. So which side is you? And what about the air touching your skin? Is that you? What about the light hitting your eyelids? What about the sounds vibrating your eardrums? Is it your breath? You breathe in air that was outside, and it becomes part of your blood, part of your cells. Then you breathe it out and it's outside again. So was it you while it was inside? Did it stop being you the moment it left? Is it your thoughts? But thoughts arise without your permission. You don't choose what pops into your head. You can choose what you do with it once it's there, but the arising itself is involuntary. So a thought's something you have, or something that happens to you. And if they're happening to you, who's the you they're happening to? Notice how the boundary keeps dissolving the closer you look. It's not that there's no boundary at all. Obviously, there's some practical difference between you and the chair you're sitting on. But the boundary is negotiable. It's contextual. It's a useful fiction for navigating daily life. but it's not a fundamental truth. And if you can't find the edge of your own consciousness, why would the universe have one? Boundaries are useful fictions, not fundamental truths. We draw them where it's convenient, where they help us make sense of things. But reality doesn't care about our convenience. This exercise, trying to find your edges and watching them dissolve, it does something to you. It makes you less rigid, less defended, more permeable. You start to see edges everywhere in your life, between work and rest, between self and other, between life and death, and you start to see them all as permeable, negotiable, constructed. And that's freedom. Not freedom from boundaries. You need some boundaries to function, but freedom from the illusion that boundaries are absolute, unchangeable, built into the nature of things. They're not. They're tools, and you can pick them up and put them down as needed. Here's one more practice, and this one's a bit more intellectual, but it's powerful. Write down your biggest existential questions, the ones that keep you up at night, the ones that make you feel small and lost and scared. Write them down as honestly as you can. Then go through each one and ask, am I asking about reality, or am I asking about the limits of my language? Is this a question about how things are, or is it a question about how I can talk about how things are? Let me give you an example. Why is there something rather than nothing? That sounds like the deepest question you can possibly ask. It sounds like the foundation of all philosophy. But what if nothing isn't a coherent state? What if nothing is just a linguistic placeholder for a state I can't imagine? Think about it. When you say nothing, what do you mean? Empty space? That's not nothing. That's space. No space. How do you have no space? What does that even mean? It's not like you're picturing an absence of space. You're picturing blackness, which is still something. You're picturing a void, which still has geometry, still has location, still has properties. Maybe nothing is just a word we made up, and it doesn't actually refer to any possible state of reality. Maybe the question, why is there something rather than nothing, is like asking, why are there true things rather than purple things? The categories don't match. The question isn't asking anything coherent. And once you see that, the question stops torturing you. You don't have to answer it anymore. You can just recognize it as a beautiful piece of language that points at the limits of language itself. A lot of your existential questions might be like this. Not all of them. Some of them are real questions about real things. But many of them are language problems pretending to be reality problems. And separating the two is incredibly liberating. You stop banging your head against incoherent questions and start getting curious about the coherent ones. Now, I want to bring this all together, because we've covered a lot of ground, and I want to make sure you're leaving with something solid, something that changes how you see yourself and your place in all of this. We started with a question. What's beyond the universe? And we found that it was built on assumptions that collapse under scrutiny. Edges, containers, outsides, beyonds. These are all tools your brain uses to navigate three-dimensional space and linear time at human scales. They work beautifully for finding your way home, for building houses, for throwing a ball. But reality isn't obligated to fit those tools. The universe doesn't have an edge because edges are relational. An edge is where one thing meets another thing. But if there's only one thing, if the universe is everything, then there's nothing for it to be in relation to. There's no other thing for it to meet. The concept of edge needs something on both sides, and there's no other side to everything. The universe doesn't expand into anything because it's not in anything. It's not a balloon in a room. It's not an explosion in space. It's the only in there is. Space itself is what's expanding. And space expanding doesn't mean moving into some pre-existing space. It means more space coming into existence. And if that breaks your brain a little, good. It should. It means you're starting to see past your default assumptions. But here's what we really found, and this is what I want you to carry with you. The question wasn't about astronomy. It wasn't about cosmology or physics or mathematics. It was about you. It was about consciousness trying to locate itself, to find its boundaries, to understand what it means to exist. And the answer, if we can call it that, is that you're not separate from the mystery. You're not a spectator standing outside reality, looking in and wondering about it. You're not a consciousness trapped in a body, peering out through eye holes at an alien universe. You're the universe interrogating itself. You're matter that got so complex it started asking questions. You're the means by which existence becomes aware of existence. And the fact that the question feels impossible, the fact that you can't visualize what's beyond, can't imagine standing outside everything, can't picture the edge of space or the beginning of time, that's not a failure, that's proof. Proof that you're asking from inside the only reality there is. Proof that you're not separate from what you're asking about. You walked in here, well, you clicked on this video, feeling small, searching for edges, hoping for answers that would make the bigness manageable, that would give you a map you could understand, that would let you relax and stop wondering. And I hope you're leaving with something stranger and better than comfort. I hope you're leaving with a sense that the bigness isn't out there. It's not something you're looking at. It's woven through you. You're not insignificant in a vast machine. You're the means by which vastness knows itself. You're how the universe looks in a mirror. And that's not comforting in a soft way. It's not a nice thing I'm saying to make you feel better. It's demanding. It's weight. It means you matter in a way you can't shirk. It means your questions matter. Your confusion matters. Your sense of wonder matters. Because without observers like you, the universe would just be. It wouldn't mean. It wouldn't know itself. It wouldn't ask why. So here's what I want you to carry with you. Here's the thing I want you to remember when you're lying in bed tonight, or walking to work tomorrow, or staring at the sky wondering about all of this again. The universe doesn't have edges. And neither do you. You're not lost in it. You're how it finds itself. Let that sit for a second. The universe doesn't have edges, and neither do you. Where you end and the world begins. That's a useful fiction. It helps you navigate. It helps you stay alive. But it's not fundamental. At the quantum level, you're exchanging atoms with the air constantly. At the conceptual level, you're made of stories and language and ideas that you didn't create, that came from outside, that passed through you and shaped you. At the existential level, you're a temporary pattern in the flow of matter and energy, no more separate from the universe than a wave is separate from the ocean. You're not lost in it. You're how it finds itself. The universe doesn't know it's beautiful until someone looks at it and feels beauty. It doesn't know it's vast until someone feels small. It doesn't know it's mysterious until someone asks questions. You're not outside that process. You're the process. You're how the universe does the thing it does. And if that makes you feel big and small at the same time, like you're everything and nothing, like you matter infinitely and not at all, good. That's the feeling. That's what it feels like to be awake to what you actually are. You're not broken. You're not missing something. You're not too small or too stupid or too limited to understand. You're exactly what you need to be. A finite consciousness asking infinite questions, a temporary pattern wondering about eternity, a piece of the universe shaped just right to ask what shape the universe is. If this shifted something in you, even just cracked open a new way of seeing, even if it's uncomfortable and you don't know what to do with it yet, I want to hear about it. Leave a comment. Tell me what clicked, what still feels broken, what you're going to sit with. What questions are you holding differently now? What answers did you use to cling to that you're ready to let go of? I read the comments. I learn from them. You teach me the same way I'm trying to teach you. And if you want more of this, questions that don't have answers but change how you hold yourself, ideas that don't resolve into comfort but expand into wonder, subscribe. Hit the like button if something here resonated. Not for the algorithm, though that helps, but because it tells me you want to keep going deeper. It tells me there are other people out there who feel the way I feel, that the biggest questions are worth asking even when they don't have answers. Especially when they don't have answers. Now go outside, look up, feel the night, the stars, the vastness. And remember, you're not looking at anything. You're the looking itself. You're the universe becoming aware of the universe. And that's not small. That's not meaningless. That's the only meaning there is.